Are you ready? Okay, just before we start, a little plug about ICAS 2024. So as you can see, this is in beautiful Stresa in Italy. It's going to be a workshop, again, around modernization of software, challenging around data curation and data services. And then also, how do we respond as centers to changing workforce? So we're working on the call for paper, so just put this in our calendar. And we are working on the call that will come out probably early next year. So thank you.
Thank you, Thomas. All right. Welcome back, everyone. We'll kick off the second day of Correctness and Reproducibility workshop. So we'll kick off with a keynote from John Baugh from North Carolina State University. John Baugh is a professor of civil engineering and operations research at NC State. His research focuses on formal methods and verification and tailoring of tools and practices to support the specific needs of scientists and engineers. And he works on problems in scientific computing, cyber physical systems, and mathematical optimization and control. And he received his PhD from Carnegie Mellon University. So he will introduce the lightweight formal methods as a means to getting more correct scientific software. So by the way, he's my PhD advisor from NC State. So he also introduced me to this idea about how we should get better and more correct scientific software. So I'm quite excited to hear what I'll present today.
All right. Well, thank you, Alper, for the kind introduction. And thank you also, Allison, for the opportunity to be there and to speak with everyone today. Am I audible? Everything okay?
Yep. Okay.
Sure. Thanks. And thanks all for being here. And sorry I can't be with you in person today. In this talk, as Alper says, I'll try and answer the questions: what are formal methods, lightweight formal methods, why I think they're useful, and how we might employ them. It's an approach that's not tied to a particular programming language or framework or technology. So whether you're writing Fortran or Julia or OCaml, or maybe you use MPI or something else, I hope you'll find something that is relevant for the kinds of things that you're working on. And so I personally have found lightweight formal methods to be both practical and useful, and importantly, applicable to problems in computational science and engineering. Indeed, I'm in a department of civil engineering at North Carolina State University. And I teach these ideas to my students, primarily in a course called Computer Methods, CE 537, that I've taught every fall since 1989 for first-year graduate students and seniors. The students in the photo, by the way, are participants in a steel bridge competition that's held annually by our professional society. Well, it's easy to get things right when they're simple. So if we're talking about correctness, I think in a way we're talking about managing complexity, and there are some historically useful strategies for doing that. Abstraction, separation of concerns have been mentioned, engineering tools, progressive codification. With respect to engineering tools, and analysis models, well, we all work with models, and we know what it's like to do that. So the suggestion here would involve us in building models of software the way we build models of physical and scientific systems. Well, here's a working definition of model: a simplified representation of reality used to provide insight. So it's about providing insight. Well, how is that useful? Well, it's about organizing knowledge about a given system in a way, taking a step back, trying to understand all of the moving parts. And so that seems to be important. Well, anytime you define a system, you talk about system boundaries, what's in a system and what's not in a system. I like the quote here: system is what is distinguished as a system. It sounds tautological, but I think there's some truth there. When it comes to modeling software, the kinds of things that we're talking about here, the models need not align with language structures. So, and importantly, we don't have to model entire systems. We can focus on parts that are particularly tricky or complex that warrant a little extra attention. One concern about doing something like this in large-scale systems is, well, when you try to extract a piece, when you try to cut out something like this, how can you do that without bringing in the entire environment? Well, the short answer to that is model finding, and I'll say more about that in just a bit. A caveat on the kind of models that I'm talking about: I won't be addressing floating point arithmetic today, a hugely important topic, as we know, though I will talk about number systems and abstract domains, which we need. Now, with all that as a backdrop, in the remainder of this talk, I'll describe, as I say, the what, why, and how of lightweight formal methods. And I'll begin with the path that I took, and some formative experiences that informed my thinking. I'll also give some rationale for why I think lightweight formal methods are useful. And I'll do this in one way by showing some examples of work that's already been done from a somewhat of a high-level perspective, just to give the flavor of what this is about, if not all the details. And then I'll take a little bit of time to talk about the how, provide some more details on alloy, and talk about things like heap invariance and a little example problem in pipe network analysis. It's a simple problem, but it illustrates some of the thinking about the modeling approaches that I guess I'm advocating for. So some formative experiences. We've all had certain kinds of experiences that shape how we think about things. As an undergraduate, I took a finite element course, and we were given a program that we were told that we could use with the understanding that it was buggy. And so we had to debug it. In that era, the turnaround time at the computer center was a day or two to get the results of a run. After that course, I thought that, well, there must be a second course in Fortran programming that I need to take, but I couldn't find it. Later at a national lab, I was asked to add a new spline type in a solids modeling package. And my vivid recollection of that experience was staring at reams of green and white fan fold paper, looking for the splines, which in reality were just arrays of indices into other arrays of indices, and so on. And so there was no real notion of splines in that package. We had something more like what's on the left of the image than what's on the right, where there is some information hiding, logical firewall, separating out the use of an abstraction from its implementation. Later still, once I went back to graduate school, I took a number of courses that were influential, one of which was by the late John Reynolds on structured programming and program proving. In his syllabus, he wrote, "The fundamental goal is the ability to write concise, clearly documented, and logically correct programs. Students will write short programs without executing them on the computer, and these exercises will be evaluated for style as well as logical correctness." Well, that was an influential course, as I say. In that, we learned about Floyd Hoare logic. and with the idea that program fragments can be specified, their behavior, by providing a precondition and a postcondition, with the interpretation that if one executes S beginning in any state described by a state predicate P, and if S terminates, then S will produce a state described by the state predicate Q. Well, this is a partial correctness argument. It's can be viewed as a safety property. Termination is a separate argument, as Ganesh said yesterday. Well-founded sets, other ways of trying to prove separation, but it's usually easier to do that separately. Some of the kinds of programs that we started with, very simple iterative ones to begin with the notion of preconditions and postconditions, and importantly, the idea of a loop invariant, something that's not changing as the loop body executes. That allows us to conclude something in the postcondition, since we know that Z is equal to X times K, and because of the termination of the loop, K is equal to Y, we can conclude that Z is equal to X times Y. Well, that's a simple problem, but it gets into one's mind the kinds of machinery that one needs, and the kinds of verification conditions that are necessary for arguing about correctness. A little checklist here for iterative loops, achieving the loop invariant, showing that the loop body S maintains the loop invariant. So if the invariant holds before and it holds after, then there's an inductive type argument that we can use that the program is correct. Well, fast forwarding to what I do in my 537 course, now we generate verification conditions in Julia. And so some of this is automated. It's not pencil and paper as it was back in the 80s, and discharge them using Z3. And so this is a little example of something that we do where P is a state predicate, Q is a state predicate, and S is Julia code. Well, the perspective here is that formal methods are studied not as an end in themselves, but to reveal what constitutes a precise specification of program behavior, and what constitutes a rigorous argument that a program meets such a specification, to give a sense of whether that kind of effort is helpful or not. I guess my thinking on this is that programs that are easier to reason about, where the arguments that it's correct are made, are easier to understand, and that's what I try to teach. So what we're talking about here is static analysis, trying to make sound guarantees about the behavior of a program. A lot of tools have been advanced, and with a lot of different proponents, generally falling into categories of theorem provers that work deductively, model checkers that are more like exhaustive enumeration, and then more recently, model finders. So lots of instances of these in functional programming language, media like Haskell and OCaml, Cock and Isabel. But we're down here today with model finders. That's what I'll be talking about. Well, if you're going to employ tools, there are different ways of employing them. Some have suggested that they disappear. Formal methods tools should disappear into familiar environments. So they're put into predictive editors, they're put into compilers, they're put into all kinds of things that don't disrupt the normal workflow that we have. A contrasting opinion is that formal methods might be used to influence design, and that's the perspective that I'm taking here. Certainly being able to do this gives you a medium for being able to do something a lot more flexibly than we can do in traditional programming languages. So I'm talking about Alloy, a language and tool for exploring software designs. This is an article in Communications of the ACM in 2019. I encourage you to, if you're interested, to visit the link, which has a little video by Daniel Jackson and a nice article describing the tool, and we'll get into more detail than I can get into today it's a nice overview that also includes applications. Well, what is Alloy? It's a declarative modeling language, so it's first order logic, relational calculus, and something called transitive closure that allows us to express rich state in a convenient way. And I'll give you some examples of what I mean by that. Certainly in scientific computing and engineering computing, those are some of the more pressing issues, I believe. It like other analysis kinds of approaches that we use, it's push button analysis, so it's not about trying to prove theorems. It's about getting feedback on models in an iterative way as we begin building them. It does this by compilation to the Boolean satisfiability problem. And this turns out to be important because there's a lot of effort in trying to improve the performance of SAT solvers. They're used widely in a lot of different contexts. And so there's a lot of pressure there to try to improve performance. And historically, the performance has grown greatly. And so Alloy can always take advantage of the most recent solvers. Well, first order logic is undecidable. The Alloy chooses a nice balance here by making use of scope complete checks, relying on something Daniel Jackson has promoted as the small scope hypothesis, that a high proportion of bugs can be found by testing a component on all inputs within a small scope. And we've certainly found this to be true in the problems that we've looked at. Lots of case studies in Alloy in almost every area you can imagine, thousands of applications. And I have a link there to the Alloy website that describes many of those, as well as success in finding lots of bugs in real software, some that are safety critical, neutron radiotherapy machines, the Cord protocol, WebAuth, and others. All right. Well, the why. A lot of discussion already has been had on challenges that we have. These have been documented, reproducibility concerns, retractions of papers in journals, and about domain characteristics, things that are different about scientific computing than computing in other areas. A lot of different paths to improvement, people suggest. Storer in a survey describes many of those, and also adds formal methods as a quality assurance practice, with the caveat that they've received considerably less attention in the scientific programming community, possibly due to the additional challenge of verifying programs that manage floating point data. Well, is there a role for tools like Alloy, which are about structured modeling or object models? Rich state is something that's certainly a feature of the kinds of models that we deal with, and complex behavior with various forms of parallelism that are used to try to improve performance. So in that sense, it seems like Alloy is a good fit. But it doesn't have a theory of reals. And so one can fairly ask, well, what about the reals and how are those handled? Well, to my mind, it's a matter of separating concerns. We naturally think of, when we look around at physical processes, we imagine them to be continuous. But the computational apparatus that underlies many of the things that we look at are really an amalgam of data structures, algorithms. And so my little equation for thinking about scientific software, scientific programs, is that it's a combination of the numerical things and a lot of interstitial machinery. And it's possible to get the interstitial machinery wrong and still have plausible results. And so that turns out to be a problem. Well, a touchstone for all of this, to me, is what happens in real life. And that's almost all of these kinds of applications, models, have a theory report. and that deals with numerical analysis, convergence, various kinds of concerns, with a lot of different implementations. And those implementations on high performance machines might either be right or wrong. And the question I have is whether we have to work with what I call here the sometimes deep semantic proofs of numerical analysis to be able to say something about correctness. And my argument would be that I don't think we have to. But we still have to work with properties of numerical expressions. If we view that as a tower or a ladder, I would try to be here to the extent that I can, as opposed to working with reals or even worse, floating point numbers for many of the kinds of checks that I think can be done, where we can draw, I think, useful conclusions from just a subset of the properties of the kinds of numerical domains that we have. Other kinds of approaches, predicate abstraction, we've used, where the idea is that if two models are performing the same kind of floating point test and are being compared in some way, then we might substitute a common term for them and dispense with floating point reasoning altogether. A lot of other abstraction techniques, some involving things like interval arithmetic and over approximation, that can be used also to help with correctness arguments. In other words, we may not need a decision procedure for real numbers at all, and it may not be helpful even if we have one, and I'll give an example of that later. So some high-level views of work that we've done using Alloy and AdCirc. AdCirc, a widely used ocean circulation model by the U.S. Army Corps of Engineers, FEMA, and others. And as part of this project, we were working on a technique we called subdomain modeling, where the idea was to be able to extract part of a mesh and be able to impose boundary conditions in such a way that tinkering could be done with a small part of the mesh without doing large-scale reruns of these kinds of models. One of the complicating aspects of that are the contingent processes that often happen whenever we're dealing with things like this. Wetting and drying is implemented in AdCirc with a series of empirical rules based on physics, but it's a collection of empirical rules, and the implications of them all together is difficult to reason about. Here's some pseudocode that shows what that wetting and drying algorithm is like. It involves elements in AdCirc. It involves nodes, both of which have wet-dry states, and the wet-dry states of nodes influence the wet-dry state of elements, and vice versa. And so showing that an extracted subdomain behaves like a full domain was something that we thought was complex enough that it warranted modeling in Alloy. And the comparison that we're doing here is, well, we have a full domain model in Alloy. This is for AdCirc, and a subdomain model in Alloy, again in AdCirc. And then using the Alloy analyzer to ask, do they provide the same final wet-dry states? One of the nice things about doing this kind of modeling is not just that you can take a hypothetical implementation and check it, but that you can also do some iterations on this where you're adjusting the boundary conditions and sort of asking the what-if question, does this amount of state and the way it's being imposed on the boundaries actually give us the same kind of behavior? So that kind of analysis is in fact quite useful. Without getting into the details of Alloy just yet, I'll just mention that one of the basic aspects of the language is defining signatures, which here allow us to talk about mesh-like things triangular-like things, vertex-like things, with various kinds of conditions. And that's was the basis for the kind of modeling that we did. Well, Alloy is a model finder, as I mentioned before, and so it's able to generate, here's just a sample of the possible mesh topologies that wetting and drying might be applied on. And so it automatically does this. This is not some algorithm or some constructive approach that we have to come up with ourselves. We define the invariants, the heap invariants, and Alloy finds those for us. And so the entire model consisted of a number of different kinds of things that we see, as I say, triangles, vertices, elements, nodes with various kinds of physical properties. And so the observation that I would make on this is that, well, Alloy allows experimentation along the interface in the manner in which state is used to enforce boundary condition, and it's Alloy's model finding ability that does this for us. So mesh topologies are defined implicitly by declarative properties. As I said, no algorithm is needed to devise or produce them. The same project motivated another study on sparse matrix computations, where here the primary motivating aspect was dealing with the interdependencies between sparse formats and solvers, and being able to use one in one context and not in the other. And do you wind up translating between sparse formats? There's direct assembly from meshes into a sparse format. Do you redo that? Do you impose boundary conditions before or after? And just a lot of places where mistakes can be made. And importantly, where even with mistakes, you have the worst possible situation where you have plausible results that are wrong. The verification approach used in this study was different than the first, where an abstract model is used for comparison. So we can say in an abstract manner what we mean by matrix multiplication, what we mean by matrix transpose, and then we can ask, is there a concrete implementation of that, say using sparse matrices, that is faithful to that implementation? Well, this commutativity diagram is the way in which that kind of verification is done, where we try to show that if we start with a sparse matrix, an arbitrary concrete sparse matrix, do something like transpose to get another one, and then view that as an abstract matrix, that we would get the same thing as, first of all, asking for the abstract matrix, and then performing our abstract notion of transpose. And so the bottom line is there that we want programs that work with either sparse or not sparse matrices to behave the same. A little more Alloy, same kind of thing with signatures here, where we're doing symbolic comparisons of expressions, where there's just one distinguished real number, 0, and then various other real numbers in the kind of analysis that we do. As I say, it's easy to extract and spot check fragments from large code bases. The surrounding state is generated by model finding. And we did find bugs and inconsistencies between code and documentation. And made some other, from the codification point of view, the historically useful strategies for dealing with complexity, a little tabular idiom that makes doing this kind of modeling look more like imperative code. And so it's convenient to do. I'll say less here. This was a little a prototype that we undertook just to see what we could find out about some parallelism issues in coarray Fortran, sometimes difficult to debug with a little Jacobi iteration. solver. So it's just sort of a proof of concept whether we could find bugs in solvers like this, where we're doing domain decomposition and halo exchanges in images that are residing on different processors but are accessed or able to be accessed by other ones. And so we found that to be a nice way of finding bugs that are otherwise difficult to find in things like Core Fortran. We also made use of this idea of commutativity diagrams to carry out those that verification. The how. So I'll turn to a little engineering application. And this, in fact, is a problem that I gave in my class this semester on water distribution networks, widely used, obviously, in civil engineering analysis and design, EPA Net being the primary tool that's used. But I'd like to go back a bit further, all the way to the 1930s, an algorithm, probably one of the first interesting algorithms in civil engineering, that was developed by Hardy Cross. And of course, this was before computers were around, for pipe network analysis. And so I'll say a little bit about the method and try to give you a sense of how I think it makes sense to, if we say we want to verify an implementation, this is certainly simple and we can probably wrap our heads around that and do something without tools. But it is interesting to ask, do formal methods tools, lightweight formal methods tools have a role here? So I'll say a little bit about how all of this works. Well, the Hardy Cross method was a hand method because this predates computers. It revolutionized water supply design. And the idea is to iteratively find the flow in pipe networks. These are nonlinear systems of equations. And so this really was an advancement on what was done before then. And it still remains as the method that's most often taught to civil engineering students. The first computer implementation of the method was in 1957. And then it was widely used after that on a lot of different computational platforms. The method itself draws on some of the basic principles of physics, conservation of mass, conservation of energy. Those must be satisfied. As Hardy Cross says in his paper, the physical conditions controlling engineering relations often consist of two groups of laws, which are quite independent of each other. And so the idea is to hold one steady, continue to maintain that as an invariant, and then try to achieve the other one. This is commonly done. And so it's a nice little application, a simple application of those kinds of ideas. One of the methods that he proposed is the balancing headwinds, where you say, I'm going to start by ensuring that I always satisfy continuity, flow continuity. And then I'm going to try to find counterbalancing flows that will maintain continuity, but get us closer to balancing heads. Just like in an electrical circuit, energy has to balance as we go around the loop and get back to where we started from. And so to me, this is interesting from a computational perspective, and just, what would it mean to verify the correctness of an implementation of Hardy Cross? Well, I'll go back to the kind of Reynolds, Floyd Hoare type thinking there, that there's a wild invariant that we would like to maintain, the continuity of flow. And in the loop body, we would like to revise flows in a way where we maintain that invariant. Termination condition being that heads in any loop are unbalanced. And so when we get to the post condition, the negation of that, from that, we can conclude that all heads are balanced and there's continuity of flow. Among the verification conditions, and we can check as many as we like, but one that seems important is that the loop invariant is in fact invariant, and it's invariant over a rich state. And so this is where alloy shines for some of the simple problems like we first looked at with multiplication by repeated addition. Solvers like theorem provers like Z3 are quite nice and helpful. But when you talk about rich state and being able to describe arbitrary pipe networks with arbitrary kinds of decisions about how the heap is being managed, then being able to do this kind of check is actually quite useful and does allow us to find flaws in how we're thinking about our representation of the physical system. Well, so that's what we hope to do. One concern might be, well, you say, well, you know, I want to bring in a theory of reals and use that to prove properties of reals. Well, even in the very first computer implementation of the Hardy-Cross method, Hoag and Weinberg, they noticed there were convergence problems. There's oscillation. You can see in the solid line, there's oscillation. And there are ways of improving that through smoothing, numerical damping, different kinds of ways of trying to improve convergence. But sometimes the method does not converge. And so is that a stopping point? So as with Newton-Raphson and other nonlinear solvers, the Hardy-Cross method may fail to converge. Does that mean that verification is impossible? Well, my argument is that it's not. It's certainly possible to implement the Hardy-Cross method, and the result can be either correct or incorrect. So we can recognize that convergence is a termination condition and prove the safety property. If the program terminates, the results are correct. That's the idea. So to get a sense of what this little exercise is like, and I'll bring in some of the computational issues and how do you represent this in a language like Julia, and some of the modeling issues in alloy, recognizing that I won't be able to do that in really sufficient detail, but I'll post the model on my website and be happy to send and interact with anyone that would like any more details on this. But these are the kind of problems that we're talking about here, where the inputs are the sources at the 4 nodes, an inflow of 100, an outflow of 20, and so on. And the flows that are appearing on the edges, those are just proposed. That's an initial step that's required in the procedure. These satisfy continuity, 100 in, 70 plus 30 out. But if you go around a loop, conservation of energy is not maintained. And so this is an iterative process to get there. And so those counterbalancing flows based on the Hardy-Cross method get calculated and then get applied. We're still satisfying continuity here, but we're now closer to balancing heads, satisfying principles of conservation of energy. Well, a simple implementation of something like this might make use of the adjacency structure, adjacency lists, or adjacency dictionaries in this case, dictionaries of dictionaries. And so you can imagine a little implementation like this, where the adjacency representation, say, for instance, edge 2,4 has a flow of 35. So from vertex 2 to vertex 4, we have a flow of 35. If you go down that route and you implement that in Julia, just a little simple implementation, the thing that you'll see is it's easy to find your out edges, as you might expect from an adjacency structure. But finding inflows, the edges pointing in, well, that requires linear search of the entire network. And so you say, okay, well, this might be okay for a small pipe network, but it's not going to be appropriate for something that's a bit larger. So you imagine, as we always do, some sort of a way of improving computational efficiency, where we're trading off memory or execution speed for space, vice versa. And so here we have reverse edges that will maintain, with the idea that there's going to be some heap structure that's going to maintain that. There's going to be some sharing involved between edges. They're going to be signs. So in the dashed edges, these are, because they're reverse edges, they have perhaps a negative sign associated with them. And then the assumed direction of flow, they have a positive sign, but recognizing that the scalar flow quantities might be positive or negative and cause a reversal in flow. So there are a lot of little nuances there of trying to get that right. And it certainly is possible to not get that right. And like I said before, to get results that are plausible, but are in fact wrong. And so we wish to show, as I said, that the continuity of flow is an invariant. And so this is all about doing something that Alloy does well. It does many things well, but one of which is thinking about building object models. And so we can do all of this in Alloy and do some checks. The main idea here is that if the loop invariant I doesn't hold, well, there's some conceptual error there in how we're doing sharing or aliasing of the various components in the heap. And we can use Alloy to help us find those. So as I say, well, we can carry over these global invariants that we find as a result of this process into actual code. So this is a view of object models as heap invariants. Well, to say just a little bit more about Alloy and to describe what that process is like, Alloy works with atoms that are uninterpreted, immutable, and indivisible, and relations that associate them together to create structure. And that's what Alloy models are like. Everything in Alloy is a relation. And so an example of using that here in our little pipe network problem is to say, well, okay, I'm going to start with something simple. This is an entire Alloy model. This says, okay, there's some things in the model that I'm not going to try to represent at this point. I just want the notion of nodes connected to nodes. And that's what's being represented in this signature. And Alloy relies on a pun that makes this look a lot like object-oriented programming languages with classes and fields, and a lot of similarities there in how things work, where nodes map to nodes and also have an attribute hanging off of them. And an attribute is just some objects that have a particular identity. And so in this case, we can ask Alloy, give us an example of an instantiation of that. That's the model finding part of Alloy. And the notation here just says from node 1 to node 0 is attribute 1, from node 1 to node 2 is attribute 2, etc. You say, well, that's, maybe that kind of representation is not clear. So maybe I'll look at a textual version of that. So we have a variety of attributes that get populated, nodes that get populated, and then relationships that constitute edges from node 1 to node 0, as I just said. And then there's some notation here that I can't describe in detail now, but there's a little bit like a database join, and also, as I say, relying on a pun, like in object-oriented programming languages, a box notation that's a little bit like dictionary or array lookup. And so this is what it's like to start building an Alloy model. In terms of the visualization, there are a lot of customizations that can be made. I won't describe that in detail, but I'll just say this doesn't look like a pipe network, but this looks closer to what I might imagine as a tiny pipe network. And so there's some magic there that you can do in Alloy with functions to create named relations and get visualizations that are actually more intuitive. If you try to generate more instances with Alloy, you'll start seeing some things that do not look like pipe networks at all. And so at this point, you say, well, there are certain kinds of requirements that I think must hold for a pipe network. Maybe I'm imagining adjacency. Maybe I'm imagining that the graph is connected and has no loops. And I can begin imposing those kinds of things. Again, I'll not go through the nuances of the syntax of Alloy, but just to say what it is that we're doing and the kinds of results that we're getting. And so once we impose those kinds of facts, we start seeing some more things that, okay, they look like things that we might expect a pipe network to look like. Now, and then we can begin doing even more embellishing, where now we have the notion of nodes that have flows. We have the notion of edges that have signs associated with them. So the reverse edges that are dashed carry a negative sign, perhaps. We have the notion of pipes. And the idea here is to represent the basic kind of features of pipe networks that we need. We're using integer values for flows because we don't need multiplicative inverses like we would need for a field with real numbers. And so, as I say, a lot of that we can do without reasoning with decision procedures for reals. Examples of assertions that constitute heap invariants. Edge signs have to be +1 or -1, and anti-parallel edges have to have opposite signs. Some, as I imagine, an object model for this may be in the style of the Gang of Four design patterns kind of thing. A pipe is shared by two anti-parallel edges. And so we can say that in the Alloy notation. Flow computations, net flow at a node should be 0 if we want to maintain a flow continuity. And we want to be able to increment flow in a pipe and around a circuit, and little predicates can be defined that allow us to do that. Well, getting back to the loop invariant and seeing if we can actually prove that, I'll focus on the bottom here. Does the invariant hold? Here's the implication, the logical implication that I said we had to say something about. Again, this is Alloy syntax, but it says that the heap invariant, which in this case is continuity of flow, has to be satisfied. And then if we revise flows in an arbitrary circuit, so we're not saying a particular loop, we're saying any loop that Alloy can find, we have to specify what we mean by a loop. Implies that the invariant holds after we've done that. And so that's an example of imposing an assertion, looking for counterexamples. And I'll just say that in terms of finding bugs, Alloy is ruthless. If there is a flaw in your thinking, it will find it. So results of the exercise, well, the results are the object model and the associated heap invariants. And this allows us to conclude that continuity of flow is assured if we have an implementation that matches our model. And I've said it's a simple problem, but it demonstrates, I think, that much can be done without a general theory of reals. As I say, we don't need multiplicative inverses here, and we're able to draw useful conclusions without reals. And I think the other thing it shows is that the boundaries of declarative models can easily grow and shrink. I very quickly said something about loops, but I didn't say how I specified them. But I did specify what is meant by an arbitrary loop in Alloy, but I could have just as easily said, well, how do you construct them? Okay, there's a little breadth first search thing for finding a spanning tree, finding cycle bases. And so that little process, if I wanted to add that to my model, I can. So I can easily intermix things that are more like specifications and things that are more like implementations, and I can choose to check what I want to check. And this is part of why I can, when using Alloy, and a tool like that, carve out boundaries and put into a system what I want to be in the system and leave out of the system what I'd rather not try to handle. So I'll try to wrap this up with conclusion. So lightweight formal methods, are they useful? Well, I think all tools are useful in some context, otherwise they're not tools. The real question is, are they useful enough? And I think that kind of sentiment has been expressed in the talks yesterday. Is a tool, is it worth learning and gaining proficiency? Well, if it's versatile, if you can apply it to lots of different kinds of problems, and I would say that Alloy, to me, I teach also an undergraduate course in, well, we call it systems engineering, but it's mostly math programming with linear and integer programming, and we use tools like Gurobi and Cplex and Lindo. Alloy has exactly the same kind of feel with that kind of versatility. And that's why I'm more or less a proponent of the approach, because you can use it for so many different kinds of problems. You just have to bring to the table the kinds of aspects of your problem that you care about and think about what it means to formalize them. And I guess the last point is that that all of this, to my mind, is complementary to the historically useful strategies of managing complexity that I've mentioned before. It fits well there, and so I think it is a useful tool. Well, I'll end on some of the books that have informed the perspective that I have, and these are some of the books, in fact, that we use in my 537 class, including John Reynolds' Craft of Programming. All nicely written and ones that I would recommend. Well, I'll stop there and I thank you for your attention, and I'd be happy to answer any questions if there's time.
Thank you, John. Questions?
Hello, thank you for the very nice talk. So I guess my question is going back to your example with AdCirc, which is sort of like this big comprehensive model and quite a lot of Fortran code and quite a lot of dependencies. Like you need to have wind fields and you need to have like vegetation fields that you pass in. So could you speak to that particular example on what the effort was to apply Alloy to something on that level, as I would say? So,
Yeah.
how difficult was it to work with such a big code?
Well, the thing that I guess the nature of the verification task, we viewed it as a verification task. The nature of that task, as we defined it, was to compare what we felt like is an improvement in terms of runtime speed with something. So we're comparing two things, and when you're comparing two things that are alike in a lot of different ways, all of the kind of things you're talking about in the subdomain, exactly the same in the full domain. So subdomain, full domain, all of those things are the same. So the verification effort says, okay, let me model what is different about the full domain and what's different about the subdomain. And so just like I mentioned with like sort of predicate abstraction, many of those things kind of fall away. And so we're not handling wind speeds. We're not, those parts of computations are being performed in exactly the same way. It's what are the differences? And so when it's that delta, it becomes easier to do that modeling.
I guess actually my question was more to the actual effort to make that work. So like AdCirc has an executable that you can run, but did you have to go into the Fortran code in order to extract the pieces that you care about in order to use? How does Alloy, I mean, so if someone sat down, a grad student had to sit down and actually make this work and understand the code and then understand Alloy. And so I guess it would be illustrative to understand, if we were to use something like this in our climate codes, which are also very complex and not always easy to just wrap something into, right?
Right.
To what context is that the effort? Like if someone were to do a similar study, what would that entail? So that was more my question. question.
Right. So let me just share my screen again, if that's okay. I'm not sure how things look there, but if that's okay, I'd like to do that because I'd like to show this wetting and drying algorithm. So this is our pseudocode. There's obviously a Fortran implementation of that. And we did not use, people do this in formal methods. They create tools to automatically extract pieces of code, fragments, and get them into a formalism, syntactically even, that they like and want to work with. We did not do that. Obviously, we looked at the Fortran, we interpreted it, and built the alloy model around that. So there's a little, there's certainly some more detail here. The idea of transition semantics and moving from one state to another, and how those things work, and how you model imperative code. And so that in and of itself, there's a learning curve there. So I be quite straightforward about that. But these are things that, to my mind, help programmers understand the machinery, what really is happening in programs, and abstracting the parts, distilling away, things that really don't matter, and being left with the things that really do matter. And so that is at least as we've done it, it was a manual process. We have imagined that there might be something more automated to do that. But we really wanted to kind of see, well, in a way, we wanted to see, are the tools useful? Do they work? Do we wind up with scaling problems where you can't do anything useful? And so we didn't start by thinking about coming up with elaborate tools, but just whether we can take off the shelf and use this in a way, like I mentioned with Garobi or Lindo, or one of these MILP solvers or something. Can we make use of that tool in a way that allows us to draw conclusions? I'm not sure if I answered your question, but it was a human manual effort of extracting models from code. And yeah, that requires some judgment.
Yeah. John, hey, this is Ganesh. How are you? Hey. So I have two comments, and one may resonate with the people who are used to thinking about loop invariance, and other may resonate with people who know a ton more linear algebra than I do, but I think there is a problem. The first is that even though IEEE has formalized floating point, we are in deep doo-doo if you try to write a loop invariant for a simple loop under the IEEE floating point semantics. We can of course write a loop invariant which is true. True is true always. That's an invariant, but it's a useless invariant. But if you try to write any tight invariant for any almost any non-trivial loop, nobody has an answer even to date. This is one of the biggest problems in transitioning from whole logic reasoning of real number programs to floating point, in my opinion. If anybody knows a solution, I would like to hear. Okay, that's the programming language part. So the long story short is we can't write a loop invariant. My claim is we can't write a loop invariant, meaningful loop invariant for any loop with IEEE semantics even. Without IEEE semantics, the hell breaks loose.
Well, sure, okay. Well, yeah, if you don't mind, I'd like to respond. The question is, can we do something that's useful now? If you talk about IEEE semantics, catastrophic subtraction, round off, these kinds of things, these are important problems, and people are working on them. And I think my position is that, well, I won't say that it's overrepresented, but I think that some of the other things are underrepresented. And so my effort, if I view this as kind of a position talk or a position paper, is to say that the design of programs in a way that makes use of this kind of formal reasoning is underrepresented. So floating point is a big deal. But for even, I mean, here we're talking about continuous processes. We're talking about modeling engineering systems, and we're talking about invariants that have to hold. Now, if I'm doing this in floating point, and in my students, I implemented this in Julia, there's an approximately equal to kind of a thing. And so I guess that, there are all kind of polemics here. In fact, I had a slide on the polemics all the way back in the 80s. Program verification, the very idea. That was a paper by Setzer. And he argued.
Quickly interrupt you. I think I'm not criticizing what you said. I really loved the message. I'm only indicating the next step forward where the formal methods community has an open challenge. That's what I was really see it taken forward. Yeah.
Right. I think that the main thing that I would say is, does this help finding bugs? And actually in building some of the little Julia code and modeling it in Alloy, bugs were found that where you can have plausible results that are actually wrong because the heap invariants are wrong, and you've misinterpreted how pipes are shared by edges, as an example. So again, I take that, and I appreciate your comment. I guess my hope is to see if some of these ideas might find traction in just as they are. I mean, I know there's a lot of work to be done, but I think the technology is there, the approaches are there that are actually helpful for real programmers that are doing real things.
I can definitely violently agree with you there. Yeah, I'll save my second comment for a later.
Yeah. Ganesh and I, by the way, we're working on projects together. We have a lot of nice back and forth. So
my class during the COVID days, and I really learned a ton. So I really like to needle John a little bit occasionally. Okay, thank you.
It's much appreciated.
Let's thank John again.
Thank you.
So our next speaker is Dominic Orchard from Department of Computer Science and Technology, University of Cambridge, and School of Computing, University of Kent.
Great, thanks very much. Can you hear me fine? And see? Can you see and hear me okay?
Yeah.
Great. Okay, thanks very much. It's great to be speaking to you all. I gave this title of my talk almost as a provocative thing to myself to think about what could the next 30 years of software verification and climate science look like. I probably should have gone with something a little bit more modest, like 10 years, but we'll see what we can do as we go on. So I'd like to just make a few points of terminology clear that I'm going to use in this talk, thinking about sort of making clear what verification versus validation means here. So validation is, did we implement the right equations? It's about the science. And verification is, did we implement the equations right? Does our software do what we intended it to do? Now, another terminological thing I'd like to make clear up front is when we talk about verified software, it's a bit of a bugbear for me when I sort of hear things about things being fully verified. Well, I think verified with respect to what? And of course, we mean verified with respect to a specification. And we've heard people making this very clear yesterday and today, so that's great. Essentially, we're thinking we have some procedure where we take our implementation and we compare it against some specification, and we see does the implementation conform to it. Now, from this perspective, validation then is also verification, but where the specification is some kind of approximate equality or some relationship with observations of the real world. So it has the same kind of characteristics in that, but the specification is really external. It's what we see in our universe, and we want to compare that in some way to our implementation. That's just a minor aside. But I think another thing to be clear about is that then the important thing is what our specifications actually give us. The value of our specifications is what we make of them. And the specifications really depend on what our goals and our values are for our software. And especially important then to think about that in the context of climate research. So what I want to do in this talk is to kind of very, very quickly go through sort of some of the state of the art, not all of it, but some of the state of the art from program verification that's come out of kind of the last 30, 40 years of computer science, and then think about how or why that could be applied in climate modeling. So let's start off with testing. That's like the mainstay of verification, and we've had lots of talks that are about testing so far. The really nice thing about testing, I think, that makes it so popular and easy to deploy is that your specification language is the same as your implementation language. So you don't have to learn something new. You're writing Fortran code, you're writing C++, you write the tests also in Fortran or C++. So that's really attractive thing about it. The challenge then is that the verification is partial. You're necessarily testing a subset of the inputs. Code coverage is really helpful in kind of guiding you to cover the control flow paths, but necessarily you're kind of limiting yourself in terms of your imagination about thinking what could go wrong. Dijkstra has this kind of classic inflammatory Dijkstra style quote about, oh, it doesn't show the absence of bugs. Perhaps another way of saying that is that it might fail to expose the unconceived of bugs. So there might be things that we never thought of, that we didn't write a test for, that we don't find out. Or we might get lucky and write a test that finds something that we didn't think about. That does happen to me, certainly. But there's this kind of necessary partiality. Now, there's been some really cool stuff that's happened. This got mentioned yesterday, and I promised I would say something about it. Property-based testing. This is where we use our source language and we write down a Boolean function. So this is a Python function that says that tests whether the reverse of a string is the same as the original string. And a property-based testing framework can then take that and enumerate a bunch of inputs. It will systematically specialize and also randomly choose inputs to test this, say like 100 times. To see if it's actually true. And the really nice thing is that it finds counterexamples for you then. So it's a different way of thinking, where you're thinking less about what does this specific execution do, but it's more about the general characteristics or properties of your program. There are some really nice frameworks around this. Quick check is where this idea came from in the Haskell language. There's a Python library called Hypothesis. And there's a lot of cool work then into designing generators, and you can have generators automatically derived for all your types. So say you have some, I don't know, complicated object with some netcdf file and some other information and they can be automatically generated for you. So the generators come for free. You just have to write your properties. Now, another kind of verification, some people argue that this is the most successful kind of verification that's used, formal verification that's used, is type systems. The nice thing about them is that they're tightly coupled into our languages. They're sort of part of the language definition. They're very lightweight specifications. They don't. They just touch particular kinds of properties. And then if you have a statically typed language, they're checked for you by the compiler. So here's some Fortran-like code. You try and add an integer and a logical. The compiler says no. I don't know what to do with this, so I'm not going to allow it. This has no meaning for me. Now, dynamic languages, you get those. The types still exist. You just get the error later on when you're running it. But there's been a lot of really nice work in recent years with gradual type systems, optional type systems, where you can take something that's dynamically typed and add in type annotations and have them checked by another tool. So a good example of this is Python and MyPy, which works really well for statically typing Python code. And there are lots of really cool things that go on in PL research of kind of coming up with new type systems to capture more properties, more of program behavior. So dependent types, that's a way of relating types to values and capturing relationships there. It's extremely powerful. Refinement types is about capturing invariants about your data representations, and a bunch of others that I won't go through, but there's sort of lots of cool work there, expanding the expressivity of type systems. Okay, another technique, which we just heard about from John in his lovely talk, is deductive verification. This comes from the idea, something called Floyd-Hoare logic, where you specify pre and post conditions on your programs. Here's a little example of a Fortran rendering here saying it's a conversion function, and you're saying, okay, if the input in degrees is between 0 and 360, then the output is between 0 and 2 pi, kind of truncated. And then you have an automated tool that checks that for you. Typically, these use some off-the-shelf automated solvers like Z3, so they kind of generate theorems that get solved for you. And there's a really nice tool for doing this with C code. It's called Pharmacy, where you can specify these things in C code and have them checked for you. Now, a downside here, and we were just hearing a little bit about that, is the loop invariance. It's actually quite subtle to design loop invariance. Sometimes it's quite clear depending on the application. Other times it's a bit more subtle. There is various work about how to generate loop invariants for people because they're difficult to get right sometimes. And another challenge is that it actually requires you to have a semantics for your language so that you can have a sound analysis. And that's difficult because for a lot of programming languages, there's no formal definition of their semantics. There's a language spec, but it's written in English and it's not very precise. There are lots of cool languages that integrate these things kind of into their guts. So there's a verification-oriented language called Daphne, which has this kind of feature really built in from the beginning, and others as well. So static analysis tools, another technique. This is where, in a sense, you've agreed upon some bad behavior ahead of time. So the specification is something that we all agree is bad, like use after free and out of bounds array access, divide by 0, other kinds of exceptions. And there are lots of tools that work with lots of languages that will do these kind of checks over your code and tell you when things look potentially fishy. The downside is that they're kind of based on this idea of some things that we all agree is bad, but then they're not domain specific. There are some really nice tools that are related to floating point and doing things like assessing floating point error, or this thing I've mentioned here is the Herbie project. It can show you when you've got floating point expressions going to be imprecise and rewrite them for you into precise floating point that will better capture the kind of intended real semantics. Okay, proof assistance and interactive theorem provers. There's lots of very cool stuff in here. This is kind of more in my background discipline. These, again, it's like your implementation language is your specification language. They're systems in which you can write formal proofs, and you have a core that checks the validity of your proofs, sometimes with a certain amount of automation. And then you can use those to model a problem and then prove properties about it within the same language. However, your language, differently to testing, here you're forced to use that language. So here's some Agda code that I was writing the other day with some students on the right. This is the Agda programming language. I have to, if I want to prove things about with the system, well, it has to all be in Agda. I can't take Fortran and prove things about it using Agda. And then the problem with getting this out into people's hands is that you have to learn a whole new language. It's very unfamiliar. This is not something you can execute in a high performance way. It doesn't have all the same libraries. However, this kind of line of work, these automated theorem provers, have been hugely successful in various areas. So you have things like entire microkernels that have been verified against some specification, verified C compilers against some formalized subset of the C language and formalized assembly language semantics that's been fully verified in these theorem provers. John talked a lot about modeling languages and a bit about model checking. So that's great. I'm not going to say a lot about that. You have some sort of specification language where you can model your software like Alloy, and you have tools that maybe can take a program and extract it into a model for you. And then model checking software lets you exhaustively check the state space of that model to find out whether certain properties are true. Again, this has been extremely effective in various safety critical systems, used by NASA, used by Intel, used by Airbus for checking safety critical systems. So that's a kind of lightning tour through some of the state of the art. I kind of end this bit of the talk with looking at a case study where from researchers at INRIA, led by Sylvie Boldo. This is a fantastic paper. They took the one-dimensional acoustic wave equation and did the normal numerical analysis stuff, applied the textbook techniques to discretize it, and then went from there into the implementation in C code, 100 lines of C. But what they did is they verified that entire thing. So using a proof assistant, they verified all the numerical analysis steps to make sure that they were doing something that was mathematically sound, that was within certain error bounds and that had convergence. They did all of those proofs formally with a theorem prover checking it for them. They then used a deductive verification framework to make sure that the C implementation was doing exactly what that abstract discrete formation said. And that generated lots of proof conditions, which they then used automated theorem provers to deal with, or proofs written inside of the Coq theorem prover. And that's amazing, end-to-end verification of a numerical model from the PDE to the implementation. But that took 6 people, 6 experts in the field, some number of months. I can't remember how many. I think it was about 6 months. It took them that long to do that. And that's for a single PDE, 100 lines of C code. Okay, so could we do that with CESM, 2 million lines of Fortran code and all the stuff that goes into that? We're nowhere near being able to do that. But the question is, do we want to do that? So at the moment of what I've gone through very quickly, how much of that is used in climate science? Well, as far as I know, very little. We know that we use testing, and that's fantastic. Type systems get used in, say, Fortran, but a very modest kind of type system. But the rest of the stuff, the rest of all these goodies have not really yet been applied. I've made the modeling and model checking slightly darker gray after John's talk because there were some very nice examples in there. But in terms of sort of general practice, as far as I know, not much of these things are applied. If you know differently, do let me know. So the question is, should we be doing more formal verification or full formal verification of climate models? That's a question I was asking myself. Well, there's some really nice kind of arguments against why it would be difficult to do that, or maybe we shouldn't, in this short paper by Daniel Jackson and Jeanette Wing. They're talking about how the cost of full verification is prohibitive, and early detection of errors is a more realistic goal. Talking about full methods in general here. The cost of proof is usually an order of magnitude greater than the cost of specification, and yet the cost of specification alone is often beyond the project's budget. I think we could see that would be the case in a GCM context. If just trying to specify these things in fully would just be prohibitive, would just take too long, take too much time. And I really like this quote here from their short paper. There can be no point embarking on the construction of a specification until it is known exactly what the specification is for, which risks it's intended to mitigate, and in which respects it will inevitably prove inadequate. So I think the key thing is to think, what are the worst things we want to guard against? And Michael asked that kind of question last night in the discussion. What are the kind of things that keep you up at night? So in the GCM context, here's a few things risks we might want to mitigate against. I think violation of conservation laws or invariances is something we definitely would be concerned about checking. Instability, things kind of blowing up numerically after some point. We get 50 years into a run and then things start diverging due to unbounded error growth. That's something we'd wish to avoid. Race conditions due to parallel implementations, giving us data that just gets kind of trashed over time or becomes non-deterministic. And I think another big risk is just the speed of development. Having to kind of constantly chase bugs slows us down when we're trying to do new science. This is, of course, not an exhaustive list, and I kind of put this here to ask that question to everyone in the room, particularly those who are involved in climate modeling. Like, what are the risks that you want to mitigate that we could be thinking about verification tools for? I'm going to skip this in the interest of time. This is just showing the kind of full verification can involve having a very large specification. Instead, maybe we want smaller specifications, partial verification. So the last case study I want to mention is a tool that we developed called CAMFORT. It's for lightweight verification for science. This came out of work with climate scientists here in Cambridge, and we had a collaboration with the Met Office and with Bloomberg as well. And we built a tool that can do sort of lightweight static analysis that's aimed at numerical modeling. So we have a few different checks. We can have a sort of check whether you do equality or inequality of the floating point, which can be a possible source of instability. We have some performance checks about traversing arrays in the right order, and allocation checks to make sure you don't do things like use after free. So these are kind of static analysis. You run the tool over your code and it gives you a report. We also added a units of measure type system to Fortran, so you can write down specifications as comments in your code that specify the units of measure of variables, and then the system checks them for you and does dimensional analysis and checks whether you've actually done things that are dimensionally consistent. In this example, we didn't have to give a specification to every variable. You can also ask the tool to insert the ones that you didn't give, so you get that extra documentation. So this came out of a project of trying to think, what are some lightweight things we can do for scientists? Some lightweight specify and check kind of tools, and some lightweight static analyses. So going forwards, the next 10, 20, 30 years, testing is, of course, we're going to keep using that. It's a really useful tool. We can use validation, science tests, as well as a proxy for verification. And I think what I'd love to see is more deployment of the property-based testing idea, because I think it's very powerful. You can also get property-based tests to be generated out of your existing unit tests, kind of generalizing them. So maybe we need to put some effort into making a Fortran property-based testing framework. And also there's lots of nice work about automatically generating tests from traces or from learning-based models. Types, gradually we see that languages pick up ideas from sort of research languages. So it would be nice to see whether we could get dependent types into some more mainstream languages, e.g. into Python or Julia via these optional type systems. Deductive verification is difficult because you need that formal semantics. There's already this tool for C from C. Maybe I wonder, well, would it be useful? Should we be someone be putting effort into making something similar for Fortran? I think that would take a lot of engineering effort. And the question is, will we still be writing Fortran in 2050? I think Sir Tony Hoare would say, yes, probably we will be. So maybe that would be a useful place to put in effort. Interactive proof assistants, I'm less sure that we'd be able to use those unless we kind of use them in the context for writing a small model that then can be extracted or lowered into Fortran code. Okay, but I think static analysis tools is a place where we can do a lot more work. They're really easy to deploy. They fit within existing processes, and with a bit of training, you can get some big wins. What I think we need is some more targeted analysis for scientists, though. Things like conservation analysis tests, sensitivity tests, robustness, to mitigate against those risks that I identified. And then lastly, maybe we should be looking at EDSLs with correct by construction properties. So we talked about DSLs yesterday. You can build those such that they give you the guarantees for free. I think what's clear, though, is that we need more interaction between the verification community and climate scientists. And to that end, there's another workshop that's happening in London in January called Programming for the Planet, or PROPL. It's co-located with the Principles of Programming Language conference. So if you're interested in this, do take a look at being involved. It's going to be hybrid as well. So that's a chance to try and cross the chasm there. Okay, thank you very much.
Thanks, Dominic. Any questions? Any online questions? So I had a quick question about the CAM for the inner working of it. Is it based on generating an ASD, or does it just parse the Fortran?
Yeah, so CAM for the way it's architected, it's basically like a compiler front end. So it lexes and parses Fortran into an AST. It then does lots of classic static analysis that a compiler would do, data flow analysis. And then from there, we build other static analyses on top of it. So it's a bit like a compiler front end with then lots of other things we built on top. And it's an open source platform. Occasionally, people build other Fortran things on top of it.
Cool. So does it use an external library for generating ASD, or does it do it itself?
No, we wrote our own. We try to be we try to write standards compliant parsers, for better or worse.
Cool.
We can have a whole big conversation about that.
Sure. All right. Let's thank Dominic again.
Thank you.
So our next speaker is Francisco Carrera from Euro-Mediterranean Center on Climate Change Foundation. Francisco, the floor is yours.
Oh yeah, thank you. Yeah, welcome to our talk on parallel reproducibility of the SciFM MPI model, on which Giorgio, Italo, Francesca, and I have been working for the last few months. So we're all working at the Euro-Mediterranean Center on Climate Change in Lecce, Italy, and Italo's also a professor at the University of Salento. And yeah, I want to start with some introductory slides about the problems we encountered and the questions. And yeah, first let's start where are we working at. So we're working at SwimCC, which is a non-profit mainly funded by universities and the government. And the goal is to use interdisciplinary science to connect weather and climate research to society, and based on that, provide advice for policy. And for the sake of this presentation, I'll divide the employees into two groups, the scientists and the engineers. And we're part of the engineers. We're in the Advanced Scientific Computing division, one of the 11 divisions you can see on the left. And ASC have developed SciFM MPI, and the problem is that it's non-bitwise reproducible. So we can see in the bottom right the Strait of Corinth around Greece, and in green and red we can see the difference in sea surface temperature in two different but in two identical parallel runs. So it's non-bitwise reproducible. So what's the goal of this presentation? So for this, I will divide development of code into 3 consecutive stages. 1 second. Oh yeah. The first one is defining your equations, then afterwards building correct, validated and verified code, and then optimizing your code. And our goal is to propose or maybe even convince you that bitwise reproducible is useful, very useful for the second stage, but maybe we don't need it after optimization for the sake of performance. So losing bitwise reproducibility is very easy, because the workflow from source code to execution is very long, and in every component you could lose bitwise reproducibility. And in our case, we have a parallelized model, and this introduces non-determinism only during execution, so only during runtime. So here, and we don't change the computing context. And we will study this non-bitwise reproducibility, or we'll study reproducibility because using rounding error. So we'll study rounding error because they're very highly linked, bitwise reproducibility and rounding error. So what did we have? We had a sequential model, and we used identical input and context to run it through a model, and as output only got a number, let's say a number plus or minus machine precision. And afterwards, we parallelized it. So we got a non-deterministic model, and we viewed the output as sampling from a probability distribution. And as a representation, I showed two distributions. So one, let's say, well-conditioned, a nice bell curve, and the other one ill-conditioned, so maybe from a chaotic system. This is just a representative plot, nothing real. Now, I want to touch upon error really quickly, because even though reproducibility is very linked to rounding error, yeah, your sequential code, your parallel code can still be correct in some sense, even though it doesn't provide one number as output. So what I want to say really is that in the parallel model, part of the rounding error emerges, and in the sequential model, rounding error is in some sense hidden. All right, but anyway, so we lost reproducibilities, and the scientists and engineers were unhappy. So what could we do? What were the solutions? The first one was to go back. So look at all the changes which were non-bitwise reproducible and redo them. So turn back. The second one would be to move forward. So use other algorithms which make the code again reproducible. For example, Reproducibility makes summation associative again. And the third one maybe would be to let go of reproducibility, and then we could influence it by, for example, tuning precision or other methods described in this paper. So we'll look at the third one. And for this, we'll first define or state some advantage of bitwise reproducibility and see if we can convince you that it's not necessary for the second part after optimization. Maybe it's naive, we'll see. And then the second and the third part will define, or will take an approach of parallel reproducibility, try to define it. It's an approach, let's say, and then apply it to SciFM MPI, so the hydrodynamic model that we had. All right, so bitwise reproducibility, when should we use it? So let's mention some advantages and disadvantages that are generally mentioned. On the left, we have the engineers, and the bitwise reproducibility is very useful for debugging, verification and validation, and regression testing. And this is quite straightforward, I would say, and yeah, we agree with this. On the scientific part, there are three advantages that I've regularly seen, so let's go through them. The first one is reviewing papers. So generally, it's said that to build science, it would be useful to for the result if a peer reviewer asks you for your code, that you get exactly the same result. So this, I would say, it's useful for building science. And the second one is for policy and applications. Of course, you don't want guilty the first time and not guilty the second time. And the third one would be ill-conditioned systems. So what if you have some very rare behavior that you're looking for, and then you found it, and the next run you run it again and you lost it because it's non-reproducible. So do we, oh yeah, and there's also some disadvantages. Coding is restrictive, and the code is more slow and efficient. It's restrictive because it's very easy to lose reproducibility, of course. So do we agree with this? On the left, we find this very useful, just like we said at the start. On the right, maybe we think optimized code, which is non-reproducibility, could be used, maybe even should be used. And then the question is, can we give some counter arguments to the right column? Yeah, we can. And so as I said before, for the sequential code, the round of error is hidden, and in the parallel, it emerges. And now I want to say about the first two, so reviewing papers and policy and applications, that the most important thing is that we use correct and validated and verified code. So if we, the question is then, do we lose validity? Do we lose correctness? Do we lose verification when the rounding error is not fixed? So can't we use a parallel model, even if it's correct, to build science, or use it for policy and applications? And of course, the non-reproducibility introduces uncertainty, but maybe we should deal it with another way. And then a counter argument for the ill-conditioned system. I think it's a bit less strong, but maybe if we have very rare behavior, we could decrease instead of non-determinism, instead of wanting full bitwise reproducibility. So yeah, this would be maybe a possibility. So in general, what I want to say is, if your optimized code is really correct, verified, and validated, we maybe should use it for science, even though it would be non-bitwise reproducible. All right, so just to reiterate again, for our goal, we think bitwise reproducible is useful for developing in the engineer part, but for the right side, then the questions arise: can we add a type of reproducibility? So can we define, measure, influence reproducibility in a larger sense than bitwise one? And in what sense do we trust the parallelized code? And we'll try a statistical definition. So let's try a statistical definition. So here is the context, this framework. Where are we putting our definition? What has already been done? So let's start on the top. We have weather and climate in reality, and we model it using, for example, a PDE or an SPD, so deterministic or stochastic. Let's go with the PDE on the left. Then you could do an implementation which is deterministic. Then it's, of course, it's bitwise reproducible, or non-deterministic. And on the right, also for the stochastic case, Hill defined deterministic, which I think, don't ask me too much, but I think it was just defining, fixing your random seed, and then it should be deterministic again. And by the way, the statistical reproducibility, Mahajim will talk about this after lunch. And the thing is, we're looking for this one, and we're also we're looking for a definition here, and we're also looking for a statistical definition. So maybe we can steal from the guys after lunch. So let's see, can we steal from the guys after lunch? What they're doing, so maybe they'll explain it better after lunch. But what we're doing is, they have two versions of the code, both deterministic, but one differs from the other by one non-bitwise reproducible difference. What they do then is they vary initial values to get a sampling. So they sample their code, and then they use a probability metric, a two-sample statistical test, so hypothesis test, to see how equal they are. So can we also do this? We can't, because we only have one version of the code, which is non-deterministic. Then we run multiple. What can we do? We can run multiple times to sample it, and then do a one-sample test. So it's not very clear how to define reproducibility stealing from here, but maybe we can try to find another sampling so that we get 2 samples. And for this, I will extend the framework a bit more. So between deterministic and non-deterministic, we'll also define, we'll look at parallelized code. And it can still be bitwise reproducible, but we are looking, of course, for a new definition. And we can actually find a second sampling from the sequential code. So that's where we get our second sampling. So we can use the definition for statistical reproducibility. And this has actually also been done in the stochastic case. A type of parallel reproducibility has been defined by comparing it with the sequential code. So this is the framework. Let's look at an example. So of course, the plus is non-associative, which means that parallelized evaluation of the sum is not bitwise reproducible. And here we can actually show how non-reproducible it is. So we see a different number of processors, and then we just plotted the distribution of the error. And what we see, for example, is that the bigger the amount of processes, the bigger the variance, and that's also what you would expect. But can we now define reproducibility for the parallel summation? How reproducible is the parallel summation? So yeah, so what do we have? We have the exact sum denoted by capital S, and we will define the approximate sum by small s. And this, of course, has a relative rounding error of the size of the machine precision. So capital S is the exact one, small s is the approximate one. And for bitwise reproducibility, we also, as said at the start, we'll look at rounding error. This can be estimated analytically, so this has been done, but we're more interested in a stochastic, in a probabilistic estimate, and that's below. So we'll just skip this one as possible, but yeah. So the expected error is for fixed point arithmetic. So let's just assume for a second we have fixed point arithmetic. It's distributed normally, and the variance grows with the square root of the number of summands. Here's n, and this is if the relative error is independently distributed, where sigma is of the size proportional to machine precision. So we do now have a second. So we do now have a second probability distribution. So we can steal from the guys after lunch now. So what would be then the method maybe to define parallel reproducibility? It would be choosing a probability metric D, a tolerance, and then just like they did, use a sample test. And now we'll use a one sample test between our sampled parallelized code and the probability distribution that we found in the last slide. And then we would accept, so we would call it parallel reproducible if it passes the hypothesis test. On the other hand, we also tried a confidence interval based method. So again, we would choose a tolerance. We would find the alpha confidence interval of the mean of the estimate of the error, the probabilistic estimate, and we would check if the parallelized sampling would lie in this alpha confidence interval. And if it would lie in this confidence interval, we would call it parallel reproducible. So let's try it for the summation. First, we'll try the second method, and I'll just quickly say that just for a high tolerance, we can see that the expected probability distribution is very wide, and the parallel sampling is very low variance. So even for high tolerances, we would expect the parallel summation to be reproducible, and even more on the right side, because apparently the parallel sampling doesn't grow as fast as square root of n. So we would define possibly for high tolerances parallel summation already as parallel reproducible. And for the first method, we tried the Kolmogorov-Smirnov test, and it actually had a negative hypothesis test outcome for even very low tolerances. This means it would not be drawn from the same distribution, of course. And then you could ask yourself, do we really want the parallel summation to not be reproducible? So this is a question. There's a problem with this approach of defining parallel reproducibility, and the thing is the distribution of the rounding error is, of course, hard to find in general. So what's the solution? We would sample the rounding error, and how do we do this? We just use non-associativity. So we would reorder the index set of the sequential code, of the bitwise reproducible code. So what would then be a third try for parallel reproducibility? Again, on the left side, instead of a one sample test, we have the same thing as before. We would try a two sample test. Oh, sorry, this should be alpha. Or we would try a confidence interval based method again. And then we would assume that the sequential sampling would be normally distributed, the mean of the sequential sampling. So we'd assume something like a central limit theorem. And just like the way before, we would define them to be parallel reproducible or not based on the same test as before. So let's see, can we define parallel reproducibility for sums again using this method? So we see again the parallel sampling in pink here and in dark green here, and the sequential sampling by reordering the sum. And we see that it's much wider than the parallel distribution, especially for 16 processes, but also a bit more for more processes. So in the first method, we would again maybe define it as parallel reproducible. And for the Kolmogorov-Smirnov test, again, it's negative. So yeah, we would not define it as parallel reproducible. So maybe it's a problem. Anyway, let's apply this quickly to SciFM MPI. I see that I'm a bit late, so I'll hurry a bit. Yeah, so due to the grid, we have communication over the boundaries, and different amount of processes can give us reordering of summands effectively. So it's non-bitwise reproducible. And we would sample now by reordering the grid. So we would sample the rounding error by reordering the grid. And actually for SciFM, it's known for SciFM MPI why two runs aren't identical, and also a bitwise reproducible version exists of SciFM MPI. But let's quickly state them. So the second one is due to internal library and external library, sorry. And the first one is due to communications across the border, as I showed earlier, and more importantly, reductions. So just quickly, we also know the difference between the sequential and the parallel execution. I'll just go a bit quicker. So by reordering the grid, what we're effectively doing is sampling these two errors. So we would test part of the difference in rounding error and see then if we can define SciFM MPI to be reproducible. So how we'll do this? We'll look at the case study, same grid as before, the Greek islands. Number of processes fixed, and we're interested in parallel reproducibility, of course, and we will use ensemble runs, so just multiple executions for the parallel and a reordering for the sequential. And for weather, we will use 1 year, which is a long run for weather. Yeah, and on the left we see a difference. One problem is we're now not anymore in the univariate case like the sum, but we're in a multivariate case. So we also have a distributions over space and time. So we have more degrees of freedom. So how do we deal with more degrees of freedom? Two possibilities. We just take our previous two methods and we adapt them to the multivariate version. So we use a multivariate test or use a confidence radius instead of a confidence interval. But what we'll do here really quickly is use use it pointwise and then reduce it very quickly. So the results, what we see for SciFM MPI, so this is a bit of a difficult plot. So what we have two types of things. Here we have the red and green bandwidth. So what do they represent? They're the sequential and parallel ensemble, and they're the 2 sigma confidence interval of the means of these ensembles. So either sequential or parallel, and we took the maximum over the grid. And then this green line shows the average distance over the grid between the mean of the sequential and the parallel ensemble. So what does it actually mean? On the right, we see it. The bandwidth is again a 2 sigma confidence interval of different sequential runs. So just by reordering, and we see actually that the difference between the sequential and the parallel runs is less than the difference between 2 sequential runs. So in other words, the rounding error that's hidden in the sequential code would be larger than the error due to non-reproducibility. So in this sense, we would define SciFM MPI reproducible. Okay, so I'll just skip the Kolmogorov-Smirnov test. So what are our thoughts in the end? So we had 2 questions. We define measure influence a reproducibility in a larger sense than the bitwise one. We tried a two-sample one, which doesn't seem really right. And we tried a confidence interval. This seems better. We had some parallel code P and a sequential code S, and then we saw some sense for Scheifele MPI that that P would be smaller equal than S. Let's state it like this: it would be parallel reproducibility. And in what sense can we then trust the parallelized code? Well, I would say if X is smaller than Y and Y is correct, then we would also define X as correct. Of course, this is due to, sorry, I will just go back. This is due to this plot that the hidden rounding error for the sequential is bigger than the difference between the sequential and the parallel. So in this sense, we would really define it as reproducible. And so we try to give a definition. This works good for well-conditioned systems, the sum and Scheifele MPI without turbulence, but we don't know yet about chaotic ill-conditioned systems. All right. So just to end, so this was what we're trying to convince you. I'll just go really quickly. Try to convince you that we could lose bitwise reproducibility of the code when optimizing, and this is the answer to the first question. So we tried to define reproducibility via confidence interval, and we tried to define a correctness if the confidence interval test is right. And for Scheifele MPI, we found that in some sense it was parallel reproducible. All of the above with no chaos, well conditioned. And one final thought: this type of parallel reproducibility can be defined not only by parallelization, but any time in which you're doing your optimization and it becomes non-reproducible. All right, so that's it. Okay, sorry, I didn't see the.
Thanks, Francesco. Is there any quick question?
I think I missed the carrot. Is the advantage of allowing non-reproducibility that you get a faster MPI and you have an application that the reductions are enough of the time that this is a worthwhile benefit?
Yes, it's so your question is it worthwhile because it's faster?
Yes.
Yes.
Yeah, it's faster because there's more room for compiler optimization and also with the reduction, with the parallel reductions, you can use topology-aware reductions, for example, which are then faster instead of deterministic reductions in MPI. So this would be the advantage.
Right, thanks, Francesco. So we're gonna have a break. So let's try to get back on 10:30. We are a bit behind, but let's see you at 10:40.
Okay, sorry about the extra time. Thank you.
Okay, we're going to get started here. I suppose I know Dorrit well enough that I could just probably give her biography, but I did. It's probably better if I skipped the official script. Maybe not. Should I ask? All right, so Professor Hammerling obtained an MA and PhD from the University of Michigan in statistics and engineering, followed by a postdoctoral fellowship at the Statistical Applied Mathematical Institute in the program for statistical inference for Massachusetts. Yeah, I'm not tired, no problem. Okay, she then joined the National Center for Atmospheric Research, where she led the statistics group within the Institute for Mathematics Applied to the Geosciences. That's where I met Dorrit. And she worked in the machine learning division before becoming now an associate professor in applied math and statistics at the Colorado School of Mines in January 2019. So thank you, Dorrit.
Thank you so much, Alison. Can you all hear me? Yeah, so just for full disclosure, the Corral School of Mine is just down the road. So I'm still here about once a week and torture Alison and other people respectively. So the work I'm going to talk about is what we kind of jointly all work together with a lot of students. And one of them is here, I think, Dan, are you here in the room? Yeah, who did a lot of the work and by now and is less traumatized and willing to come back to talk about it. Theo is also here, but we had a lot of other students work on this. So, and I want to thank Alison and Alba for organizing this because it has been really interesting to get all these different perspectives. And here you'll get yet another perspective that's really very statistically driven and also based on the fact we really had to do something and make it work. So without that, I'll quickly say, I mean, obviously you're all here, you know where we are, NCAR, the National Center for Atmospheric Research, and Brian Dobson is here who can talk a lot about the supercomputer. One of the reasons I mentioned that is what's unique about this center here is that the supercomputer is right associated with the climate model. So we can do things like say, hey, can we get 800 runs just for testing purposes, which maybe in other settings wouldn't be that easy. Hopefully Thomas doesn't hear that, but yeah, that's the kind of stuff we could do. So that's important to be aware of. I don't need to go through all these details here. And we have been talking a lot about CSM. So that's the model, the community Earth system model. The community aspect of this is really relevant, I think, compared to some other models that seem a little bit more tightly controlled in how they are programmed and set up. There's tons of users, literally 10,000 of users, a lot of institutions that have that model downloaded. So that gives some kind of perspective here. And that next slide is also pretty telling. I think the point is actually here. Yeah, what you can see here in the timeline is getting bigger and bigger. And this is something that Alison said, 30 years of code, modern and not so much. Yeah, that might be a slight understatement. That code is pretty messy. Yeah, so you shouldn't, other people's dirty laundry, but in some ways I still feel part of it. Like it's obviously a challenge. And there's obviously reasons why some of this code is in there's amazing science there, but just the reality of it. And I guess by now it's 2.5 million lines of code. So just it's a bit away from unit testing. Let's put it like that. I'm actually a huge fan of unit testing. I remember when I had interns here in the summer, and there was an initiative at NCAR to start unit testing, and I made all my interns go through the workshop and everything that this summer they had to write unit tests for. And again, I think this is really useful. It's just that's not where maybe the model is quite now. And apart from all that, so what motivated this work was something really practical. So when CSM is being, let's say, implemented in another institution, you have to some way make sure they're actually doing that right. That sounds trivial, but in reality, there's a lot of different modules and there's a lot of other files you have to pull in. There's all kinds of stuff that can go wrong. And then very practical things. If you want to test a new compiler, does that actually work? Other code modifications, things porting part of it onto GPUs, optimization, and more generally heterogeneous computing environments. So that's what we are really talking about here. Kind of things external to the code that I think anyone who works on HPC systems can appreciate that in these kind of cases, we are losing bit for bit. So to clarify the setting here, CSM is actually deterministic in the sense of if you fix the random seed and you run it on exactly the same computer infrastructure, you do get bit for bit results. So that's the setting here. But as soon as you change any of these things here, that's not the case anymore. So Francesca was just talking very specifically about parallelization. So this is the way I view this is one of many things that can, if you change them, and that's practically what you would changes the outcome. So this is typically not the case. So going for bit in this whole model environment is just practically too restrictive. So we wanted to come up with something that, given the reality of what we want to achieve, that still works and gives us some reasonable testing. And it's very much in the spirit of what Francesco was doing, except taking 7 steps back and looking at it more externally and trying to tackle all these things. So setting up the framework here. So we have an original accepted CSM run. Everything same setting. Now we port this to a new institution, we get slightly different results. And the question we want to answer now, is that output still correct? And to frame that in climate scientist language, what they are really care about is that still the same climate? And there's this really term that gave me a kind of a lot of headache. Is it climate changing? So if you come from a stats math side, you're like, yeah, well, what does that mean? Climate changing, we can tackle things like if we have big output fields and people tell us, well, it can't change more than 0.5% in these 96 variables of these 300 we are putting out, then we can deal with this. But climate scientists don't think about that way, right? They don't take, like Brian said yesterday, well, if Boulder is all of a sudden 500 degrees, that's wrong. Yeah, well, that's true. Yeah, but specifying that exactly, that people tell you, well, in these, and there are hundreds of output fields. Yeah? So they have a sense for that. So the way this was done before, obviously climate scientists are brilliant scientists. The way this was done before is you make a change, then you run that thing out for 100 years, and some smart scientist stares and looks and analyzes these fields for well, I can tell weeks, yeah, and looks at that and finds this out. Is there anything wrong here? And is something wrong here? And there's all kinds of stuff you can look at. That's obviously very time consuming. If every time somebody says, well, maybe we can optimize this one thing here, let's do this procedure, not gonna happen. So there was a real need for an automated tool that probably many of you can relate to, that can say, if you make some client's little change and we bring it to a different institution, can you give us an easy to use objective tests? And that's what I'm going to talk about. So just so this is our kind of our journey towards this easy to use objective automated tool here. So just to get back to what is the question, can we assess now if this difference is climate changing? And statisticians are known for that. Let's reframe the problem. If a question is really hard, let's just ask a different question here. And that's the question we ask here. Yeah? Instead of saying, is it climate changing, we just say, well, is this new data statistically distinguishable from some kind of accepted data? And that's the stuff I'm going to talk more in more detail. So that's important to understand though. So I'm not using any high-flying words like validation or verification, because I think we all understand those are tricky terms and we've heard a lot about that. So we're doing something much simpler here. We are saying we are going for ensemble consistency test. So we are saying, we have a new output here. Does that kind of look like, in this very high dimensional output space, does it look like many runs from what we accept as we think about that's correct? All these terms are, of course, super loaded. So we just say accepted data in the sense of data that we run on the infrastructure we are familiar with, and we more or less think that made some sense. So that's the setting here. I think, as we have heard already many times here, a very natural way to do this with chaotic systems, so just the way I think about chaotic systems, is if we have slight changes in the initial conditions, we can have quite different outcome. So this is, I think, in many ways how people can think about the climate. I think that it's worth considering that the type of software we are talking about with climate models really is extremely complex. That's very different than saying a software that where we want to get the flight paths right. Not to say that's not complex, and I can obviously appreciate how this is also really important. But the reality is that in climate systems, we represent a lot of things in ways that we know are simplifications. And Steve brought that out very quickly. So I think it's worth to think about that in that context. And if we think about all these models here. So setup here, again, we want to look at this in this context of this ensemble here. And the one thing I want to point out here is that the high dimensionality in variable space of the output really matters. When we worked on this, there were something more than 200 variables output, but now I think it's more like 300 something variables. And in MPAS that Theo is going to talk about an alternative model, there's even more than that. So that's important to keep in mind. So that, because if you have a single thing or a few things, you put out maybe quite different models, or kind of statistical approaches would be more appropriate. So that will be a bit of a theme in my talk here. All right, so quick, another conceptual idea when we thought about developing this tool here is, so you can kind of see the workflow here. So creating that baseline ensemble and doing that in a meaningful way, and then establishing statistically what quantify what the variability is. And on the other hand, then we have the user community who can use the tool to quickly check, let's say, their implementation in a different facility to make sure that actually works correctly and get a quick pass-fail thing on this. So this is kind of what we want here. And it's worth noting that here, we have a lot of smart people who can put a lot of work in that. So this part here, it's okay to be involved. So this can have quite a bit of work. But the way we set the tool up is, on this end here, we don't want the user to have to run big ensembles or anything like that. We want something that on the user end is very simple. That's a little bit different approach than what we heard yesterday from Abhishek Gopal when they were talking about that method that we are quite familiar with, where they basically say, let's compare two big ensemble distributions. So that's purposefully something we didn't want to do to keep it kind of light on the user end here. All right. So digging right in, how we came up with creating that baseline CSM run. So here, again, when I say accepted machine software stack, that is basically HPC infrastructure at Anchor here. The initial work we did with this 1 degree atmosphere land model and used this typical way how initial condition perturbations are done here by perturbing the temperature field varies at 10 to the minus 14. So for any practical purposes, obviously, that's just to introduce chaos here. There is a little side note here that I want to point out, and that's going to be my sabbatical project a year from now or something. There are actually many options how you can create the ensemble, and they can actually matter. So as a side note, I'm just going to throw this in there. I tortured Alison and Dan at the time to actually also see, well, what happens if we use different compilers? So we use these initial conditions, but we have basically a two-factor design, but also use different compilers, because that's maybe as a proxy more realistic to what actually happens if we translate or port the model to different computer environments. And the type of variability we see in the output fields for some variables is really different. So I'm not going to talk about that, but it does certainly makes me think about this. How good this approximation really is. So what the practical way we dealt with that in our setup, we just said, well, let's use a third of this runs to establish the ensemble from all of the compilers, but there's a lot more interesting research here. So that's a total side note back to what we want to do. When we first started out, we did 1 year simulations here. We'll see later how we can cut that radically and actually don't need that, surprisingly enough. And as I had said before, 200 variables. So when I started, my background is spatial statistics for large data. So I was all excited about non-stationary fields and, like all of these things here, fields. Turns out totally not needed. All you need is the mean of each field. That is still the most surprising thing to me, that in that mean of this field, we actually capture what's going on. Totally surprising. Like I did not believe that for like 2 years and was still hoping there's something spatial there to be had, but nope, the mean does it all. There we go. So now we are back to 200 plus globally averaged variables. So another theme here is many of these output variables are highly correlated. So any kind of testing framework, we might hear more about that in the afternoon, but any kind of testing framework in a correlated setting, you need to adjust for that. So this is pretty tricky. So if you want to make pass-fail decisions on that, you would really have to characterize the correlation between these variables, and that's actually not trivial. So doing that one by one introduces all kinds of tricky things in terms of setting up a hypothesis testing framework to come up with pass-fail decisions. So one natural way to go about that in statistics land is to use something called principal component analysis that many of you are probably very familiar with. What we do with that is basically orthogonalize and form linear combinations and orthogonalize the underlying variable space here. And that's really at the core of this kind of setup here. So there are some steps you have to do is like standardize all the variables, as we've heard here many times. They're all on crazy different scales. That's a clearly important thing here. And then you project the data into that orthogonal space here. I'll talk about that a little more afterwards because it gives us all kinds of nice properties that we can actually work, also derive theoretical properties of this test here. So what we are testing in this framework now is not the original variable space, but rather the linear combinations, which is equivalent to these principal component stores of the original variables. Another thing you want, the question is now, how many of these do you want to do? And the way we classically think about that in principal component space is that you want to say, well, we want to look at enough of those things that we capture the overall variability in the system. And Theo is going to speak about this more, how you can think about this more general here. In our setting here for CSM, 50 of these did a really nice job capturing something like 95+% of the variance, which in terms of catching if something goes wrong, it definitely gets at it. But that can be very dependent on what the actually system looks like. And this really kind of goes off the how many degrees of freedom are there truly in your output? I mean, in the CSM case, there were not that many because a lot of these variables, like I said, are really highly correlated. All right. So one of the kind of nice side effects of using this kind of PCA based testing framework is that we can also pick up the correctness of relationships between variables. And I'm gonna discuss that on a pretty high level here, but if you think about these climate models, the output variables can take on many different states. This is really a very high dimensional joint distribution. So let's say we have cloud cover and sunshine. So both the sun, can shine really strongly, and with the cloud cover can be none or a lot. But you wouldn't expect them to be existing at the same time. So if you have lots of sun and also lots of sunshine, but lots of cloud cover, that kind of doesn't work together. Obviously, I'm doing something very simple or much trickier than that. And what this allows you, if you just tested one by one, that wouldn't really work because, of course, it's okay that the sun shines, and of course, it's okay that it's super cloudy, but you wouldn't catch their relationship. And this tool actually indirectly picks this up very nicely. So to formalize this a little bit, so the null hypothesis here is that the new climate simulations come from the same distribution as the ensemble simulations. So that's kind of the thing we want to test here. And as any kind of test here, there's two things you kind of care about. One is the false positive rate, like how much do we reject the null hypothesis, even though it's true? And the power, when do we actually correctly reject it if something is going on? We will very much, and in generally, you also want that false positive rate as low as possible and the power as high as possible. I will always only almost exclusively focus on the false positive rate for a very practical reason. Whenever we ask people to give us any example of something they would actually want to catch, it failed spectacularly. So in some sense, of course, we did do certain things like power, like can we detect a tiny little change here or something like that. But it's not, you can contrive things like that. But the way we went about it is really asking people, give us realistic things we want to catch, and we always caught them. So we didn't really worry too much about power. Obviously, there's some room there to think about it a little bit harder. All right, so I'm going to quickly walk you through how this procedure works now. So one thing, you can, all of these, in any kind of hypothesis testing framework, there's all kinds of parameters you can set, and you can tune them depending on how much, kind of like how you want to control these different, we call this type 1 or type 2 errors, but you can think about it, how much you want to control that false positive rate or the power here. The setup we went for is that we said from the new institution, let's say that we want to test the runs, we only want 3 runs from them. That's good enough to give us kind of the properties we want here. So we get these new runs, we project them into that orthogonal space, and we get now what's called these principal component scores from 50 in the case of CSM here. And then we look and compare them to the distribution that we get of the scores from our established ensembles. And we express this distribution just through the variability here. Maybe the details don't matter, but the way we set this up is now we check for each of these scores, how many times does it fall within the distribution and how many times does it not fall within this distribution. And then we set it up in a way that we say, well, if it fails more than 2 times here, like this row here would be a failure, we declare that score to be a failure. So this is in some ways a contrived setup. I'll show you afterwards that you can, what's nice about it, you can actually derive this fully theoretically under certain assumptions. So that's nice, but that's what the setup looks like. Again, all these individual things very tunable here. And here overall, then you say, well, I'm counting up how many of those failures I get. And then depending on what they are, and again, these numbers are fully tunable to what you want. You can define, did I pass or fail this? So that's what sits under the hood here. I'll discuss this in a little more detail afterwards, after you get some break from math here. So to state this, so this is, all this work is published now probably like 4 years ago or something, and is fully implemented. So everything I'm talking about is what's actually running right now. So we had done lots of testing here. Dan probably still has trauma from this. All we got, I think we literally went to a climate scientist torch and give us something that you think would fail. And we tested a lot of these. I don't know, Alison, do you remember, like 30, 50, 100 cases? And then did also a lot of work of modifications that we would hope that they wouldn't be climate changing, and things like changing the number of threads, different optimization compiler versions, all kinds of stuff like that. So kind of the stuff that Marshall is trying really hard to prevent, which makes a lot of sense in his setting. We were like, let's do that, because I'm sure that's happening in our code, like changing the order and these type of things. And that was all passing. So that's exactly the setup we want to pass here. Yep. And so this is in use right now. I think it's hopefully useful and uncovering errors in code and hardware. And I think in practice, it's really working well, which is probably one of the reasons it is used. So just a quick overview here, so that just to give the highlights again. So it's an automated Python tool, objective, user-friendly, rapid feedback, and all the kind of things we wanted. And one key factor here is you need no climate model expertise at all to run this thing. So if you ask your software people, please they put it, create 3 runs here, plug it in this tool, get a pass or fail. Nobody who is smart about climate change needs to know anything about this. So that's kind of what the tool is right now. Yep. One question that we were wondering, even with patient people who give us a lot of computer allocation, running year-long runs, if you're talking about hundreds, if not thousands of ensemble runs, not so popular. So we were wondering, do we really need year-long runs? What about if we could make it shorter? And shorter is obviously cheaper. But we were in the beginning kind of questioning, could we even pick things up in year-long runs, given how complicated the climate is, and thought, well, shorter is probably not so good, but who knows, might work. So we decided to do that. And again, that's a lot of the work that Dan did here. And what you see here is all the CSM variables we looked at. Obviously, nobody would expect you to read it, but just to give you an idea of how many there are. So all the CSM variables are listed here and here. And you see here the time steps from left to right, zeros time step, even there things can be different, and all the way going through the first 10 time steps. And you see the number of significant digits that they have in common. So here, the light, white, yellow thingy is a lot in common, and less and less and less. And you can see things start to change pretty quickly. So a time step corresponds roughly to half an hour in real time, in model, real time is in model time. Yeah, but you can see there's a lot of variability. Another way of viewing that is here we look at 3 specific variables of these hundreds of variables, how they behave here. And you can see, I'm going to just focus on that 9th time steps, because that's what we actually ran, came up running with. So you can see what the distribution looks like here moving forward. And clearly things are very much still happening. But it turns out, again, very surprisingly, all the info is there. So we can actually run this tool with 9 time steps. And that's what we call the ultra fast test. So instead of having to run this thing a year out, just run it for 9 time steps, which is obviously a lot cheaper to do computationally, use that instantaneous value, and it works surprisingly well. As you can imagine, people were really critical of that, and poor Alison and Dan had to do more and more and more, and really, I would say, tested the heck out of what can possibly happen. It was really difficult to find counterexamples, but I'm going to show you 2 after all this testing. So there are some counterexamples. One counterexample is changing that hydro base flow thing, which is one specific soil hydrology parameter. And that thing, for that to really basically controls the amount of water drained from the soil. And for that to really manifest itself in anything, sorry, I did actually not mention that. This test is all about looking at CAM only, which is the atmosphere component of SAM, of the community or system model. And that thing doesn't manifest itself at all in the 9th time step. So that is an example where you do catch it in the 1-year run, but you don't catch it in the 9th time. So having said that, I think what's written here, only very contrived manufacturing sample, is very true. I think we literally worked months to find a counterexample. And I'm going to show you one other counterexample that's going the other way. That's changing the random number generator. So that's something you pick up. That's relevant for cloud, for some of the cloud physics, among other things. That's something you pick up in the 9th time step. And so you can really show that you can repeat this many times. If you use a different random number generator in the 9th time steps, these distributions are slightly different, and we pick that up. That stuff averages out by the time you get to 1-year runs. So it's important to be aware of these kind of things. Again, this is 2 counterexamples we found out of many things. But there are these kind of differences that kind of, I think people who understand numerical analysis will make kind of sense why this potentially could happen here. So the way we kind of, I think, Enka goes about this now is that by default, the ultra-fast version is used. If there's some kind of unexpected failure, then you can always go back to the longer version, see is that actually consistent, or is it just something that comes here. So I would say, general, it's fair to say in these kind of settings where bit for bit reproducibility is not possible, that's probably a good way to go. So, and now I'm gonna poke holes into some of the things I was talking about. One thing is, a highly accurate test leads to new challenges. So, I think we have had that theme before. I think Tom mentioned that yesterday. If you tell people, we are pretty sure your stuff is wrong, but we really have no idea why it could be wrong. That can be not so popular. This is a very real example. So this was porting CSM to a new HPC system, one of the DOE machines that, by all knowledge are really good machines. Didn't pass. I think 10 probably still has a trauma from that too. So not only 10, but 10 people were really trying to find out, because they were supposed to be one of these big initiatives to run the model many times there. And then turned out it was that fused multiply add compiler setting. And this is for me, this was a very interesting example, because this is a case, I think from a pure math point of view, you could argue this is probably the better way to do it. Point being is, this is something as far as I can tell, there's no truth. It's not like using FMA is inherently stupid. If then that would be obvious. This is not a bug. This is just a different way of running it. It brings to light maybe how sensitive the code is to this kind of settings. And it was another reminder for me, maybe we need to define this ensemble in a broader sense. Having said that, that's exactly what they turned it off, so then it passed. So that's what happened then. But it was a good motivation to actually come up with a tool to give more info on like what's actually wrong here. And I should have then come out here and talk about this, but the idea was let's really dig deep if we have these kind of cases. And then instead of looking only at the difference at the 9th time step, let's even go further and look at the difference at the 1st time step, and then find out which of these variables are actually affected compared to the ensemble distribution. And then did this super ambitious thing to convert the source code, and even if it's only part of it, you'll see in the next slide what that looks like, to a directed graph. So here we're talking about take this, now I guess 2.5 million lines of code, and try to prune the source code and turn it into, build an abstract syntax tree out of it. And that, of course, is a formidable kind of quest. And then get a directed graph out of that. And I'll spare you the details, but just to say, this is a tiny portion of the CSM modules. So this is, to me, seems pretty intangible, but Dan is extremely brave and kind of conquer this on. And then worked on these kind of things that you can actually induce subgraphs and do all kinds of smart things to try to isolate where could this actually come from. So this example that you see here is actually using the different random number simulator here. And I'm not going to go into any of these details. This is also published work that Dan did, but you can kind of dig deeper and iteratively narrow down the search and say, well, where is in the code is this thing actually causing these kind of differences? And there's all kinds of things with centrality, and then doing smart variable slicing and instrumenting the part of the code that actually matters. I think many of you have an appreciation of how much work this is. Yeah, so having said that, I think clearly promising. My sense is Dan is on to better things now or different things, but obviously this is clearly a direction one could go. But I think reading his paper would give some idea of how much effort is involved in doing something like that. And of course, these kind of tools, they get after the code. And the problem in that FMA case isn't the code, or maybe it's some way indirectly it's the code, but it's not like there's something changed in the code at all. So in these kind of settings, you can use these tools. And what happens if you smart people who, I mean, Steve mentioned that nobody knows the whole model anymore, and that's obviously true, but there are some people who know some parts of the model really well. So it was already really helpful to look at, even at time one, what's different, and people were like, okay, I think this is this module, and eventually you could figure it out. So I think that this is maybe the most still open part. How can we link getting a failure to truly telling people very quickly what's actually wrong here? Right, all right. With that unhappy note, I'll shift gear here and go a little bit more into the statistical details of this ensemble consistency testing. Specifically, oh goodness, what a slide with a lot of text here that you can mainly forget here. But what I want to point out is because of the properties, because of the fact that we orthogonalize this thing and we invoke things like the central limit theorem, we can actually come up with a theoretical false positive rate. And that is, of course, useful if you want to set up that test and tune these given parameters here. And I'm just going to outline that as well. There's only one slide with some kind of mathy stuff on the next one here. But the idea is, again, we assume that the tests come from the same distribution. So our new samples come from the same distribution as the ensemble. And then we look at the probability that we get a failing result. And the way you go about that is you can frame this whole testing setup as a Bernoulli variable. And then at the individual steps, you set them up as like what we define here as sub-random variables, and they correspond to these individual steps here. Giving you the picture here. So this is again the setup where we get these new runs, we compare them. How do they compare to the other distribution? When do they fall outside in these individual scores here? How does that all sum up? And I probably shouldn't have put this math in here, but here I'll just forget about the details, but because we can make these distributional assumptions, we only need this in this very one step on the ensemble distribution with all this averaging, where we have done a lot of testing where you can really justify after you do this global averaging that there are normally distributed. You can then fully derive what the false positive rate is of this test here. And the way we have set it up in CSM, the false positive rate is something like 0.3, whatever, 5% here. It turns out that the empirical false positive rate that we tested was something close to 0.5%. And we dug into that a little bit deeper. And that goes into another important aspect about this thing is whenever you do stats, you come up with this kind of hypothesis testing framework, you assume that your samples are large enough that some of these things you assume are actually well estimated. And here we have a very specific inference problem that kicks in if we deal with finite samples. And I'll talk about this a little bit more here. So there's underlying in this framework, we assume that we can describe these normal distributions on these scores. But there is an estimation bias of these eigenvalues and the equivalent to the spread in the scores without going into any details. And in this picture, you can see it a little bit more clearly. For these smaller ensemble sizes, you can obviously see this is where we would like to be if there wouldn't be a bias here, but we get this very structured estimation bias in here. And in Theo's talk, you'll hear a lot more about that. Here's some really nice work to dig into that deeper. That's a known phenomenon that I wasn't aware about, and there's very little literature about it. But it's something you have to deal with in reality. And what you can see here, so another student, Galen, was working a lot on that. What you see here from left to right is increasing the sample size. And then what you see from top to bottom is using different statsy ways of dealing with this. And what you can see here our initial sample size, I think was 100, what is it here, 150. And if we go all the way to 1,500, that problem mostly goes away. So this is at the core of this. Anyone who works in science probably knows that estimating high dimensional covariance matrices is inherently tricky. You need a ton of data to do that. So here we get away of this, and he investigated other ways to threshold. Like, for example, here you can see doing sparse. PCA introduces other problems because we have high variability in these type of things. I won't go into any of that. I think Theo might be talking about this a little bit more here. This is the summary of what happens with these kind of different alternative estimators here. And the big takeaway from that is if you have a really large sample size, the blue is where we would, the blue dashed line is where we would really like to be. The problem more or less goes away. We can live with the sample. But of course, that's a lot of ensemble runs here, which is a nice lead into taking a step back after all the stuff I told you now. Is when is this kind of testing really applicable? So when we think about statistical, or when I think about statistical methodology we develop, it's always important to understand for what kind of class of problems is that actually relevant. And I list 4 things here that I think are the key kind of factors to consider if you want to even think about doing something like that. So when we think about these output fields here, so from these big ensemble output fields, let's say we have 1,000 ensemble members, and we really get these spatial fields and then we average them. The underlying assumption here statistically is really that we think this is a stochastic process. This can be a very complex stochastic process, doesn't need to be Gaussian or anything, but there's still some notion of like they come from something, that these fields are different realizations of something that can in some way be described in a statistical way. I'm not going into any details here, but if you have a model that does really completely different things, there's no way you could think about each one as like coming from something the same, then that doesn't make sense. So I think for anything climate model, that assumption is practically clearly met. Then maybe the biggest and still most surprising assumption is here that the mean actually captures the signal. I'm going to give you a counterexample right after that, but that's not the case. So that's also a strong assumption. Having said that, it was very surprising. I've said this before, but I'm going to say it one more time because it's still so surprising to me 7 years later that the mean actually captures these signals, especially only in 9 time steps. So big assumption here, obviously something you want to check. Then doing this kind of translation into the projected orthogonal space really only makes sense if you have a large number of output variables. If you only look at 3 output variables, no sense doing that. And then also another big thing here is it needs to be feasible that you can actually get enough ensemble members that you have a fair shot of estimating that covariance matrix, because the covariance matrix, estimating that is really at the core of being able to do that projection. If you have a model that's extremely expensive and you have 689 output variables, but you can only do 200 runs, we can't even get an inverse. But even if that ratio isn't that bad, you need, Theo will also talk about that, but you need probably, like in our setting here, you want hundreds of ensemble members who get at that right. So in cheap models, and as we have heard, you don't need to store them. You just need flops, almost free. We heard from Brian. You don't need to store them. You just need to run them once, calculate all this stuff, you can throw them away. But you have to have the ability to actually do that. All right. Here's the counter example. Just I told you all this list. So this one doesn't check at least two things, 2 and 3, which, if you remember right, we'll go back. Mean captures the signal or a large number of output variables. So this is the ocean component, one of the ocean components. I think now there's a different ocean component that we have heard about before. But the POP was the model we were testing and have a paper on. So there, same idea. We want to figure out, well, is this model running correctly under all these other changes I talked about today, earlier. But there are much fewer diagnostic variables. If I remember correct, there were 5 or 6 variables. So in that case, it makes a lot more sense to look at them individually. And the variability, I'm showing you one of these ocean fields here. The variability is extremely spatially heterogeneous. So in this setting, saying let's kill the signal and get the mean clearly doesn't work. So there we used a very different approach where we actually do these kind of comparisons. I'm not going to go into any details, but we do this comparison in space, where we really say, like, for each grid box, does that look differently? And we also did kind of the same studies. How much do you actually need to characterize this? How many ensembles and how far in do you want to run it? So very different approach. This is just one example of it. This is certainly not the tool to use for anything. So I think that checklist is really important to kind of keep in mind before you would even want to go that direction. So quick summary here and future work here. So this kind of what I refer to as structured hypothesis testing with PCA can be very useful in the context of numerical models with many output variables where you can't get bit for bit. We obviously thought about it in this kind of heterogeneous computing environment, but I think as we have heard, there can be many other reasons why that's the case here. That estimation bias is relevant if you don't only have relatively few ensemble runs, or if you can't characterize that well. And if you can really make the ensemble size really large, you don't have to worry about it all that much. And more on that you'll hear right after my talk, and how to kind of more think about generalizing this framework for other model setups. This will be all in Theo's talk very soon. And so I think it works surprisingly well. And like I had said before, the much harder open problem is finding the root cause of this failure. And yeah, I don't have a good plan for that, but we have kind of maybe Dan's paper certainly has some good ideas in what directions could one take for that. Yeah. There's a bunch of work, so if anything, that we're happy to share this presentation, of course. And I'll leave it at that. Thank you.
Yeah, very inspiring talk. Thank you. I have 2 questions. First, when you do those ensemble tests, so what resolution you're using, or how much resources do you expect? Say, I made this update and then do this experiment, how many nodes I take, or what is in a low resolution, high resolution, how much in general?
Yeah. So let me actually, I think Theo has actually just done this for new models. It will be really cool to hear all his talk about it, but let me quickly show this here in the 9 step setting. Alison, you can maybe talk more about, actually, I was going to talk to you about this here. Yeah, this is the setting. Alison, do you want to maybe answer the question, because you know more about the compute resources than I do?
Oh, the question was about how many computing resources. I think I usually run on about 70 processors, and honestly, it takes me longer to copy the output data and compress it to my permanent storage than it does to run the model. So I usually submit hundreds of jobs at once, and if no one's using the machine, they're done. It's really pretty. 1 degree, usually we do 1 degree resolution. I mean, we have done higher resolution for that IHAS project. We did 1/4 degree resolution, so that was obviously more expensive, but they had lots of cycles. It was at the TAC computer, and they wanted to check it, but usually we just do 1 degree.
The second question related to this is, for this tool, what do you expect say, users can use that is that you can use, you mentioned about compiler changes, but for scientific updates, say the one you mentioned about soil update and then you found error. Is the developer's purpose is to see, am I coding correctly, or am I expect my code change will be identified as changing climate?
Yeah, so obviously that depends on the kind of code change, or the kind of code change we were targeting here, and I think that people use in practice is that they want to optimize something in the code, but they don't expect it to change the climate. That's exactly, and that of course is really useful because you can say, well, I changed whatever that routine, and now I'm running 3 of these really quick runs that takes me no time, and then I can quickly check did that happen. If you change the climate, if you actually purposefully introduce new science where you say that it changes the climate, then you have to redo the procedure, because then you would want to re-establish what is actually the ensemble. This is a great question, and that's kind of what Theo here will talk about. It is in this case is not using the same model and changing it, doing something that is a true scientific change, but rather using it for a different model that tries to do the same thing.
Thank you, Dorit, for the great talk and the great tool. It's absolutely invaluable for CSM developers, this tool. And I wanted to mention that we do have a website where you can upload your 3 ECT samples and compare it against the ensemble. That's for the CSM 2.1, which was used for CMIP 6. We don't do this for our current development model because we're already expecting climate changes with pretty much every contribution to the model. So once we have a stable, fully coupled model again, we'll generate another ensemble and start testing that as well.
Thank you.
I had a quick question. Excellent talk. And my question is, could you put some light on why you can identify the changes in 9 time steps? Because the error is still growing at the time, so it's in a very non-stationary state.
Absolutely. I mean, the whole thing is, the only answer is because it's already manifested. I find this completely surprising myself. But this is apparently in this system, there is something there that even in these means, it knows the difference. I can only tell you, we've done it by now, I don't want to say a million times, but thousands of times, and it is a reality. If you had asked me this thing 5 years ago, do we think we can see in 9 time steps all kinds of things that climate scientists are worried about? I would have said, no, probably not. But the reality is, it is there.
Very nice talk. Thank you. So I just wanted to ask, like you said, you guys do 1 degree simulations. Have you tried lower resolution to save computational time?
I think Alice and Jim just talked about that. They did it once for quarter resolution, and
we've done lower too. We've done 2.
Okay, so was it like equivalent? Did you get the same results with 2 degrees?
So we created a 2 degree ensemble and tested against that, but we didn't do a lot of the extra work they did to actually reduce errors and see if they
I mean,
yeah,
I think
no,
Theo's talk might, this is an excellent question here. So all I talked about is very specific, and Theo, who is a PhD student, will introduce here, so has really done great work thinking about this more broadly and saying, like, how can we actually take this framework and use it for a new model? And you can think about a model like CSM at a different resolution as a new model in a way. And how can we streamline this whole process? Because this is like a lot of this stuff, I didn't maybe write it down as well as I could. And Theo has done that work to really think this deeper and say, like, here we have a new model. Balwinder is your name, right? Yeah. Wants to run it at 2 degrees. How would you actually go very efficiently about this? And hopefully we'll learn this here soon. Yeah.
So we have a few online questions. Abhishek says, thanks for the talk. I was wondering how complicated it might be to extend EC to other climate models, say ICON.
That's the next talk. That's going to be the next
That's the
talk.
next
Hi,
talk.
Abhishek. I think hopefully very simple. Thanks to Theo.
Yeah, that's the next talk. I think the next question is sort of the next talk too. What is the impact if I increase the size of the test simulations from 3 to a larger number?
In the neuron? You could do that, so that, you know, when we look at that whole derivation of the like theoretical false positive and all this kind of stuff, you can set up whatever you want, really. That 3 happens to be a sweet spot, and we were thinking about like, let's do it as little as possible, you know, for the users, and 3 really hits it already. There's probably nothing to say against 2, 4 or something. Like, these are arbitrary choices. You just need to keep this all in mind and do the math and like work on the theoretical false positive rate. In our setting, because we had such strong power no matter what, we really wanted to push the false positive rate down. Because, I mean, you know, cry wolf only once, you know, like make people work really hard at saying it failed when it didn't fail. That's kind of what we don't want to do, especially in a setting where we detect anything everywhere anyway. But if you're in a different setting where you can live with having a much higher false positive rate, you could set it up quite differently. This is all published work, the theoretical false positive rate. You can literally plug these kind of settings in and do whatever you want, wherever you want to be in that balanced space.
Yeah, thank you. This is absolutely fascinating. I've got maybe a slightly philosophical question, or maybe a pragmatic question. So when you talked about things that should pass and things that should fail, you set up a nice dichotomy. The things that should fail are things where you've essentially changed the forcing, more carbon dioxide in the atmosphere, for example. We know that should give you a different climate. And the things that should pass were very low-level things like changing compiler flags, changing the number of threads. But it seems to me there's a gray area in the middle of things that probably shouldn't change the climate, but probably will, like changing grid resolution. And I wondered if you could talk about kind of that pragmatic question of things that you might change in the model that shouldn't change the climate, but would fail this test, and perhaps vice versa.
I absolutely agree. Like, that literally is what I want to do during my sabbatical, because it goes back to that question about using these different compilers. Some of you might be familiar with that lens ensemble. Alison, do I still have time, or should I be? Okay, good. So that lens ensemble, which was a large climate project that was run here at ENCA, 5 of those runs, I think, were run at the University of Toronto. I tell you a little story here. And one of my colleagues who teaches at an undergrad stats institution, they wanted to analyze this data for some nice project. Turns out, I'm talking here, second-year undergrad students, they could all identify which runs were run in Toronto. Then afterwards, they were sent back to Jim knows all about it. There was a disclaimer on the webpage and all that. So staying in your philosophical realm, like what do we consider climate changing is really a loaded question in so many ways. Because I think we are climate scientists historically, and obviously for this kind of chaos theory reasons, always think about perturbing the initial conditions. But it might be the reality, and people might not like to hear that, but maybe we should think about this much broader and say, well, if we change to these heterogeneous computer environments, we have all these, whatever numerical instabilities in the models and all these type of things. Maybe we should think about this much broader of what we actually consider truly changes. I'm obviously not the right person to ask this, because I'm sure climate scientists have thought about this much harder. It was just informative for me to see the reality of this. Like this project I was telling you about, this, I looked at this one afternoon, and it's blatantly obvious that the variability in output fields, if you change compilers compared to, and it mainly goes in that direction, compared to perturbed initial conditions, is higher. In most output fields, not all. And that's saying something that speaks to the fact that the runs from the University of Toronto were really different, but not like crazy different. They don't take off. So maybe we need to think about the chaotic uncertainty in different ways. So I think this is a long ways away from the fact that maybe also like the work we heard much earlier today about making sure the code itself is actually better. Like, for example, if I see these numerical instabilities, there's probably lots of stuff you can just take care of by making the code better. But then it also highlights, though, we can do all these really nitty-gritty things to make the code better, but the reality is maybe still this is a model that on some high level does all these things. Like we've talked, most models run on 100 by 100 kilometer grid cells, and we parameterize 1 million processes. Clearly, we're not, me breathing or something like the typical butterfly effect in chaotic systems. So I think it's important to keep that in perspective in this philosophical thing. Like, not to say I'm against these efforts in any way. Yeah, it's just important to also be aware of that.
I'll just kind of quickly ask quickly. I'm going to extend Balwinder's question in the opposite direction. So at the DOE, we're working on a model that runs at 3 kilometers, and that produces a tremendous amount of data, which is probably prohibitively expensive to process.
By taking the mean is pretty simple.
Okay, but maybe my question is moot because it's so simple. Because I was going to ask, if you find yourself with these massive data sets that are difficult to work with, how valid would it be to look at coarsened versions of that same solution? Not coarsened runs, but just the data has been coarsened, and hopefully you still capture a lot of the statistical variability, but maybe not.
No, yeah, that's exactly the interesting question. And you can obviously very easily, nothing is very easy, but you can verify that. So like I said, my expertise, I did my whole postdoc before coming here on like statistical inference on very massive spatial data that are non-stationary. So that's why I got involved in this project. The question is, where's the signal? If in your super high-res model, the signal still is existent in the mean, then who cares? For what we have seen, and this is only based on this one data point running it at a quarter degree, that still works. So it might be that because you don't care about representing everything. Clearly, you're not representing everything. That's why we have high-res models in a mean. But the question is, do you have the signal that indicates the failure mode? And if that's still preserved, and there's a very simple way of doing it, test it. And of course, initially I was thinking, at the very least, we should have a regional means and test all this. But it turns out these global means do the trick. And of course, the way to go about that is to say, instead of the extreme way to do this is to think about this truly as non-stationary stochastic fields, and that do this comparison, which there's some literature of very complicated. But the simpler you can, of course, make it, what you compare, the more you can reduce it. So my first thing would be try this framework, and do you have a signal? If you have it, you are in good shape.
I wanted to briefly mention regarding this, either being able to detect things at a few time steps or very long periods. Our group has found this as well, that for a lot of climate changing things in the atmosphere, if you start with a very similar initial condition and you do 2 runs, and it's for a few time steps or a few days, then there's a very clear systematic difference between the 2 runs. And then internal variability and randomness in the model take over and really kind of wash that out. But then if you run for long enough, then you get to see that systematic bias again. So we see that again, that either a few time steps or a year or more, but somehow in between, it's not as useful.
That makes
a
lot of sense, actually. Yep, that makes so much sense. I'm so glad you said that. Yeah, really good point. Thank you.
All right, thank you, Dorit. The next speaker will be, the next speaker will be Teo Price-Brancusia, and he is a grad student at CU Boulder, but he's been working here at NCAR with myself and Dorit.
Hello, hopefully you can hear me all right. Yeah, this is definitely sort of just a follow-on talk to Dorit's talk, and so hopefully we can continue some of these conversations. A lot of questions were about, so that's sort of nice. So this is sort of talking about methods and tools for the application of this kind of approach, this UFBCT, to new models, which it seemed like some people were interested in, so that's nice. So the purpose, maybe well discussed, identifying these inconsistencies between these large scientific model outputs in different configurations, and overview of the approach, right? So we start with this big ensemble. We do sort of the first part to try to summarize the big ensemble. And then we take the second part where we do a few runs, try to issue a pass or fail. And this has this nice sort of dichotomy of work, which Dora talked about a lot. You know, most of the work is done in part one, and then there's sort of less work that a user needs to do in part two. But there's actually sort of a variety of sort of these model dependent parameters that need to be decided on. So one of these is like, how long do you need to run your model? You know, that might really vary. With CSM, right, this previous work found it could run for maybe as little as 9 time steps. So that's nice. It might be different for a different model. How large of an ensemble do you need? How many of these principal components do you need to really characterize your model? And then Dora talked a little bit about this too. You know, what do you consider sort of a failure in an individual principal component? How far outside of from the mean do you consider a failure? And so if you want to, I feel like to sort of pull the curtain back a little bit of this work with CSM, a lot of this stuff was sort of developed over time. Answers to these questions were developed over time. A lot of Dan's work, you know, how long do you need to run this for? You can actually run for really short amounts of time. How big does this ensemble need to be? How many principal components really capture the model? That work actually sort of derived from these like earlier year-long runs and then sort of just transferred to later really short runs. But we really want to apply so you can model. There's really sort of this like part zero, this sort of like step zero, which is if you're going to a totally new run, maybe you need to decide these things first for a given model, and then you can move into this part one and part two. And as long as you don't really change the overall structure, so the complexity of your code, your model, then maybe part zero can sort of stay valid for a while. And so that's sort of the goal of this work. How do we go about applying this method to new models? So can we develop a recipe, and really a recipe that we can sort of implement in a somewhat automated way? That's sort of maybe a goal of a lot of this work, you know, is taking ourselves out of this handcrafted approach. So can we choose these test parameters that help us detect changes? That's obviously one of our main goals, but also ensure usability. So Dora's like, only cry wolf once. We don't want to be like giving a lot of erroneous failures. People probably won't use the test at all then, and they won't be that useful. And so we're going to talk about this actually applying to a new, different Earth system model, this MPAS, atmospheric component. Thanks to Michael for all his help on this. And then try to see with CSM CAM, you know, are the parameters that we use for this test previously in a really different version of CAM, are those sort of still valid now, or do we need to update them? So I'm going to try to go really fast here because there's just like not that much time. But when we talked about how long to run a model, and it's sort of funny to give a talk like this in front of people who've been doing this work for like 10 years and done most of the work that it's based on. I'm like, oh, I don't offend anyone with what I say. But in a lot of this work to sort of first decide, like, can we run these models for really short amounts of time and get a signal? That was a discussion like in the graph that Dora showed, really like how much spread, how much difference is there between model outputs? And we found that's sort of another nice way to think about this, and maybe one that translates a little bit easier to sort of some concepts of automation and maybe even also sort of like an intuitive sense, is how many of these variables in our outputs are considered sort of non-normal. So if we think about the structure of the test, like Dora said, we actually only perturb one field. So all the other fields across the ensemble start out as these like uniform distributions. And as our initial perturbations in that one field sort of propagate through the model, they make it into these other fields, and then through the spatial averaging, they sort of look more and more normal. Not all of them look normal even at the end, and some of them sort of by chance will always look non-normal. But eventually this number sort of stabilizes. And this really reflects a characteristic of our model. How fast is your model sort of coupled, or all these fields coupled in your model? And so this is sort of the approach that we've landed on, which is let's look for when this test of normality sort of stabilizes. The total number of our non-normal variables stabilizes. And this is for CSM, and we can see sort of stabilizes. This is in CSM 2.3, which is CAM 6.3, I think. Sort of stabilizes around this 7 to 9 time steps. So that's nice because we can still keep Dan's title of his paper, which was so catchy. So now for some of these other parameters, I really have to take this detour to discuss this variance estimation bias, which Dora mentioned. And the idea is when we're estimating the variance of our principal components, there really is this sort of directional bias, and it has been known a lot, but probably under discussed for a long time. So this is from Wally 1956. You can see our sort of stochastic noise term over there on the right decreases as our sample size increases with the square of the sample size. But then there's a term in the middle, and it only decreases with 1/n. And so that's not great. And these lambdas are sort of our true variances of the principal components. And we can see that this bias really depends on the actual like relative size of those variances. So it's a little tricky. And on the left here, we see sort of like an idealized version of this. And sort of the net effect is these large variances are overestimated, the small variances are underestimated. We already talked about this. In reality, it sort of looks more like this. And because of these like really close relationships between the relative variances, it's not this smooth curve, and there's actually like a lot of noise introduced in trying to estimate it, and there's even more variance if you try to use these alternative estimators. It opens up like a lot of cans of worms, different cans of worms. And so when we take these next steps, we'll try to do it with an eye towards the effect of this bias. And so for our first example of that is how many principal components we really need to describe a model. So one sort of way that this variance bias shows up is that it changes our estimate of how many principal components we really need to estimate sort of the variability of a model. So if you see this like blue curve, so you see this like blue curve is a really small sample size. You see it sort of goes up steeply and then peters out. That's because like overestimating the variance of those early principal components. And so if we use too small of a sample size, we might say, well, we actually don't need that many principal components to estimate the internal variability of our model. But as we see, as we increase that sample size, it sort of, that curve flattens out and it starts to stabilize. So that's actually sort of what we'll try to take advantage of. We'll say, let's increase the sample size until the number of principal component dimensions that we need to explain a certain amount of the variance also stabilizes. And so we can see here, this is with MPAS-A. We need maybe 38 principal components, dimensions, to explain 95% of the variance. And that gives us also sort of a floor on our ensemble size. So that's nice. But the bias shows up again, and maybe in a slightly more insidious way, when we talk about this false positive rate. And that really reflects how large of an ensemble we need when we choose that. So let's say we underestimate the variance of some specific principal components like we're expecting to do because of this this later principal components. So if we think of our biased estimate of that particular distribution in orange, you sort of narrowed the width of that distribution. So even samples from our true distribution, these false positives, we're likely to fail those even more than we would if we knew that distribution perfectly. So that's not great. And as we increase our ensemble size, we'll address this. And this is sort of like one byproduct of the setup of this test, which is failures from these underestimates aren't actually sort of canceled out by overestimates of other distributions. If you fail a particular principal component, you fail that principal component. So those can sort of add up. And so in order to do this, we sort of build in this this empirical false positive rate testing. And we see that as we increase the ensemble size, sort of starting from this floor we used from our stability of our overall variance, where that bias is somewhat averaged out between the different principal components, we see we continue to decrease our false positive rate. We'll do that until we sort of get to this acceptable false positive rate. But this sort of introduces this additional question. So this failure cutoff, this has sort of traditionally been set at m=2, this sort of canonical like 2 sigma cutoff. It's a nice thing. But as Dorit said, we can sort of derive good values of all of these sort of failure parameters. So the number of new runs we use, the number of runs that are considered failures, and all of these together are really what set this empirical false positive rate. And this really comes into play because as the models we consider get larger, we're going to need more principal components to explain them, and that means that we have more chances of failure. We're basically rolling the dice over and over again, and this is a curve of that, sort of our theoretical false positive rate. We see if we get to a model that requires like 120 principal components to explain it, we keep all these parameters sort of the same, we're going to be failing all the time, 5–10% of the time, even these false positives, right? So we introduced this step to numerically solve for m sigma, which is this one sort of non-integer value, so we can set it to anything, to give us a reasonable theoretical false positive rate. And this helps us give us sort of a estimate of how much of our false positive rates do this like theoretical floor of comparing things to a distribution, and how much is sort of due to the bias. So overall, we determine the length to run the model, we determine an appropriate number of principal components to use. This also gives us a minimum ensemble size, and then we'll determine an appropriate failure cutoff and ensemble size to prevent too many erroneous failures with this false positive rate. So now moving on to some testing done with this new model, and now this maybe will sort of introduce some interesting questions related to what people were talking about just before. So this is the atmospheric component of MPAS, the model cross prediction scales, this unstructured mesh-based model. And so there's a few different kinds of test types, and sort of alluded to this previous work done on these, but one of them is false positives, sort of do runs from the same configuration fail. We'll sort of consider that step done because we sort of did that by construction. Then we'll consider these non-climate changing modifications, and maybe this is a slightly blurry line, but things that we know might lead to bit for bit changes, but aren't expected to affect our scientific conclusions. And then finally, ones that we really would expect to affect our conclusions. So this refers as EET, which I think maybe Dan coined this term, but sort of basically we'll run the test with many different sort of samples of the ensembles and test runs, basically running it many times to get an overall failure rate. So for MPAS, we'll say, oh, well, let's try changing the compiler. We get this like pretty low within our sort of goal range of our false positive rate. So that's nice. Core counts, changing the compiler optimizations, all of these basically say like these haven't sort of been statistically distinguishable. Changing some order of operations in an equivalent way is a little higher, but still pretty low. And then we get into ones that just fail. So one of these is precision. And so this is a pretty massive change in a model, right? This is affecting the whole model for MPAS, and it fails all the time. And I'm going to talk about this again after we look at the second one, which is maybe the unsettling, because this is another example, similar, right? This, our sort of accepted configuration was run on Cheyenne, and now we've got this new cluster, derecho. Hopefully the model runs the same on derecho, and when we tested it, it turns out like 40% of the time it does not. So that's maybe not great, but we had a little hint thanks to all this work done before. So if we turn off FMA, it passes. And I think these are both sort of interesting examples, and maybe get also to maybe some future work, which is this approach really relies on spread, sort of the spread, the internal chaotic variability of which like this large ensemble study and stuff, a lot of other work gets to that. But it's taking sort of a snapshot in time, right? What is the spread at time step X? And these kinds of changes, we've got more work to do, but it's possible that they're sort of changing that rate of spread, right? So we introduced this initial variability via our perturbations, but say you change from double to single precision, now at every time step, at every kind of equation, you're also introducing this like rounding error. You're introducing perturbations all the time. You might be spreading out. So we maybe need more work to distinguish between what kind of failures are due to like changing our mean of these new runs, or are they just changing the spread? And how much is spread sort of like a key component of a model? On this other kind of testing, changing climate parameters, this was relatively limited testing, but we looked at these 4 different parameters that we maybe would expect to change the test. My one request for all model developers is make it so that it's easy to change parameters in your model, feel like nameless or something, as opposed to recompiling your entire model. That'd be nice. But we did something a little different here, which is sort of really change these over a range. So Dora talked about previously, often these were like, to a climate scientist, like what's a change you would expect to fail? So we sort of like extend that a little bit, which is like, okay, we're going to change that over all these orders of magnitude. And if we plot the locations where the test starts to pick up those changes, and there's a lot going on the slide. So here's our big conclusion. Basically, we detect scientific parameter changes down to around 1 to 10% magnitude, which I don't know. Would you say that's good or bad? Maybe it's hard to say. Maybe that's not sensitive enough. But I think one of the interesting takeaways here is like, what is that when we single to double precision, that fails all the time. Now we have a little bit of a comparison to say like, that's sort of like changing a parameter in your model by like maybe up to 10% or something. So it's like these kind of like non-climate changing modifications, at least from this view, sort of have an equivalence to changing scientific parameters like pretty substantially. So the final thing I'll say is, when do we actually need to update these test parameters for a new kind of model? So we've looked at CAMP, but CAMP's changed a lot. So now looking at sort of this like CAMP 6.3 versus 5.3, after we've excluded sort of these like numerical issue variables, we're going from 108 default output variables to 275, and that really reflects a lot of new physics. So before, these were the parameters that were used. Or I touched on these. If we go through the same approach, we're now saying, you know, maybe increasing, maybe we could even reduce the time step slightly, but we're still in the same sort of area for time step, maybe greater than 7 time steps. But maybe we need to increase the number of principal components we consider quite a lot. So we wait for this to stabilize. Maybe now we're looking at 128 principal components versus 50. What about M sigma? At 128, this curve is like way too high, this theoretical floor for the false positive rate. So if we adjust this to one that gives us sort of this reasonable balance between false positive rate induced by the bias and sort of theoretical false positive rate, we might change our failure cutoff to 2.23. And this relates to a substantially larger ensemble. So to like touch on a lot of people's questions, we're sort of saved through all these steps because running for 7 time steps or 9 time steps is super cheap. So even a large ensemble like this might be very reasonable to do. So what's a big takeaway here? If you made a big change in your model, you know, we might need a relatively large change to update the ECT method to like still be appropriate and capture the full behavior of the model. So thanks.
I had this question after Dorit's wonderful observation that the mean may represent the signal. I was very preoccupied with that. And then I remembered I had read something about that in rounding literature. So I did my Google research and found a paper. So I think if I'm right, buy me a beer. I think it is the rounding mode. If you try stochastic rounding in single precision, it may work better. This is what Tim Palmer's paper that I just forwarded to Doris and Allison seems to say. So it is not the precision, it is the rounding bias. And stochastic rounding has a very nice property, which is if you add up a bunch of numbers, that is the deterministic addition problem we have, right? Yeah, they have shown that backward error grows much, much lower than with the round to nearest. So there is that. Okay, try that. I don't know the answer.
Yeah, that's an interesting idea.
Yeah. Have you thought about a different version of this tool that instead of giving you a binary pass-fail, actually gives you some measure of distance between 2 models? And it reminds me of, there was a lovely paper by Reto Nuti a few years ago in which he looked at all of the models in the CMIP5 ensemble and had this beautiful dendrogram showing which models were more similar than others. And it turned out models from the same lab were always more similar than models from different labs, even over multiple versions, which was a surprising result. But it occurs to me that there's a version of this tool that, yeah, is a really nice potential way of analyzing model similarity across all sorts of dimensions.
Yeah, I think that is a sort of a key, maybe like next direction. So George talked about like a huge goal of this work is sort of can be fast, can be used sort of continuously, can be automated, but then you get to a failure and you're sort of confronted with this question of why or how or in what way are we failing? And I think at that step, sort of there's these additional maybe questions that we're sort of like maybe well equipped to answer, which is not just, you know, we're moving in this one kind of way, or we're failing, but you know, is that because our mean has stayed the same, but our model now has this greater variability? Is it because we do have this trend where like these 2 different model configurations predict like mean warming that's different? So I think for that sort of like post-failure step, there is like a lot of work to be done, but some interesting like hints maybe of like where that we could ask those questions.
Thanks for the talk. I don't think you mentioned what resolution you used impasse at. Was it also at 1 degree, or did you use?
That's,
You know,
I guess because it's a, yeah, because it's a mesh, so it's a little slightly different maybe, but Michael's the, yeah.
Roughly 1 degree.
Yeah.
And then have you looked at all, so impasse and CAM-SE, which is what we're using in CSM now, both have this variable resolution capability. Have you looked at all at the impact of that variable resolution mesh?
No, not for this kind of work. I guess I think one interesting thing was like that these results did change going from that 1 year long run to the ultra short runs, like how many principal components you need. So it'd be interesting to see if that sort of same kind of difference holds for resolution, that there would be different sort of recommendations or not. But yeah, thank you. All right.
Okay. Thank you. And I see, I'll just answer the one quick question under to Jackson. Hopefully in the next month or two, there'll be a citable publication. Okay, thank you. All right, the next talk is June Wang, and she is from NOAA. And let us just share it again. I'm obviously closing some window and I was supposed to.
Yeah, thank you all. So I will talk about the correctness and reproducibility in the UFS weather model continuous integration. So here's outline. I will talk about the challenges when we do the code commit. Basically, all the changes coming to the model and what are the challenge for us to get the code change into the model correctly. And some I will also talk about how we verify the correctness and reproducibility in code update, then some future work. For those of you may already know about the UFS weather model, this is NOAA's unified model system that will be used in operation. So at this time, the UFS weather model is open source software. It supports both research community and operational development. So the model will be implemented in operation with code updates from community and from the committee, including research centers and also universities, and of course, NOAA labs too. So far, it contains 17 authoritative repositories. So for us, some of the repositories are not managed by NOAA. So basically, the components listed on the right, you see many of them are managed by different organizations. We have 9 major flagship model components. As you see, atmosphere side, we are using the FP3 DICOR, CCPP physics, and we have land system, wave, ocean, sea ice, and also aerosol and chemistry models. I want emphasize here the applications we support for those operational configurations. So this model actually has been run to support the coupled prototypes. So when we develop the operational configuration, the prototype are the configurations we build up and towards the operational implementation. We have implemented actually 8 prototypes. And then at this time, the model configuration have been set up for those operational model I listed here. For example, GFS version 17, global ensemble forecast version 13. Those are the global models. And then we also have regional models, for example, roofs version 1. It will be in regional and high resolution. And it also supports regional air quality model, hurricane model, and data simulation, JEDI. And for us, we also have marine DA forecast system that is using this model. So far for this system, it has 215 forks. We have at least 150 active developers, and there are 2,000 issues and pull requests has been committed to the model. And then we have 10K files, 4.3 million lines of code. This model is supported in operation. Try to get this. Anyway, this. Oh, you cannot see. That's okay. That's okay. Yeah, on the right.
If you switch it from the presenter view, we might be able to see. If you click use slideshow at the top. Oh, maybe not. Because it was on presenter view.
Yeah, it worked. We tested it, but I don't know what happened.
Okay, that's fine. Yeah, that's okay. The animation, I actually try to show you the code updates coming into the repository. It's tremendous code changes. So this model also support operational platform and R&D platforms. So we are working with the UFS community to develop this model. Okay, the challenges. When a code change coming into the repository and people are expecting the code change to be committed. So as you see, this is a complicated system. So how do we verify the code updates committed to the repository are correct? The challenge we face is that there are significant amount of code updates every day based on many code are 30 years or even older than that. And second, as you see, the configurations are built upon the shared component. So any incorrect code updates or bugs, when they come into the repository, it has big impact for many applications. And third, the testing framework is incomplete. So as you see yesterday in Ed's talk, he talked about the unit test. That component is missing in many of the model component. Component itself, component testing is missing too. And so far we build up the regression test and we heavily rely on those regression tests. So all the regression tests will be set up for every applications you see in the previous page. There will be some testing there, just got the code change coming to the repository, so they won't break the current capabilities. Third, we also implement this standard code update procedure. So basically every PR, if you make a PR, you come into the UFS weather model, you see a template. But many times, even today, if you go there, you see many PR, the code manager mark it incomplete. Why you do this change and what you changed? What do you expect for other applications? Which one will change? This is unknown. So this makes make sure for us to understand what change is coming in, for the community to understand the impact to each application. This makes those work hard. Communication also is an issue. I understand for many people, when we have a code changes, we're eager to get this in. When I have this code, the features in the repository, okay, I achieve something, but the testing system, how is my code change impacting others, other application? What do I expect? This is more than just that you are doing your own development. This because we are working on a unified system. This is a big challenge too. Next, very limited resources. This is include the human resources to manage the repository. to check all the code updates are correctly committed, tested, and this is also including the test system. Testing is not cheap. We do want to have basic tests to at this time, since when the change coming into the repository, we hope at least the testing has been done, but that is unknown. So how can we make sure the change coming in are tested? So we have to set up those test framework, and that is not cheap. So ensure correctness in the UFS weather model CI. We do want to have a goal in our mind is that the code changes or updates produce results scientifically and technically verified. So the change when you have a PR come into UFS, at least you need to show the change you made scientifically tested or verified, and you have the results to show that. For us, testing is a key to validate correctness. We have users, I made the change, I think this is correct, I'm coding correctly, but we need to prove that. So far, when we look at the test, the code updates, we clarify them into 3 categories. The first is simple, the code changes do not change results. So for example, I rewrite the code, I want to have consistent variable names and so on. So everybody knows it should not change results, but you need to test and show that. Or I implement a IO feature, and this IO feature will not change results. We know it doesn't change signs, so it should not change the output. Or I want to add a log information. So this is a simplest one we want to, so far we have. The second second type is the code changes did change results. So this includes both science updates and technical updates. I think the previous talk also talked about, for example, the technical update, compiler update, library update, rewriting the code, they're all, or porting to different platforms, they're all technical updates, and we expect the results will change. So how do you show the change made correctly? On the other part, there are science update and bug fix, and you need to show the update produce results that scientifically verified. And so basically for scientific change, we do want to see the results from scientific experiments. And for the technical part, we want to know we can confirm the update did not change climatology. Then there are new features. So the new features coming in the current procedure, we ask the developer to implement as options. So I have this new feature I want to use, but a better way is you implement as option so you do not impact other people's features. In many times in the final development, the feature will be included or not included in a operational configuration will be tested later. So the test framework, this is on the right. I think many people may already know this model. On the left of the V actually is what we do when we do the development. So first the requirement. I want to make this great wave drag updates, and then I analyze what should I do, and then I look at the code, what modules I will change and how I implement that. Then I update, I do the module design. So how my code will look like, then you do coding. But for us, when it comes to us, it's at the bottom. So we have your code. And then we hope we can build this hierarchical testing framework. So first, your code, you wrote the code, you need to have unit testing. I really actually now agree with Ed. Otherwise, it's really hard to check your coding is correct. And then we have this integration test. You have your code and how this code is interact with other part of the code. And then we do system testing in the application level. You show the results. And then in the end, the accepting testing would be tested in the workflow side. So for each of the, on the right side, you see the unit test, integration test system. It has 4 components. First, you need to have test data. And then you need to have test manager. You execute the test, and you do need to monitor the test results. So for the UFS CIs, where are we? Most regression tests are actually system tests. We have very limited integration tests. So the component, how they interact with each other. Some components have unit tests, but not all of them. Accepting test is actually delayed to the workflow level. So in the current UFS weather model, we do have regression tests. This is how we set up and run regression tests. First, for the test data generation, we have the input data, basically they're what we call the can case, the fixed initial condition, fixed configuration for all the supported applications. We do have tests for global, regional, air quality, and those you see. And the data are saved on tier 1 platform and cloud. So anyone, if you are doing development, you can get the data and you can run those tests. Also, we have the results from all the regression tests we set up, saved on the as a baseline on those platforms. So for us, those baseline give us an idea when your change coming in, if it change results, actually we have something to compare. So we do have the test manager, we have the regression test script, and we have CI pipeline to automatically run those tests, and then we monitoring the results. Basically, what has been changed will be recorded in the log file, and the new baseline are saved for the next code commit. So this is a cycle for them. We also have some supplemental tests here. I do want to say for operational configuration, code robustness is really important. So we developed this, what we call the operational requirement test. All the changes when it comes in, we have debug tests set up for all the applications. This need to be run and pass those debug tests. Reproducibility test is very strict, I know. We have baseline tests, so no matter where you run, we need to get run-to-run reproducibility. You cannot run the first time you run a result, and second time the result will be different. That's not accept. We have threading test. If you are running with thread, basically all the tests, all the code changes coming in, we require you implement the threading. And we have the domain decomposition test. You have the same MPI, you do different layout. The result has to reproduce. We have MPI task test. It's what we call the mini scalability test. And we have restart test. So basically, this all required for operation model. When you run in the operation, those are the required features. So I do hope that in the community level, maybe when you do research, it's not critical, but if you think your development work will be used in operation, then those are what we have to have. Some supplemental tests, we do have some tests we call the butterfly test. So basically, if you see the feature on the left, so we only perturb 1 bit of the lowest temperature initial condition on a single point. So that basically 10 to minus 20 around. So in 5 days, you will see the results on the right. I took 2 points. So you see the temperature near the point actually doesn't change, but in the South Pole, it does. So we use this feature to test transition to different Intel compiler. So these are the basic results. And we also use for the platform that we tested all the time, we are confident the results are correct. We use those to test it. For example, the code, rewriting the code. So the left you see the SST change when we run on 2 different platforms, and the other is the code rewrite. Verifying the correctness for new features. So all the new features, if it's scientific innovations, so those are the things we're looking at. It's rigid, but those are the things we do want to know user did those tests. And for technical innovations, those are the items we are looking at. Basically, we do want to, for example, run different resolutions, scalabilities, scientific changes. Is that the scale aware? Is that model run stable? Those are the things we're looking at. Future work, currently we are still manage the UFS weather model with EPIC, and we do hope to build this hierarchical test. And another thing we were looking at is for the changes that will change results. So we are looking at the machine learning method. So we hope to use the unsupervised machine learning to catch patterns in the control baseline. And then when the scientific change comes in, at least we will see if those patterns are changed or what is the impact. So that is something we're looking into. Okay, that's all. Thank you.
So Steve hinted at this earlier, but that didn't get into details. So I'm wondering if you could kind of help me understand it. It seems like the way you're using the terms validation and verification is maybe very different from how we use them in software engineering. Can you tell me what you mean by those?
Okay. So on the left side, even though for many development, I think for the developers, they may not know those are the steps they go through, but they are. On the right side is what we are trying to build the test system. So validate phases. This is what we have. But we want to communicate with developers. On the left side, those are the steps you take. So on the right side, those you take and can be recorded in a way. On the right side, the testing can test to ensure the code quality. Okay, so for example, on the module design, if you update your code, we want to have a unit test associated with that to confirm your code is running correctly. Maybe that's but
okay, I'm gonna let you all follow up. It's lunchtime. Everyone knows the drill in the cafeteria. 1:20. I think yesterday I forgot to say when we resumed. So one. Okay, I'd like to get started. It looks like most people are back. So our next talk is by Salil Mahajan. Did I say that right? Okay. And he's at Oak Ridge National Lab. So take
Hello. Yeah. So I was saying this work was heavily inspired by Allison's work, Doris's work, and their colleagues and their papers over the past few years. So basically, we're trying to apply statistical tests to ensure climate reproducibility in Earth system models, component by component. So we've done it for the atmosphere and the ocean. Let's see. So this is work done under the E3SM project. So E3SM has a big mandate to effectively use a DOE leadership class HPC machines, which means using hybrid architectures, which means refactoring code to improve its effectiveness. And one of those goals is also to improve model trustworthiness. And if you look at code evolution, you'll see that there are 2 ways of changing code. One is bit for bit reproducing, where just people trying to add a new comp set, for example, a new output variable, etc. Then there are these non-bit for bit changes, where you would add, say, a new parameterization, and you would expect the model to improve or at least change. But then there are changes where you're porting code or refactoring, where where the answer is non-bit for bit, but you not expect the noise statistics or the climate statistics to change. Right? So our goal is to test the null hypotheses that climate simulations remain statistically equivalent or indistinguishable or similar after unintended innocuous non-bit for bit changes. So as we have been seeing all through this conference, computers represent numbers as truncated floating points, they're round off errors, and they're non-associative. So large numbers, when you add in different orders, you get a different answer. This could be caused by many things: optimizations, hybrid architectures, refactoring, etc. And on top of that, climate models are very chaotic. Lorentz butterfly mode, for example, and any small change in the system can lead to orders of change in a very few time steps very quickly. This is an example from CAM4 and CAM5 from a recent paper. So again, the problem is to how do we identify systematic bugs from innocuous non-bit for bit changes, and is there a way to do it with statistical tests? So ETSM has a bunch of tests, just like every other model. It's on GitHub, and there are nightly tests that are run, which include smoke tests, restart tests, system tests, performance P layout tests, and things like that. But we also have a couple of non-bit for bit change tests. Convergence test and perturbation tests are short tests run in a few time steps, and Balwinder has been working on that. And then we have these climate reproducibility tests, which are statistical tests looking at a longer term global annual mean averages. And then, of course, we have expert opinion and ad hoc tests. So just what we have been talking about all these past 2 days, if you add a perturbation to the initial condition, the error growth is very fast. And within 30 days, you'll see that each of your ensemble members is uncorrelated with each other, and you get a different weather for each ensemble. So this is for about 150 such runs, looking at the L1 norm of T850 global average, basically global average difference in temperature compared to a reference run. We just perturb the initial conditions. And so the model, the error grows, and you get a constrained chaotic system theory. And then, so in our case, the problem that we're facing is if you modify the model, and it might lead to a different ensemble. And how do you show that ensemble X is the same as ensemble Y or different than ensemble Y if there is a difference? So again, to rephrase, this is more, and this is just one variable. We have tons of variables. So it's basically a multivariate two-sample equality of distribution testing problem, with the null hypothesis being that they're statistically equivalent. And again, it's a high dimension, and with a low sample size, typically you don't have a large ensemble to test. And so our approach was to use some advanced statistics and machine learning approaches to do this two-sample distribution of the two-sample equality of distribution test. And a few of them were kernel tests, energy tests, and we did something simple with the KS tests using one-by-one variable testing. So this is just one example of such a test. This is called the energy test. And this is looking at a metric called the E-distance metric. So say you have two ensembles, so X and Y, and in the multi-dimensional space. And what this matrix is looking at is the pairwise distance within each ensemble. So sum of that minus the pairwise distance across the ensembles. So if these ensembles are on top of each other, you'd expect this difference to be close to 0. So the smaller the E distance, the higher the chances that the ensembles are from the same population. And the larger the distance, they are probably likely from a different population. And so what is the null distribution of this distance? We do that with resampling. So we run say a control ensemble, 150 members, and then we compute, and we know that they are from the same population. We randomly sample 30 or 40 or whatnot, and compare this E metric for each such resampling, and you get a null distribution of that of the E distance metric. And now if you have a new modified ensemble, you can compute the E distance metric with the control ensemble and see if it's lying in the range where you can reject the null hypothesis. And the kernel test is something similar. It just, instead of the distance metric, it would have like a kernel function, like a Gaussian radial function or something like that. The other approach we took was a much simpler approach, which is just applying. So So the model has lots of output variables. We just use 120 of them. And a simple approach is we test each one of them, and we compare each variable, say temperature, precipitation, and we look at the PDFs or CDFs of both of them and apply a KS test on each variable. And so our larger hypothesis in this case is yes, the models are similar, but our smaller our local hypothesis is for each variable, saying that okay, is this variable different from in the modified ensemble, different from that in the control ensemble. And we do that for each such variable, 120 in this cases. So in this case, our test statistic, instead of the distance metric we had there, is the number of variables failing in the KS test. So out of 120, how many are failing? And so what's the null distribution of that number? That again, we can grab from resampling. So we did 150 member ensemble, control ensemble, and we grabbed 30 members from there. And we got a null distribution of the number of variables that are allowed to fail if it's from the same population. And the number we came up with was 13 in that case. So we just did a test case. We took a very low resolution model. So this is a 500 kilometer model in E3SM. We ran 30 member ensembles, but with initial conditions. And we changed the tuning parameter. This is ZMC not ocean, which controls the amount of change from cloud droplets to precipitation over the ocean. And this is a very strong change. So you'd expect the test to catch it. And once we do that, we find that both the KS test, the energy test, and the kernel test reject the null hypothesis, meaning it can catch differences like this. But then if you can catch it, so we also want to look at the false negatives or type 2 error rates, which is like, what does it mean if the test is a pass? Is it really similar to each other? Or in other words, what is the false negative rate? So can the model still pass something that is known to be a different model climate? Or in other words, how small a change can the test detect? Or how big an ensemble do we need to catch a particular magnitude of difference in the model? So for that, we used the same tuning parameter, and we have done it this other tuning parameters too. So we changed this first to 0.045, and we did 100 ensembles, and this is the default 0.007. We had another 100 ensembles for that. And then, but instead of going all the way to 0.045, we went to 0.04, and we did another 100 ensembles. And then we went to 0.03 and another 100 ensembles. And then we compare these ensembles against each other, mostly against the default, and see up to what magnitude can the test catch it. So we did this for 30 member ensembles, resamplings, 40 and 50 and 60. And we conduct these tests and repeat it many, many times. And so this is a populated plot, but this is the result of those power analyses. And what we see here is that on the x-axis, you have this different discrete values of ZMC not ocean, for which we ran the 100 member ensembles for each of them. And this is the power, meaning what fraction of the test, or what fraction of the resamples were caught by the tests, because we know we have changed something, so the climate is slightly different, at least in each one of them. So for differences as big as 0.045, for all ensemble sizes, we can detect the difference at 100% rate, all the way back to 0.0073, where everything, we are still able to catch everything. But as you go down further to 0.0073, that's where you start seeing that some tests fall through the cracks. And so, for example, for the 60 member ensemble, 90% of the tests are caught for differences as small as 0.0072. So what is the point of this? So this helps both developers maybe and this climate scientists. If you say that, okay, we ran a test, there was a non-bit for bit change in the model, and our test passes. But what does that mean? That means that your new ensemble is as similar to the default if you had changed your one control parameter by 2% in this case. So that gives some confidence to the developer, some confidence to the climate scientists that, okay, this is a change that we can either take in and not care about it, or this is something concerning, and maybe we need a stronger test, or we need to debug. So this was for the KS test, and we did the similar power analyses for the energy test and the kernel test. And what we found was that the most power comes from the KS test, And these energy and the kernel tests have much weaker power compared to case tests. For example, with the 30-member ensemble, even with that bigger change, the power is only at 60%. So we did this for other tuning parameters. This is an example for DCS. Same thing, we change it to by different values from the default. And we again find that up to like 3 or 4% differences, we can catch it with a 30-member ensemble. And we did this for a number of tuning parameters, and we found that the KS test was still doing better than the kernel and the energy test. And so it seems to be more powerful than the others. And so we have put that test in a framework called E4ESM, Extended Verification and Validation for Earth System Models. It's a Python-based toolkit, and it will do your runs, your control runs, and your new ensembles. It'll post-process, conduct the test, and give you a pass or a fail. And it'll have other plots of interest for each of the variables if the need be. And this is just a real-world example of the test. So this is going back to March of this year. And the tests are conducted nightly now. And so in April, there was a large feature introduced. It was UCI chemistry, new chemistry added to the model, and with a stealth feature, meaning that if you switch it off, the model, the other configuration should not change. But we found that there was something that was causing the test to fail. And so we reported that, and that was fixed in a few days. And that was retracted, and then there was another fix, and we found another bug, and that was retracted too, and then they fixed it ultimately. Yeah. So that was mostly for the atmosphere model, and we have also applied a similar test to the ocean. But so the ocean behaves slightly similarly, but as Dorrit was saying, we only use 5 prognostic variables to test, and we follow their approach. We look at the spatial distribution. The only difference is that we are still doing the KS test, and there's another test called Cuccioni test, but we are doing it at each grid point. But then there are 7,000 such grid points in the low resolution case. So the 5% of them would fail no matter what. But then there are corrections that you can apply, which reduces that number of failures. And this correction, for example, FDR that Michael is going to talk about more, is it corrects it so much that even if one variable fails or one grid point in the spatial domain fails, you can reject the test. And just an illustration of that. We applied this, and we did a empirical false positive rate estimation from there. And we found that, and with the KS test, if you don't do the correction, 426 variables fail in a control ensemble setting where you're resampling and doing 500 such resamples. But if you have applied the FDR correction, then no variables are failing, basically. We applied that, and we did a test case where we increased the vertical mixing parameterization, so GM kappa, from reduced it from 1800 to 600, and we catched that test. And we did the same power analysis framework for that parameter, and we applied that to the KS test and the Cuccioni test, and we find that the KS test was still doing better than the Cuccioni test. And this is in the works to be ported into for E3SM. And that's the summary, and I can stop here if you have any questions.
Questions?
Thanks for the great talk. Super cool to see this work presented. You might have mentioned this early on, but just for clarification, so is there a downside to the KS test?
Yeah, the downside may be that it may not have enough power, all right, for everything. The tests we have done are limited. For example, if you go back.
That was the third one though, right?
Yeah, the third one. So it has power, it has more power than everything else, but the sample size might be in question. How big an ensemble size we need to catch the kind of test that we want.
Are there any differences between these different kinds of tests for like the false positive rate? I apologize if you did present that early on, but.
False positive rate, I think it was similar because it's by design, it's 5%. So even the empirical data was showing that, more or less. Yeah, I think.
Yeah, I'm wondering in your tour, how long does it run? For example,
Oh,
you
so,
one
so
day.
following their approach, so 1 year. So we allow 1 month for the air growth, saturate, and then we look at the year after.
So how often do you run this? For example, you catch the errors.
So this is a very low resolution model. So any 400-500 kilometers, we run it every night. And the challenging question here is, we are testing it on a very low resolution model, but are the results applicable to a high resolution production run, for example? And in a couple of cases where we did look at it, we found that yeah, they were comparing well, but that remains to be tested.
Any other questions?
I really like this KS testing, but the one thing I would add is because we are really looking at the CDF and the largest difference in there.
Yeah.
And in these high resolution runs, we have done this a little bit in the context of compression.
Yeah.
They can be super sensitive. So I think that watching for the false positive rate as you go to high res runs will be really critical.
Oh, okay. When compared to a low res, yes.
Yes, yeah. Because there you have more sensitivity in the CDF because you have a more,
Yeah, over the tails, they are not very performant, yes. So there are other tests that you want to look at, the Earth's distance or one of those tests, which is better in the tails. We haven't done that yet.
All right, thank you very much. Okay, and our next speaker is Michael Keller, and he is from Oak Ridge National Lab as well. So,
I'm going to follow up on this work that Salil has been doing, and then I've been working on him with him, and some improvements that we try to make to the kind of reliability and the reliability of the test itself. So as Salil mentioned, we want to evaluate the changes on simulated climate within E3SM. There's that whole nightly testing suite. There's hundreds of tests. Most of them test just for bit in different configurations, whether that's the compiler or the different machines that we have, restart tests, all of that sort of thing. And then there's the suite of non-bit for bit tests that evaluate if some sort of change has modified the simulated climate that we have. So this includes the MVK test that's Salil developed, which compares these two short independent ensembles. Each one is a 30-member ensemble that's 14 months long. Take off the first 2 months for spin up, and then do global average on all of these variables for the atmosphere model. So we generate a baseline after each approved climate changing code modification, and then every night make a new test ensemble and then do this comparison. And the E for ESM, and then there's also LibKit. That's what actually generates the web pages, but that lets it be user friendly, and folks can click on that page and see. A developer can run this test, or the nightly test produces these output web pages as well that you can drill down and see where the test is going wrong. So we perform this KS test. It's a test on the two cumulative distribution functions across 120 different variables, output by EAM. Salil talked about the 150-member ensembles that were performed with version 1 of E3SM, and then the power analysis to determine this threshold of 13 variables. And then you run it across all of these different variables and issue a pass-fail for each night. And then this is an example of what we get out. This is Cloud Liquid, and it's obviously the distribution of these two variables looks very different. And then there's temperature from the same run that looks, they're different, but they're not statistically different. So our problem was that several nightly tests, which were bit for bit, had output of this test above the threshold for failure and were thus incorrectly identified as climate changing. So was our threshold too low? So the thing that we were doing is each night, instead of using the same seed for the random number generator to generate, exactly the same ensemble that should be bit for bit, we also want to do some science, and we get a completely different ensemble every night. So the solution, number one, would be to revert to just use the same seeds. That solves the problem. If the model is bit for bit, the results of this will be bit for bit. But that's not that interesting. So we wanted to try to implement this false discovery rate correction to account for the multiple tests, because we're doing multiple tests at the same time on variables that are correlated. Let's try to leverage that. So the black line here is before that period that Salil showed. This is when it was the model, at least for the atmosphere and for this particular resolution and comp set, this is when the model was bit for bit, or it should be bit for bit. So our uncorrected p-values, this is the number of rejected variables on the y-axis and the date across the x-axis. And anytime it's above this red dashed line, that means we call that a global failure. And so that's winds up being a 16.8% false positive rate, which is not great. I think everybody would agree. So because we save all of the output from these, we can post-process those p-values. We save the chaos. We can't save all of the output, but we can save some, summary statistics. And we can post-process those and feed them through this false discovery rate correction. I'll talk a little bit more about what exactly that means. But if we correct it, the red line is a correction design for variables that are not necessarily positively correlated. So it's a correction that applies for variables that could be positively, negatively, or completely uncorrelated. So that gives us a false positive rate of 2.5%, which and never 2 nights in a row. On the red line here, they're separated, so we can say, oh yeah, that was a spurious failure because the next night it passed. So can we do away with bootstrapping a large ensemble? This is another question that we would like to answer. Can we do away with bootstrapping a large ensemble to find this failure threshold? So what do? We start by generating a large ensemble using the same setup and simulation duration as the operational test. This ultra low resolution, which is 7.5 degree atmosphere, 240 kilometer ocean, and 14-month simulation. And then each variation of our parameters is going to have a 120 member ensemble that we compare the distributions. So far with these year-long runs, we've tested to determine how small of a change that we can detect. We chose the Club C1, it's a cloud microphysics tuning parameter that's very highly sensitive in E3SM version 1, and the orographic gravity wave drag, which is much less sensitive, as we'll see. And then we compare the distributions with 500 bootstrap iterations, random draws. For this, we didn't vary the ensemble size. That's another thing that we can test now that we have all of these ensembles generated. But we use strictly 30 random from each, 30 random draws for each bootstrap iteration. And then compare the distributions using the KS test, and then apply this false discovery rate correction to the p-values. It's really simple. It just looks like this. Sort the p-values And then the ith p-value is multiplied by its position, its rank, divided by the number of tests that you have. So for this, it would be divided by 120 different. It's the 120 different variables of the EAM. So that's our n for this. And then the ith null hypothesis is rejected if that corrected p-value is less than your chosen significance level of alpha. And then the key thing here that this gives us is that the global null hypothesis, which is that do these two simulations have the same climate, is rejected if any of these null hypotheses are rejected. So our new threshold with this correction, regardless of the this bootstrap ensemble, the new threshold is 0. If it's bigger than 0, then it fails. So this is the number of variables that get rejected are really steep lines here. The dashed lines are varying the club C1 parameter, and the much shallower curves are the gravity wave drag parameter. And so we've got, okay, this is at least 5% of the tests have, or no, sorry, 95% of the tests have at least, so for this line here, this is at least 95% of the tests of the uncorrected p-values are rejected. There's 3. Okay, so that's not a detectable change. And this gives us what we're looking for here is does the green line cross this lower horizontal dashed line before the purple line crosses this higher dashed line? And so the answer is yes. And it for at least 95% of the tests, it works pretty well to correct this and catch.
Hello.
Hello. And catch these changes a little bit sooner, but it's not that good at catching them sooner. So this is the power analysis, and instead of the fraction of tests, this is just the number of bootstrap iterations that have a global significance. So for the purple lines, again, that means that at least 14 or more variables are rejected. And the green lines, that means any variables are rejected. And so at the very lowest, you could say that the uncorrected p-values are maybe outperforming it, but it's really, really close there. And the same, bumping this parameter up to 10%, it takes a really long time for the gravity wave drag to have any impact on this. But eventually it saturates here a little bit quicker for the corrected p-values. So what can the false discovery rate do for our nightly testing? It can increase confidence because the false detection, I didn't mention this, the false detection rate, that's what the global alpha is. So that your chosen significance level is your false discovery rate. So you expect no more than 5% false discovery if your alpha is 0.05. And it also removes the need for bootstrapping to find a global failure threshold when you have changed your climate enough that you have maybe a different variability, and maybe your original threshold is not appropriate for this new version of your model. But it doesn't really make your testing able to capture smaller changes in these tuning parameters, at least not yet. Any questions? Thank you.
Thank you. Questions? I have a question. So in general, like when you get a fail, like you made a comment, like it failed one night, but not 2 nights in a row. Like how do you decide when to take action?
We ask experts. So the people that make the code modifications and people that work on the different components, it's in consultation with them. Do you expect this code to be climate changing? You have a conversation. It's climate changing in these variables. And then go from there.
Any other questions?
So I guess I was a little bit confused why there's only one version to test each night. Is that there's like some blessed branch and only things that got into that then are tested, or it's actually after it's been merged you're testing?
Right. So this is the nightly tests happen on what's called the next branch. So there's the main branch of E3SM, and that's kind of the approved changes. And there's a next branch that gets tested nightly, and those are it's kind of a staging branch that works up to it. That's what gets tested, and hopefully you catch a failure before you get onto master.
I was going to add that, like, yeah, there's the master and the next. Master is also always getting tested. It's just if next passes, then you can move to the stage where a change will go into master.
Yeah, I guess I was just making sure it wasn't the other model, which could be you have some number of pull requests that came in during that day, and at night when you have the time is you evaluate all those pull requests, but then it wouldn't be one every night. So that's why it was okay.
Any other questions? Anything online? No. Okay, well, thank you very much. And next, we're going to have our panel discussion, and Brian Dobbins is going to moderate that. And so if the panelists could please come up. And I think, yeah, five minute quick break. There's no food.
All right, everybody, let's get started in a second. Okay. All right. So thanks, everybody. This has been a great day and a half of talk so far. A large variety of topics, some great discussions that I've been involved in at lunch and elsewhere. And now we've got this excellent panel of people from a pretty diverse set of backgrounds. And we're going to ask some high-level questions. But the goal of this is really to facilitate some conversation. So we have a discussion coming up. We have a break coming up. So I want you guys to think of questions too. I've got a bunch I'm going to start with. But please, if you got a question for the group, just raise your hand. We'll come out to you with a microphone, and that would be awesome. That's the whole point of these conferences. So I'm going to start and have you all introduce yourselves. Just tell a little bit about yourself, what you do, and what your interests are here, and then we'll dive in with the questions. So Eileen, I'll start with you.
Okay, is this on?
Yes.
Okay, so my name is Eileen Carpenter. I work as the Earth Sciences Segment Manager at HPE. So I'm on the vendor side. I worked in applications benchmarking and performance for a number of years. And so my opinions about this are definitely colored by the challenges porting and tuning applications. And then I guess that's it.
All right. Hi, my name is Aaron Donahue. I work at the Department of Energy. I work on the E3SM project, which we just saw 2 talks about the testing of that. In particular, I work now on what's known colloquially as the SCREAM project, which is DOE's effort to produce a very high resolution 3-kilometer model of the atmosphere, and soon we're actually pushing that for the ocean as well. But right now we have the atmosphere component running at kilometer scale, with the effort to sort of focus on getting up to exascale, which we've accomplished and very excited about. So yeah, I've been working on climate model development, so that's my expertise. And most particularly just getting my hands dirty in the CESM and E3SM code bases.
All right. I'm Cousin Piers. I'm from Geon. Actually, I'm beside at the German Climate Computing Center at MTKZ in Germany, and I'm in the Department of Data Management. So I'm not a modeler. I'm a data manager. And essentially, my interest here, or what gave me here, is that we're very much involved in developing new data handling, the workflows for these new exascale system models. In particular, the icon model, which is now actually being run at DKZ in coupled mode in some resolving at mid-kilometer resolutions. So there's all this data handling, very agile development, porting to other computers, this kind of stuff, which is a really, really active environment. And I've got a background in climate science, and so actually I kind of know what you guys all I'm talking about, but I'm actually I'm a data guy. So, and it comes to compression as well. So compression is important. So this is all very exciting. Thanks.
Yeah, hi. I'm Ganesh Gopalkrishnan. I've been with the University of Utah for a long time. You can guess 36 years actually. Yeah. I started with the classical computer science and correctness and all that around 2002. I had a colleague who said he works on MPI. I said, Max Planck Institute? I said, no. He said, there's something called MPI that HPC use. So I started understanding the MPI library, and soon I found there are 12 ways to do sends and receives. And that got me hooked because I like to see these grubby corner case bugs. And sorry, I may go excessive on that, but sometimes it helps to know the extreme failures in a system. My main private achievement is a lot of my PhD students who do excellent training of me. So I'm learning through them. That's about it. About 25 students graduated, 7 in the pipe, and no sign of stopping. I hope, knock on wood. Yeah. Thank you.
Okay, so in the spirit of starting with something fun and a little bit contentious, I'm gonna ask you guys, what is your strongest opinion about some kind of common practice in computational science, and how do we address it? And just to give an example, Ed was pretty strong the other day about unit testing. I raised that I feel it's absolute heresy to do single climate runs. I'm in a lab where a lot of people do that. So what are some of your strong takes that we can learn from, and why? And Aaron, I'm going to start with you. He told me at lunch he was going to argue with me, so yeah.
But yeah, but I sat here so that I would definitely not be the first person. No, that didn't work. I backfired. Actually, so I've been thinking about that question throughout this workshop. So I would say actually my strong opinion has evolved because of this workshop. I would be like Ed. So I would say that in our experience on the EMXX project, so the super high resolution model, is that we did focus a lot on unit testing. And because of that, I've become sort of a new convert to the power of unit testing. And you know, when reflecting upon that with comparison to older models I've worked on that don't have such robust unit testing, and property tests are another one. So I would say that that's a really important thing. And I feel like unit tests are fantastic and I think better understood, but I think property tests deserve their, deserve to shine as well. I think it's going to be really important for us when we want to understand if something is correct. Being able to lean on a property test at least lets us think of things that are not necessarily wrong. And there's always more property tests that you can come up with. So I think that they deserve also to shine.
Great. Yeah, let's go down the line. Yeah.
All right. Okay. That's all right. I think I have two aspects here, especially the first aspect really came to my mind today. Kind of how do you define if a model is actually correct in development cycles? We've got this situation now where at Max Planck and DKZ, where the ICAM model is being pushed very, very strongly at a very, very high pace, which implies that the development process is sometimes a bit mingled. I think Panos can say a bit more about that as well. So, and there is no reference runs, and that's the problem. And so push towards high resolution, and you get pretty pictures, and the model, well, sometimes crashes, and it sometimes runs for half a year, so or maybe a year, and it looks very nice, but you have no idea if it's actually good or not. And it's being said, well, this is the model, it's nice, and it runs. Look at the model, and it's like, yes, okay, it's one run, yeah, okay. So this whole kind of having a clean development process, even if there's high time pressure, which is, I think, hard to achieve, but I think that's a problem. And the other one would be from data management in terms of, I'm going to say the very bad word, fair data, which has been mentioned here, I think, once in this workshop, in the talk of the Yazan Valtool, or maybe twice, I don't really know, not so often, but that this the fair data and reproducible the workflows are not really yet a thing in the community, but it has to be done. Of course, it's a bit of a nuisance, but you have to get there, and steady pressure kind of makes it happen. That's kind of my take.
Great, thank you.
Oh,
right,
yeah. You get your mic.
Yeah, it was a very good setup. Thanks for the question. I think what I will start with is an observation I have made. What's this thing about paranoia? You're doing the same thing twice and getting different results. So I think half of us are paranoid, half of us are not paranoid. But one of the things I have seen is many people. Okay, one thing I noticed in this setting is I heard the word or phrase data races mentioned only a few times. Floating point came up many times. But data races are also going to cause non-determinism and non-reproducibility. And there was a famous bug that kind of made us famous. Hyper is a tool that Ellison worked on. When they ran Hyper under optimization, it used to produce garbage results. When they didn't have any optimization, it worked fine. And it turned out we root caused it to 2 threads writing 0 to the same location. That's it. 0 and 0 is 0, right? Why does it fail under optimization? Any guesses? We don't know. We read the IBM Excel compiler, assembly couldn't, but there is a reason. There is something called word tearing, because large words are not necessarily written atomically. You can write words piecemeal, so it need not clear the word. So things fail under compiler optimization. So one of the common practices in this area is run the code twice to see if you get the same answer. If there is no answer, even for non-numerical codes, they assume there's no data race. It is wrong. So there is something that one has to pay attention to. And to make matters worse, there isn't a single usable GPU data race checker today. I can tell you that, because NVIDIA race checker only checks for shared memory races. There isn't a check for global memory races. Academics built tools several times, including us, but we cannot maintain the tool. The front end keeps changing. So there is no data race checking. So you're on your own in that space. If you want a pithy example that I administer to my students each time, there's a 5-line Java program. It's a hilarious example. You can actually run it with Java volatiles for 2 variables versus non-Java no volatiles. And if you don't have the volatiles, after 7,000 runs, it hangs because the store load reordering happens in the store buffer. So these are all examples that tell me that there is a lot that can be done, even with today's CS knowledge, to correct the myths and gaps. Here I go with some more. IBM Excel compilers -00 slips in FMA for you. GCC's -00 does not, so watch out. Applying a compiler optimization flag doesn't mean the compiler always listens. It listens only when the code opportunity is there. The third is FMA doesn't always improve accuracy. There's one corner case when you have A times B plus A times C, where B equal to -C, the normal non-FMA is better because it cancels exactly. Another thing we have been bitten is -1 mod n is what in Fortran and what is in C. Anyone know? Yeah. -1 mod n is n-1 Fortran, like in mathematics, and -1 in C. So if you try to do a rotation of values in an MPI torus with C, it'll hang because -1 is conveniently dev null, and read from dev nulls are ignored. So there's an orphan sent, okay? So there are a lot of these things we've been collecting. and happy to put many of these out. But the main point is run twice and don't expect that's not good. Okay. Yeah.
Mine is the way that compilers are developed commercially and supported hinders the science that people who depend on those compilers need to do. It drives me crazy that we have OpenMP and OpenACC for GPUs that are both supposedly open standards, but one very large company won't do OpenACC, right, and has a different strategy. There's these competing business challenges that cause these problems that affect you guys who want to write performance portable code. The alternative, which is an open source compiler, doesn't have the level of support that a lot of organizations need, or may not have the robustness that you need, right? Especially with Fortran. And this just seems like a really big problem, and it drives me crazy, to be honest.
Thank you. So what I've taken from this is we have data and hardware issues, workflow issues, testing issues, standard issues, compiler issues, and more. So it's a feel-good story. So does anyone have follow-up questions on any of these for right now? Yes. Here, I'll give you the mic.
You mentioned about the race condition. Actually, I want to ask if you any suggestions say we can check race condition from user updated code. We got this a couple times, but it's really hard to debug and only shows in a certain case. So.
Yeah, well, there are by now some good OpenMP data race checkers, including some that we developed jointly with Livermore that has been productized inside Livermore. It's called Archer. It is Dong An was promoting that a lot. There are subsequently many more. For GPUs, we are actually developing one. We hope it will last. Who knows? But we are developing a Clang-based GPU. But it's a hard problem. It's not very widely solved. We are now working on AMD GPU to CPU race checking. This is becoming a nightmare because CPUs can queue jobs in job streams. Okay, that's a partial order of jobs going. GPUs can pick up the jobs and then send back, and then you can do a stream synchronized read. Then you're okay. But there isn't enough data, so we are struggling with that in a project going on with Livermore. So there are a lot of new opportunities to create races coming. NVIDIA's H100 has a new synchronization domain called thread cluster block, where multiple thread blocks, not all of them, can synchronize. And there is another transactional semantics coming in H100's tensor core. So the more tools we create, the more opportunities to check for races in other concurrency domains are opening up. So let's hope we'll catch up. Yeah. We meaning the community. Yeah.
Opportunities for bugs. I've never heard it put that way, but that's, yeah, right. Any other follow-ups on this? Okay, great. I'll move on to our second question then. So we're seeing a massive diversification of computing environments. This is varieties of GPUs, as you've just been talking about, heterogeneous nodes. Those are going in the new Livermore system, AI, machine learning hardware, floating point formats, and even lossy compressed data. How does this change our approaches to reproducibility, correctness, and verification for climate and weather models and their workflows? What do you feel should be part of best practices moving forward? And Karsten, I'm going to start with you this time. Yeah, I'm rotating, so got to keep you on your toes. Yeah. So,
this kind of goes really much back to the point I just made, is that if you have these new heterogeneous infrastructures which you have to adapt to, for example, Max Planck is porting the icon model to Lumi computers, and it's been ported to the GPUs, and the one component is being run on GPUs in the atmosphere. The ocean compartment is still run on CPUs, but I think by now it's been ported to GPUs. Yes, nodding, yes. But then porting this to Lumi, because of course it's supposed to be an exascale Asian model. It's supposed to do big runs over a long period of time, and for that kind of DKZ is a bit too small. So we have to go to bigger machines to have the Asian run in a reasonable amount of time. but that's a different infrastructure, different compiler options. Annie's already laughing a bit there, and it's proven to be a real pain. Actually, I'm not involved, but I see this very often with the colleagues talking about this, and this is really a pain. But I think that's just the way we have to deal with it, right? I mean, at some point we have to get through, and it's again as well. If you have this model development under high pressure, which has to be done quickly, there are projects which have deliverables which have to be done by a certain amount of time. There's contracts destination Earth. It's got to run, right? And if it just doesn't go as quick as you expected, and then you get, I don't know, maybe it gets a bit too sloppy. I don't want to say sloppy, but it's not so well organized, it seems, and then you get into problems. And I think that is an issue. I think that's my point here. I can look at my notes and maybe I come back later with another point.
Ganesh, I'll go to you next.
Listen to students, read papers, but I guess that's another way of gaining expertise. We can't do it all ourselves, and I had done coding in the past. But let me reflect on things I see. Okay, so recently we contacted a group at Sandia who is working on a wonderful benchmark. They're actually creating it as a mixed precision benchmark. It's a GMRS code, and there's a paper out by Ichitaro Yamazaki, Shivaraja Monikam. Long story short is, if you run in FP32, it runs fine, let's say. If you run in FP16, what do you expect? Well, faster, right? Because less memory data transfers. But sometimes the code loops because the residuals don't go to zero. So this is a danger waiting. So we cannot do it carelessly. So certain iterative algorithms may not terminate. That's one thing. That's one observation. So we had to kind of be very careful about precision tuning because it's an allure, it's a mantra that is driven. One group that I have seen done it well is, I haven't met this gentleman, T.N. Palmer. Do you know? He's a climate scientist at Oxford. He has written shallow water code where he looks at an actual equation system which my student understands. And he takes advantage of that equation and puts in FP16 right there. And it's nice, no problem. And the entire Julia code is well parameterized. So that's an example of a good design where the scientist has used mixed precision in a parametric code. Recently, there was another success, again, benefit of a collaboration where they look at this code called smooth particle hydrodynamics. I guess that is something that people do. And there they got tremendous boost by using low precision. But again, they took advantage of the values being representable carefully by FP16. So if you really know what you're doing, FP16 is a good thing and you can take advantage of GPUs. I used to believe, many of us still believe, machine learning code is immune to low precision floating point abuses, right? We all think so. In fact, if you look at how there's no machine learning these days, largely speaking, at high end without mixed precision and tensor cores. That is a reality. And almost all the large models that are getting trained have to use low precision, have to use tensor cores. Otherwise, it'll take a long time to train. But in there, they actually look at the NAND generation in a feedback loop. They adjust the grading gradients. So if there is too much NAND, then they scale all the gradients, they recover. But a recent article that I put up in my talk by Google shows don't count on it because sometimes the NANDs go up and kill the forward pass or the backward pass. So we have to be careful even in machine learning code with exceeding the representation range and getting into trouble. So this is not a safe area. And other thing is stochastic rounding. I have been hearing a lot about it. I talked to enough experts and GraphCore. Have you heard of the GraphCore CPU? It's not, the company is in trouble, I hear. I don't know whether the company is viable, that somebody is trying to acquire. But GraphCore has stochastic rounding in hardware. So for those who don't know what stochastic rounding is, I just learned recently, you have two representable floating point values and say the calculation falls slightly to the right of the center. because you have extra bits in the inside, right? The usual rounding rules are round to nearest or round to minus infinity, round to plus infinity. Stochastic rounding calculates the distance from the point you land to the nearest representable numbers. And if you are further away from a point, you still have a low probability to round to that. So it actually evens up the number distributions. It shows up. So I have heard that stochastic rounding is inevitable for low precision. I'm kind of believing that. So this is something that I need to pay attention to. The hardware costs are not too high because Graphcore did build it. So that's what I would kind of say, that there are differences and maybe you can package it. But real numbers are a leaky abstraction for floating point. I heard the term leaky abstraction. It means that it's not fully, a real number is not a faithful representation. The bad properties of floating point tends to leak through and bite us. And one space, again, sorry to go long if I have the time.
By all means.
One space where, this is something I don't know and you can tell me. Say you have a matrix with a certain condition number, okay? What's the condition number? I looked up today, okay? Cheating, okay? So if you have a unit sphere, apparently, and if you apply a matrix, which is an operator, the matrix, based on its condition number, beats the unit sphere into a pulp, into a long egg, right? A cigar shape or something. So let's say it beats into a cigar shape. So you then take the cigar's major axis and minor axis and divide. That distance apparently is, do you agree, Alison? Is that working okay? Kind of, okay. So if you have a high condition number matrix, okay. Now if you subject the elements of the matrix to rounding, how does the condition number adjust based on the rounding? This is not a easy journey because word level error and matrix operator level error don't seem to have a direct formula that connects them. You just need to search through. So there are some gotchas where if you precision tune, you may be in the badlands of a matrix diagonal where the eigenvalues sit and you may be in trouble. So I don't know how to bridge that. Okay.
So where I want to go with that question is back to what's driving it. The end of Moore's law is driving this increase in diversity and the specialization of silicon to do certain things well. It's also feature sizes are decreasing. And one of the things that I think we need to talk about that Ganesh may have hinted at, but we haven't really talked about today is how the rate of silent data corruption events will increase as density and increases and data path width increases. And we haven't talked about that. All the talks in this workshop have assumed that the computer is giving you the right answer. And we've seen cases historically, we've seen them with NOAA and their climate models, where they have found problems in processors, they found problems in NICs, they found problems all over. I'm talking 20 years ago. These are going to become more common and they're really, really hard to find. And so the diversity thing, yeah, it's hard. It's hard. I mean, the icon model and having to run on Lumi and Leonardo and Levante, that's hard, right? And OpenAC and OpenMP, yeah, that's all hard and it's a pain in the butt. But a world in which you don't know if your hardware is always giving you the right answer and occasionally gives you the wrong answer is something that I think we need to design processes to deal with.
That was great. Where I'll go with that is maybe from the actual climate model developer perspective and user perspective. And so first with an anecdote, a personal experience or experience of the project. So we, of course, are running on heterogeneous architectures, running on Frontier, running on Summit at the DOE. And so we have a suite of tests that test all of our code for CPUs and GPUs. And a common thing that will happen is that you'll have code that works really well on a CPU, but will fail unit tests on a GPU. And that's very frustrating, especially for traditional climate model developers who are very comfortable dealing with things that happen on host, and it's very straightforward. And then there's these nuances to programming in a way that the GPU will be accepting. So, I'd add that anecdote to say one of the things that we have to think about is sort of this relationship between the software engineers and the climate model developers that perhaps should become stronger because we have always been able to overcome these issues because the climate model developers would see the fail. We could go to our software engineers on the project, and very quickly everyone could figure out what was going wrong, and we were able to move forward. And that actually helps because we also have accelerated timelines, and so the pressure is there to get through things quickly, but the pressure is also there to not let failed tests go by unnoticed. And so from one perspective, just focusing on reproducibility, things that might happen that are completely outside of our realm of expertise, like the hardware not giving us the right answer. We always think computers are infallible. So those kinds of things are the insight that you don't have as a developer that you would have in conversation with software engineers. So maybe as a community, having a more heterogeneous project team is also part of what would be very beneficial. I also just want to add that one of the things we can think about is from a pragmatic perspective and looking at accelerated timelines, et cetera. Coming up with a way that developers or climate modelers can feel confident that their code is working on, say, a GPU, it's not going to be the same answer that they got when they were running on a CPU. And honestly, most development happens on, I think, CPUs because they're just a little easier to work with and we have more access to them, right? So coming up with a sort of pragmatic paradigm for how we can be confident, at least somewhat in our code. We can never be 100% confident, but to establish some kind of confidence. So I'm going to go back to my hobby horse that I was supposed to talk about in question 1, which is where these are unit tests and property tests, I think really shine in the sense that if you can at least run your property tests and your unit tests on a GPU, it does establish some level of confidence moving forward, because ultimately I think we're going to run these codes and then we're going to look at the climate. Like an expert's going to look and say, does that make sense? But also if they feel confident that at least basic properties were established, like were passed, it's more comfortable then to actually look at the end product. And we're spending a lot of money to run some of these models, right? Like, running the 3 kilometers is not cheap. So we want to do it when we're ready.
I found some more points. So coming back to the data question. So I mean, this is kind of the downstream of the modeling. So there's this the one point which was mentioned in the question about the compression. So of course, I mean, if you look at the data which is now being available in the ESGF, CMAP 6, it's I think on the order of 10 or 20 petabytes of data. And if you go to CMAP 7, this is going to be not manageable if we keep data in the format it is now. So we have to invest into deciding on what's the best compression. So there's the ongoing work, especially in the European project, EasyWays 3, where we actually want to develop a guideline or like a document which advises you to choose the best compression for the parameter. So kind of achieving compression rates on of factor 100 or so. So this would actually solve many of those meta storage issues. So that's ongoing work, and that's very important, especially there's actually also ongoing work on actually compressing already data in the model run, kind of in the memory. So that's ongoing work, and the other one is actually data integrity, data security. How do you know that the data which you're getting from ESGF, just for example, and you want to use for IPCC simulations, is that data which is told to be? Because I've heard about this, I think about a quarter year ago. So, and I was maybe too naive to believe it in the first time. If you look at ChatGPT, it's very powerful. And I think you could tell ChatGPT, please modify the output files of, I don't know, some climate model to just give me a bit less warming. And I think apparently that could be possible. So you have to really invest on checksums or maybe identifying metadata by a hash, which is generated by its content to really be really certain that the data which you're getting is that we think it is. And I think apparently that's a problem, which I hadn't thought about, and maybe because I'm too naive. But I think people out there would have interest in actually doing this kind of malicious attacks. So I think that's another issue.
I agree that that's an issue. And there's this group, the Data Access and Archive Working Group, that's part of NOAA Science Advisory Board, I guess. And that's one of the things that we've been talking about a bit, which is, data integrity in the age of AI. And how do you know that data hasn't been tampered with, but also how do you know that it came from the group that's right, that says that it came from, right? There's a lot of new issues that we have to deal with in this new world. And I think people are just starting to think about it.
Yeah, I'll add on the CESM side, we do signatures for input data because the nightmare scenario is you've got an open source climate model by NCAR and some, this is the US, a lot of people are against climate science and they run it and say, aha, the world is cooling, those guys were full of it, but they modified the data. So you got to be able to have checksums on it. But we don't do this for output data, and that's where most people do analysis. So this is a really interesting point and probably needs more thought, yeah. I have some follow-ups, but I want to go, oh yes, all right, good. This is what we want. Yeah.
So we've talked about reproducibility mostly, I think, in terms of sort of day-to-day reproducibility. Does today's build work the same way as yesterday's build? But what about over much longer timescales, like today and a decade from now? Is that interesting? Is that relevant? Do people care?
I would say as a vendor, we struggle with this. We have contracts where things have to stay reproducible once models are validated. And yet, if you need to make a major update in your system software stack, or even in firmware, sometimes you're not going to get bitwise reproducibility. And that's only in the course of one system's life, like 5 years. Can you reproduce something bit for bit that was done on a machine that doesn't exist anymore with a version of a compiler that doesn't exist anymore, right? I'd say no.
So I guess I'll just say from the perspective of in a decade, I don't suspect that we'll be running the models we're running right now. And I think the hope from a climate scientist is that you wouldn't be getting the same answer because that would represent a decade of improvement, right? Hopefully. So I guess, yeah, so I think your time scale, it's interesting to think of your time scale. Maybe a year from now, I don't think that the development is so extreme, right? But that there would be some similar reproducibility. But I think that on the order of a decade, we anticipate, right, that we wouldn't be getting the exact same answer because not on the exact level, maybe still qualitatively, because we'd like to think that we're doing a pretty good job now and that we would just get a more insight a decade from now. So I guess it depends on your scale of reproducibility. Are we reproducing qualitatively what we expect to happen when we do these simulations, or are we trying to get something that's statistically the exact same answer? Oh, cool! Now we can see ourselves.
Yeah, I would say that even in today's, from what I know again through a collaborator, Martin Buscher at Texas State, even in today's situation, even without floating point, there are situations we cannot afford to have reproducibility. So if you want to establish the chromatic number of a large graph, okay, and the number of colors, the minimum number of colors you need, okay. It's something that you cannot do in a scalable fashion. So they only offer certain bounds, like the chromatic number is at least verifiable with respect to the maximum out degree of a node or something like that. So there are heuristics they use. So I feel that the algorithm designers have to decide on what level of reproducibility they want and how it matters. That's what my quick take is, even without numerical.
Thanks, Michael. Very good question. So, from the view of a data manager, of course, if you're a scientist, if you do a paper and publication, you're required to store the input data and the primary data, as it's called, along with the publication to actually be in a fair manner to have it being reproducible for 10 years or whatever. But of course, if you have a very high resolution model simulation, which is expensive to run and involves tons of storage, you cannot save all the data, period. That's always, and to actually be able to produce the plots on a paper, what the scientists they tell us is I'm going to give you the scripts and the settings and the compiler, and then you save that, plus the final output files, which I use for the plots. And then if someone in 5 years wants to do that again, but they can because they have it all. No, not really, because that's really hard to do, right? So, but this is kind of what we're trying to do in my group is to actually think about ways to have reproducible the workflows from beginning of conceiving experiment to the end of the paper, and to then actually have that published in a fair manner. That's kind of really much ongoing research. So what do you need in a workflow for the future? And that's actually quite hard.
So we heard a speaker, I think yesterday, talk about how changing libc on some system changed transcendental or something, right? So how far down the stack do you go with the software that you need to reproduce? And is that actually possible? I think that that speaker talked about a strategy that makes it so that some of those things don't matter. Like you're insulated from that through the techniques he talked about. And I think that's really important because you can't reproduce the environment exactly with the entire stack all the way down to the hardware. And yet those things can affect the results.
Give me 1 second. I'm going to get to you. There's some comments online. Marshall Ward was pointing out that GFDL has actually done reproducible codes across compilers for over a decade, which is surprising to me. I'd love to hear more about that. And Jim Edwards also had a question about containers and whether they'll be able to solve this. And I'd be curious to hear if anybody wants to comment on that.
I'm going to go out on a limb and say no, I don't think so.
All right.
Bridges the last two questions. So there is one use case I'm aware of where it's actually very important for us to have reproducibility on the scale of a decade. We have certain operational systems at NASA where we provide consistent data sets for instruments that have decadal lifetimes. In practice, what happens is we start those kind of operational systems on the latest supercomputer, and as things age, we eventually get to the point where in order to preserve that older operating system, in order to preserve the compiler that they're using, they actually sort of, put it behind yet another firewall. It's not accessible for the general users, and it's just dedicated to this, aging data set. The computing center doesn't like to do this, but that's sort of where we end up. We think that containers could solve this problem for non-heterogeneous type systems where, okay, yeah, the instruction set for Intel is still the same, and so we can freeze that operating system on this thing that's behind a firewall so it can't be hacked and all that kind of stuff. So there are some use cases, but most of the time we don't care.
I think this is a very interesting observation. For instance, JWST is supposed to last 20 years, right? And they're already planning for the LISA mission and so on. So, yeah.
And I just want to say, I think GFDL has done a superb job, and they have, through their methods, found all kinds of problems. They've been forced to do things in very careful ways, and they've done that very well. I'd say most organizations aren't paying as close attention to this as they do.
So I was talking with a colleague recently, who I will not name, but who's complaining, who's a mathematician who was complaining that climate people are so focused on bit for bit reproducibility, sometimes even across like different data layouts or types of machinery, that they neglect correctness. And so you can have a code that's more accurate and more correct, but doesn't have that bit for bit reproducibility. And then you lose performance if you get, so anyway, there's this whole conversation. I don't agree with that opinion, but I can sympathize with that frustration. But on the other end, I had a recent experience of encountering a bug that was due to, basically there was like an if guarded divide where it says, if such and such is greater than 0, then do this division, and then you avoid the divide by 0. But of course, a very small non-zero value, then it gives you an instability. But it turns out that that was very rare, that was bad enough to produce discernible results, or in the case that I had crashed the model, you had to run for decades with a fine enough grid to get billions and billions of runs of this piece of code before it would crash. And once we encountered that crash, we had to back up and rerun the model over and over to narrow it down from like the millions of lines of code that we have to like wherever that block was. And so even just, this is not an exotic form, just like running the same build on the same platform over and over again, needing that bit for bit reproducibility just to find where this bug was. And so one question that I had, given that some of you were talking about either increased issues with like bit flipping or different like deliberately stochastic hardware implementations of various things, is this sort of debugging going to become more important? Because for instance, if there's a bit flip issue, then you can just rerun the model twice more, and if it gives the same answer and doesn't crash, then you know that it's right. Or is this going to become useless because like on a lot of platforms, you're just going to expect non-determinism all the time, and so you'll never be able to get set into easy reproducer again. Right, that was kind of long-winded, but
I will take on it, but I will first, sorry, go ahead.
Yeah, I just wanted to maybe be a bit controversial. I think there's a danger here that we're conflating two quite different meanings of reproducibility. So bit for bit reproducibility has proven to be remarkably effective in climate science for finding bugs, for things that are not supposed to change the model, and somebody screwed up and they did. So that's a bug finding technique. That's completely different from scientific reproducibility. So there's this movement across many fields of science to when you publish a paper, you publish the code, you publish all the data, and other scientists should be able to rerun exactly what you did. It's a myth. Nobody does that. Nobody ever downloads the code from a published paper and runs it, not even in the peer review process. Does anybody ever do that? I mean, there may be a few loonies out there that try it, but really, the amount of work it takes to set up the environment to rerun code from another lab, it's just not worth it. Nobody's going to do it. So what do you do if you read a paper and you think, I'm not sure about their results, I want to reproduce it? You write your own version. That's what you do. And that's really important because you're coming at it from a slightly different angle, and you get kind of two different versions of a run or a model. So the notion that we might need to reproduce bit for bit a model run from a decade ago for scientific reasons, I think does not exist.
So I know that Michael has a question, but I think I'll add on to what Steve has to say. Actually, in a lot of cases, it would be completely infeasible to reproduce it. So, again, we're running 3 kilometer on Frontier. There's not very many modeling groups that can do that. Even if we wanted to do that, we have to get the allocation to do it. And if we get that allocation, we're not going to do it so that we can reproduce our paper from 5 years ago. We're going to do it to do new science. So I think in some cases, especially as we go to these high resolution simulations, it's actually just not going to happen. Like there's just pragmatically, it's not possible.
So I just wanted to point out that in the software engineering and programming languages communities, we do this. Obviously, the scale is totally different. We're not using supercomputers, right? But there's an artifact evaluation process, and the norm now is if there's code that you ran whose results are in your paper, then you should publish the code and publish the data and publish details about documentation for how to run it. And then there are artifact evaluators that run it. Yeah. And obviously in cases where the scale doesn't work, that whole thing falls down.
Yeah, so I'll say while the mic is going to Steve, I'll say, yeah, it forces people to live up to a certain level of high standard. And sometimes in one case, I was adamant at not accepting a paper because they had this amazing algorithm, I won't say what. And the editor-in-chief weighed me down saying the idea matters more, and the other reviewers. Yeah, so this one was a bummer for me because I wish I had that tool. Yeah. Steve.
Yes, so actually that was essentially what I was going to say. The value of publishing your data and your code when you publish a paper is not so that other people can run it. It's to force you to be a lot more rigorous because somebody could look at it.
And in one case, I accepted a paper where there was a Docker which allowed me to run all their code. It was, again, it worked both ways. Thanks.
Yeah, I just want to add a case. Actually, a couple months ago, we received email from a private company because we're running high resolution case in operational settings. And they notify us they are reproduce our results. And they found in the last month, between the 10 days, the results are different. And now they were asking, are you doing some system work or anything? Because after that, they got reproduced. And we realized even for operation setting, such high demanding resources work, and there are someone actually reproduce the work. So it is answer to your question, it's more than just the research community. There are people actually running those.
Sorry, I'll say one more thing. Why did I hear not performance reproducibility so far? In every HPC conference, that's what they harass us saying. Correctness reproducibility is one thing. Performance reproducibility is what we want. So you guys are not interested in performance? I'm just joking, but I mean, in heterogeneity, that's going to bite us, right? I mean, you buy new hardware and you can't get performance reproducibility across your benchmarks. Wouldn't that be bad? You can all answer. I don't know that.
Yeah.
That's all right. I'm just going to come back to Steve's point, you know, of climate models not being able, as well, at not being reproducible. The point is, though, that climate models or a couple of models are becoming such a resolution, and it's planned in the next 5 to 10 years to actually have them be in operational pipelines to inform adaptation policies, stakeholders, societies, you know, the city planners. Just imagine if you have a simulation which that shows a particular extreme event, I don't know, flash flood, storm, hurricane, tornado, yeah, just to name it, but you forgot to actually output a certain variable, right? A parameter, and you want to do it again and run it, and then you have a bit of it, and it's gone. So we have to think about actually how we deal with this kind of stuff in order when climate models can get actually used in an operational setting by, you know, people who matter for society and decision makers. So I think that's also an issue.
I think it is, but when you look at what happens in the weather forecasting community, I think there's a lot to learn there, right? The forecasters don't just look at one model. They look at lots of different models from different places, right? They have multiple modeling suites of their own that are on different, you know, time ahead. I mean, they're looking at more than just a single model when they say this extreme event is going to happen and you need to do something about it. So, you know, I think I'm not worried about that aspect of it.
And this all just comes back to property tests, right? Like, I guess if you can reproduce that your property test passes, that gets at this point that you don't have to reproduce bit for bit, but you can be confident that those things haven't changed.
I just wanted to respond again to something that Steve brought up, which was nobody ever like downloads the code and runs it. I've considered it and still have not been that loony, I guess. But I have tried to reproduce from like a decades old paper, or like one of their figures, because there's a parameterization I wanted to use. And it's like kind of uncommonly used. I just wanted to test that it was right. And I could not get their figure from their equations. And there was a typo in the equation. If I had the code there, I could have looked there and I could have compared my code, their code, and what was written in the paper. I could have figured out where the discrepancy was much faster than, you know, if you have somebody who's still doing stuff that you can email, this is less of an issue, but sometimes parameterizations stick around for decades. I don't know if this person's still even doing climate science. And so these sorts of things do happen like across decades, trying to reproduce what somebody else's code does. It's just in the micro, not in the whole model.
I would say that there is great value in freezing a code base, for example, having a tag associated with that, so that code base can get there. I think just this, maybe just the difficulty of ensuring that if you were to pick my code up now 5 years later, it would be bit for bit. In your case, if you had the code base, you could have copied and pasted it and run it. You probably would have gotten a very similar figure, even if at machine precision, your dots might have been moved, right? You wouldn't have even noticed, and it wouldn't have mattered for you. So I think it's the bit for bit. That's a different kind of reproducibility than, could I reproduce qualitatively? Do I get a figure that looks almost exactly like this figure? Essentially tells me the same thing this figure is trying to tell me. And I'm not worried so much that the compiler has changed to a new version and I'm no longer getting my bits.
Yeah, I mean, we all want machine learning, right? There is an article in ICSI, I can point to you, where they tried LeNet. LeNet is an old neural network, and they cannot get a bit for bit or even test accuracy reproduction. So it's a sad story there. So several places inside the machine learning code, they could have controlled the random number generation or all the mini batching scheduling and all that. And so this is going to be a big worry. The more machine learning code we ingest, machine learning, the reproducibility problem is only going to get worse unless we really get a good handle on the internals of the machine learning system.
So there's an aspect that I wonder about. I don't know the answer to this, but some of you guys may have thought of it. And that is, how does the separation of concerns in the use of domain-specific languages intersect this topic, right? If you have a Fortran code and you see all the code, or C, C++, you can say, okay, I want to run that code. But if your code is written in Python, it's using lots of packages from other people, or it's using the GT for Pi, what does it mean to freeze the code base? Except that you're using things that come from other places. I mean, I guess you take a snapshot of it and say, this is what it was at the moment we used it. Okay, thanks.
Yeah, and E3SM uses submodules similarly, so we can freeze the submodule versions.
And just
Worry
to
about the architectural changes, if you freeze the code, is that enough? Or I don't know.
in my one bit of contentious thing, just to get back to the question that nobody downloads and reruns something. There was a great paper in Science like 10 years ago outside this field. It was in cancer research, and some guys decided to try to reproduce. I think it was 52 different studies. 3 were reproducible, and these are determining treatments for people and stuff like that. So I feel there should be an emphasis on usability and reproducibility, or people verifying that experiments have worked fine. Yeah.
About Eileen's last point, perhaps one thing we also haven't talked about yet is the diagnostics tools that we use. So the models may be perfectly reproducible, perfectly correct, but the diagnostics tools we use may not be. And then so our analysis—
Don't scare us.
our analysis will not be. And so most recent diagnostics tools we use heavily rely on Python, external libraries, environments, things like that. So I guess there are quite a lot of problems there in terms of reproducibility, because you work with one environment, tomorrow you won't be able to reproduce the same environment. So I just wanted to bring that up.
Yes, it's turtles all the way down. Yeah, there we go.
So I work with a high performance, like a high precision data. So this might be a very bad question to ask, but then like I'm not talking about the performance reproducibility here, but if we consider taking a small subset of data to just check for the correctness reproducibility. So within that context, how do you see the Jupyter notebooks, especially in the ML space?
It's a great enabler. In fact, it's a great teaching tool too, and it's wonderful to popularize it. That's what I would say. Yeah. There's an excellent book by the inventor of delta debugging. Remind me his name, German. Zeller. Yeah, Zeller has issued an entire delta debugging book in Jupyter notebooks. These are all simple things one can do and makes both pedagogy and reproduction. Yeah. Yeah, sure. I have personal things I can say, but more power to it. At least it's an enabler. But whether you get better bit for bit reproducibility as a result, that's the second problem, I guess. It enables, I guess.
I think again, just second that is that I think it's a great enabler, but in order for them to be able to be actually reused, of course, you have to comply with documentation standards, document the code well, and then if you want to really share it out there, just to be sure that people who reuse the data do know, or the notebooks, they do know what they do, and that they actually know what they're being used for, and especially also document what they cannot be used for. I think that's also a point. But yeah, I would totally agree. Good software.
Okay, this has been a really good intro to the next question I'm going to ask. Given how complex this space is getting, how do we go about convincing management or funding agencies about the importance of adequately resourcing this? I mean, I'm pretty sure NSF isn't thinking about random bit flips or race conditions in GPUs. They're thinking science capabilities. So what are the approaches we take? And Eileen, I'll start with you this time.
Wow, gosh. I actually I don't have any suggestions there. I mean, this is a serious problem. And just going back to Fortran compilers and acceleration on GPUs, I don't know.
So maybe it's naive, but I think maybe just an honest conversation on the actual dollar cost associated with not taking these things seriously. So I think that goes back to Ed's talk yesterday that, unit tests, a lack of unit tests costs money. It doesn't feel like it does, but then if you're able to have an honest discussion about how much time is being spent chasing bugs that are hard to find because you don't have testing. Similarly, how much time is being spent dealing with a code not working on a new architecture because something goes wrong with the compiler, or we're just not understanding what's going on. So maybe, yeah, I think that, from managers' perspective, they want to be efficient. They want to use the time and the money, the time of their staff and the money they have wisely and as best they possibly can. And having an honest discussion might be a good open door to that.
So when I first saw this question, it reminded me again of data management, because research data management has actually been evolving very quickly in the past decade or so. The advent of the fair data principles and these kind of things. It's now mandatory that you have data management plans, all these kind of things. And at least in Germany, and I think in the US as well, there's actually dedicated funding to really comply with these principles, right? So it took some time. At some point, I saw the benefit of this. So something must have happened to make data management a part of the funding process. I didn't know. I don't know how that happened, but maybe this could be a similar avenue for reproducibility and correctness of codes. Maybe.
I think Brian, Brian, right? Yeah. I think there's another entity. Let's imagine who will be making processors 5 to 10 years from now. Any opinion? I won't name companies, but hyperscalers may be making it. Elon Musk's company might be making the processor that runs HPC as a viable GPU. AWS may be making it. So I think without cooperation from big corporations, which are the powerful entity now, which have tremendous budgets, we cannot solve this problem. So for instance, we had to understand NVIDIA's exception behavior. So where to look, well, LLVM is not good enough. We need to go to machine code. So we decided we'll understand the SAS assembly language. Then first we realized there is no division in NVIDIA. Yeah, I don't know whether you knew that. Division is done by reciprocal approximation using an iterative algorithm, then a multiply. Then we had to figure out which are the source and destination registers. And slowly but surely, we have been reverse engineering SAS to the point we understand it sufficiently. We are not the only ones. There is a company called Citadel. This is a quant trading company. They are reverse engineering NVIDIA. Guess why? Because they want to run GPU code fast for fast trading. So what they do is there is an internal cache for the registers within NVIDIA. So you can rewrite the SAS instruction such that you utilize the cache much better. So they actually are into SAS to SAS rewriting for faster coding. And we have reverse engineered AMD, one of my students. Again, we are in the reverse engineering game now. There is a better group at Rochester who is amazing. We talk to each other. We have reverse engineered NVIDIA tensor cores and AMD matrix cores, and we know that their rounding behavior is different in certain cases, in certain bit precisions. And there's another group, Nick Hyam's students. We know, many of us know Nick Hyam. He's one of the towering figures. His student, Mantas, he has written a paper, which shows that monotonicity of addition is not preserved. What does that mean? So if you have a vector A, vector B, where all the elements of A are less than equal to elements of B, what do you expect the summation of A to be with respect to summation of B? According to mathematics, right? Less than equal to, right? Can be in some cases. If you do not normalize the results after every addition, you can get a greater than. So this can break your triangular inequality or whatever you want. I mean, this is a battle. So I'm really seeing this battle getting worse, not better. And libraries are another closed source. The best linear solvers may be put out by companies. You don't know the innards of the solver. And Kasia Sviridovich at PNNL has written a wonderful paper. She used the best available solvers to solve power system linear systems. And she has matrix with condition numbers of 10 raised to 20. I couldn't believe that, but she says they arise naturally. And then she evaluated all the solvers, and apparently one sequential solver from France alone worked. None of the other solvers worked. So this is becoming, I really am worried about this. I think without, this is in the various reports that NSF and DOE is writing at this point, the report I mentioned. Without manufacturers cooperating, there is really no way to make, because we don't have a specification for the ISA. What do you do then? Yeah.
I completely agree. And I think that the things are getting harder because the players are changing, right? So the high performance computing community used to work with a relatively small number of vendors that were influenced by what the high performance computing community needed. And now the companies with the deepest pockets and the most innovation, or the ability to fund the most innovation, are not doing it for our community. And we have to learn to live with what they develop for other communities and with the constraints they place on us on things like understanding their hardware, right? I mean, it's different from how it was for the last, say, 40 years.
And I guess I'd say then maybe this is you know, common for Alper and Allison. Maybe we need to invite you know, NSF and DOE program officials and maybe some of the hyperscaler people to something like this, or they need to hear the report. Because it's one thing if NCAR says, we need more money for software engineers because it's getting harder, but it's more of a unified message if it's coming from everybody, because it is impacting everybody.
So the notes I have on this silent data corruption actually come from a study that Facebook published. And it was a problem that they noticed in their, they compress and uncompress data. And they were finding that sometimes the file lengths were coming out 0 when, and that was a flaw in a processor that only showed up on like core number 56 at huge scale. And so Facebook is doing research in this area, and they're publishing papers about this, right? And so we do need to be having conversations with hyperscalers.
In fact, there's an article, Dan Reed and Dongara, future of HBC, cloudy and uncertain, the chance of meatballs, I get no. So I think that article has this very powerful.
I might, so Eileen, if you could send us that article, maybe we put a couple of these links on the conference webpage, including the ICCS Reproducibility Challenge one. Yeah, so if you have cool links relating to this, send them to Allison.
So I'm going to be switching gears a little bit, and I don't know how the best way to say this, so I'll just say it in the most blunt way. Is there such a thing as over testing? Like, can you, I mean, because in practice, like the reminded me was the NSF, you know, like my group has a task that's usually bringing some science feature, and of course we want to test that, but ultimately the grant's going to run out of money, or, you know, we have to do things like documentation or performance or whatever. So I'm asking for anyone, like, how do you decide basically when my testing's good enough? Or can you decide that? You know, I mean, when do you, because you can always add another unit test, another property to check, another system. So yeah, for anyone, how do you say this testing is good enough?
That's a good question. So I asked the same question to our unit testing guru on our project, and his answer was no. So it's pretty simple. No, he basically expressed that you write tests as they basically write as many tests as can come to you, right? Like you have to at some point be comfortable with what you've done, right? Like you can't be stressing all the time that you haven't written just enough unit tests. Although he sort of expressed that maybe this is what he does when he's drifting off to sleep. When you're laying in bed and thinking, oh, did I test that one property? Make sure you write it down so that you go ahead and write the test for it later. So maybe the answer is really no, but it's not that you literally just have to stop production because you're in this never-ending pit of writing tests. It's just that maybe the answer is write tests as they come to you. Like if a test becomes apparent, if you fix a bug, I think this was talked about a lot during the meeting. If you find a bug, write a test to fix the bug. And now that bug will never ever come back again. And so these kinds of things mean that it can be organic as you build more tests, I think.
This is an excellent question, and Dorit. Yeah. No, I think here my take on it is try to be in touch with how hardware is getting designed. I try to my best. I talked to an ASML person who was in JuliaCon. They use inverse lithography. I learned what it is. They don't project the actual mask as it should be on the chip. You should see that video. They produce some kind of a very garbage-ish mask, but due to diffraction and all that light interference, it actually projects the right one. It's very cool. So that's where then how do they know that the masks they're producing are right and all that? Yeah, there is a certain yield that they are facing. I recently learned there's a 50% yield. I don't know how they determine that number. This is that's not good enough. So they are going to kick the yield up. Then comes the chip company. How do they decide to release tapes? Do they do scan testing anymore? I mean, in olden days, they used to chain up all the flip-flops and scan in, scan out. I don't think that is possible. So I think there are a lot of critical decision steps where these decisions are being taken by very smart people. So software is one of the things. I don't think software is can take a high position and say, hardware, give me a spec. No, it's not that. I think it's a continuum. And there may be alternatives to CMOS, but I don't see that. I don't know. There may be quantum sometime. Yeah.
I have a new question, though. So if you have more answers, someone else. So my question is, where do the scientists, and even I would include even the stats grad students, let's say, fit into this? Like we are talking about all these complicated things, like the stuff you think about, Ganesh. Like where is the interface where scientists should actually sit? Like should they isolate them completely and they should just talk to computational programmers or something like that? I mean, I think that's a really important question because like the knowledge you have, yeah, obviously apart from everyone here, is we cannot possibly expect somebody, let's say a grad student who wants to get into this field and actually do new science and some aspect of these climate models who have, like they probably need to know something about this, but not all of this because then they're just going to run out of the room. Yeah. So
no, I actually during your talk, I noticed the ECT and I was wondering whether one could use ensemble consistency testing for floating point. Why not? Let's give it a try. I mean, there may be rounding issues, compiler issues, not of your CSM scale, but I may be designing a solver and I might be changing the precision and in many ways. And I want to try and do the principal components. It's worth a try. I think there is something good there. I mean, yeah.
I actually just want to say thank you, Dorit, right? Like that's true in the sense that there's a lot to worry about and it's very difficult for anybody to spend all the time it takes especially when making software to consider all of these things. So I mean, I think going back to not my hobby horse with the whole unit test property test thing, but this idea that if we could have a system that was automated or simple to use that allows a new code developer to answer these questions without having to know exactly what's happening under the hood. Because a grad student has a lot of things on their plate, and this is probably not going to be the first one that they want to do, but I think they would be amenable to running a suite of tests, for example. And when it comes to like, a lot of these testing frameworks like E3SM has and CESM has, right? Like those are tests, the developer's test suite is something that grad students will run. They learn how to do it right away. So if there's an extension of those same kinds of tests, the developer test suite, it looks at bit-for-bit reproducibility or other properties as well. But if we had something that allowed somebody to confidently feel good about their code without having to know everything that we're discussing here, I think that would go a really long way to empowering computer scientists. And actually, that empowerment goes kind of, I think, to one of the diagrams we had, where that empowerment leads to wanting to know more and wanting to continue using these tools and making sure that subsequent code is similarly empowering. I think that's really powerful and very valuable, yeah, for the community at large.
So I've got another question. Can I ask a question?
Can I follow up on that? Oh, cool. Although maps sound a bit like a broken record here, I see analogs to data management again. So do we have this struggle with the customers, the scientists, that especially grad students or postdoc level scientists, they really have very seldomly any idea of what actually data management means, and that's because it hasn't been taught in any way in the curriculum. So maybe it's about actually raising awareness of the issue in the curriculum during studies, to say that, well, this is an important point. If you go into computer science, or if you go into if you go to write code, this is what you might have to look out for, and maybe the level of this, having to accept that this is important and going into this whole process is a bit lower. So maybe this will also help, and this is the very same thing in data management. So but now we have basic courses in data management in grad student courses, which is actually helping a lot. So just raising awareness, I think, would be a good point here.
And
because so I would say I live in a very interdisciplinary world, and I think there's almost like a sweet spot, like if you think about a Venn diagram, that you need to know enough about something to meaningfully have conversations and know what matters. Yeah, at least maybe that's how I think about the world. Yeah, and I find that really, this might happen at multiple levels. For example, your stakeholder, with the example you gave before, that somebody has one run of a climate model, and then they think there will be a big flood, and that's how they design their dam. I'm simplifying what you said. That's really scary, right? Because they should understand there could be 100 runs, and maybe one time you have a flood, and what does it really mean? So I feel like having that level of understanding is really important, so you don't do really stupid things, but you don't have to be the expert. So what you just said, and I think our curricula, maybe it might have to change dynamically.
Yes,
Like
yes.
statistics is the classical example. 30 years ago, I have faculty that taught me, who said, I have never used a computer, but like data, I don't touch that. You do theoretical derivations, and the life has just changed. And the same, I think, is true for scientists. That's very little meaningful work you can do without being able to code to some level. But what that is and how much you have to know, and like if you raise conditions, I think there's no, it would be interesting to do a study of how many people in the science community even understand what that means, and not thinking you talk about the Boston Marathon or something, right? So that's important.
And I think it goes back to the sociological experiment, that if you bring it up, you might actually make them feel guilty for not knowing, thinking that they're supposed to know, right? So you might even stop any conversation before it begins because you've sort of gone in too much in the weeds.
I think this is something can make people unpopular and also contentious. So yeah, in NVIDIA, C CUDA, volatile still has a meaning. Whereas in C++11, they have deprecated volatile. And it's just an anointment to not keep things in register. I mean, these are things that are curious things I pick up. I don't know why, but you need to pick these up to survive. And you sometimes learn these when you're in a PC and you say the wrong thing and the other PC members push back. This knowledge is hard to come by. Yeah. And the same keyword. And Java volatile is not the same as C volatile. This is another thing. So the same keyword. Okay.
So one of the discussion about graduate students made me think about the UFS and EPIC project and the graduate student test, and the goal that a graduate student could download the code, build it, and do science with it. Is that ever going to be possible with coupled climate models? Is that a goal?
Hey, I'm just the moderator. I give you my. I'm going to let people answer.
But,
Yeah.
so I guess Allison maybe has it. So I think that's I think my answer to you would be depend on the group you're in, right? So I would argue that like DOE is very focused, right, on where I don't think we're as focused on whether or not our model could be downloaded by a grad student and run. I mean, we have a pathway. You can look up how to download E3SM and you can try to run it, but our focus is different, right? Whereas I think CESM, maybe the philosophy is different.
Well, I mean, as someone who's had, I don't know whether it's the misfortune or the fortune to have had to port CSM to different platforms when I was in benchmarking, I'd say like, wow, well, that took a year and it was really, really hard. It's not something a graduate student would do.
So I've heard, I will give an answer now because this is CSM's my baby. So there was something I heard about once, somebody called it the tier test. You guys heard this term? And this was, I heard this in terms of the EPIC workshop, and it was how many tears will a grad student cry trying to get your model going? And that's terrible. Obviously you want that to be 0. And I do think that CSM has made great strides. And again, it gets to priorities as an engineer, and it gets to priorities and differentiation. Like I feel there's value in having a widely used, easy community model, even if it isn't focusing on some things like the ultra high res, which we don't have the systems to match you guys on. So there's value in that, and we do spend a lot of effort trying to teach students, and it gets better. But it's still hard getting back to that funding question to get, funding agencies to say, hey, can you give money towards usability, towards ease of use? Because they're like, no, we want a new parameterization for some cloud physics or something like that. And that is a battle. And I think that it's partly because places like NSF are staffed entirely by scientists and not grad students who wrestle with these things. So
grad students once, can't they remember?
They forget, or actually they also say, I went through hell, so now you have to go through hell.
They're paying it forward.
So yeah.
I think that one might make the argument that with the increasing heterogeneity and diversity of technology, that the same kinds of investments that would enable that sort of ease of use will enable productivity for everyone, even the experts who are embedded in it all the time.
So yeah, so maybe I could respond to that though, from the perspective of what E3SM and EMAX-X are doing. So in some regard, we are trying to make it easier for us to move from one system to another, because it is very painful when a new architecture comes online to get our code working on it. And so like EMAX-X went the direction of using Cocos as a way to have this performance portability layer. And Cocos is by no means the only option. But I guess then sort of an extension of your question is to how valuable is it to use tools like that for this case, where potentially someone could pick up a piece of code for their architecture and the barrier for making it work wouldn't be as extreme, provided that they can read Cocos, which is a whole different story. But this idea of having these performance portable codes that don't need to be just wrestled into place.
And while I'm going up here, I would say I often try to make the financial case. If you have 1,000 new users, new grad students, and it takes them 6 months to run the model, well, you're paying 500 years worth of salary to a grad student just to do something that could take a week. So that's a good case.
I guess I feel like I have to jump in here as a grad student who's tried to get CSM running on a system. And I don't know if I cried tears. I go to CU Boulder and we have sort of a small cluster there called Summit. And I think I may have caused quite a few tears in the research computing group due to my request to get CSM up and running on Summit. Actually, there was an older version, but getting like the newest version, not easy to do. So even not as a grad student, with like a person who is like an HPC administrator, basically. But to sort of the other question is like, is that something that could be possible? That's something that's like really near and dear to my heart, sort of just the idea that it's like, could we get to a point where some kind of coupled climate model or climate models in general could be run? And I actually sort of got into this field and got connected with Allison really from a different goal, which is sort of the question of reduced models. What is the value of scientific models that make concessions about sort of their fidelity or accuracy in order to expand their use. And in a lot of fields, that's like a really common thing. There's some high fidelity model, but it's just like so impractical to run on the fly, or something that all of these reduced models have been developed. It's true in combustion codes and all sorts of like civil engineering codes. But it's been somewhat shocking to see that it's not that common. There's sort of this set of like benchmark simpler problems, it seems like, in climate codes. But to me, a big part of this question is like trying to quantify like what is a correct version of a model, is to be able to open this door to saying, now that we've actually sort of characterized the outputs of a climate code, can we go about maybe creating cheaper versions of the model that capture much of that behavior for a much reduced computational cost? And that's a bit different from this like bit for bit reproducibility. But if we're trying to capture some like underlying behavior, and I would be curious if you have any thoughts on that kind of thing. It's something that I'm sort of shocked that it gets talked about, or I haven't seen talked about so much in the climate field compared to other scientific computing fields.
Oh, just real quick, I think for getting a grad student to run very quickly, that is one place where containers can help, because you can give them almost all the environment to run at least a low resolution version of the model, and get familiar with the mechanics of running it without having to bother with the pain of porting it.
First, I wanted to give anybody an opportunity to respond.
Oh, yeah, I was wondering if you were going to respond. Are you planning to respond?
Yeah, I want to add for UFS, we actually, from the developer point of view, we have several developers actually would like to, for example, run the model on their laptop, maybe their own computers, so they can work at home and without worry about HPC and those. So there is a need from inside too. On the other side, we do about the complexity. We try to run a lower resolution test, so can fit into the laptop you have, rather than develop a simple model or simplified model. So that actually give people who are interested in the same code base you can run. But since we are testing and maintaining those low resolution tests, at least you have some kind of confidence, say, okay, I have a baseline and I know someone actually working on the model on the laptop, and I have the same laptop and I can set up this. So if you have documentation, that definitely help the graduate student to start work on it. And if they have questions, and at least there are some developers that have experience to answer them.
I didn't have, I was just going to say, probably yes, but I mean, in terms of like the value of letting there be something that's a little bit more simple that someone can use, maybe it's always based on the application, right? Like the 3-kilometer model is not meant to be the model that we always run, but there's science to be done with it. And it's valuable for informing the lower resolution models as well, which will also be workhorses for science. And so similarly, you know, there probably would be value to having a climate model that could be run for educational purposes as an entry into these more complicated models as well. And then even like the lower resolution configuration might just be that. You can run a low resolution configuration on your laptop. You're not going to publish in Science with the results, but you will understand the science. And then when you do get the chance to use a bigger machine, then you can actually apply that knowledge. So maybe the pathway's already there. It's just maybe the issue with being able to run it wherever you want to. But it looks like we have that option. Running on your laptop or containers might be actually a path forward. Oh yeah, so yeah, that's fair. Yeah, that's
There's
another
both,
point.
but we're at 3:30, so I'm going to let Eileen go quickly, and then we'll close out the panel. And the good news is we can keep discussing this during the break. So, oh.
We have a closing discussion schedule, but we are open to actually skip that, right?
Ah,
Yeah, just
okay.
let Eileen
Wait,
talk
let's
and then
finish this, and then we'll have an announcement from them. Then we have a break. So, Eileen.
No, I was just going to say what he just said.
Ah. Oh, that was super easy. All right, great. Well, okay, let's give a round of applause to the panel. I'll thank them for their time. Okay, and I'm going to give an announcement from Allison first, and then we'll go on.
Yeah, so in the schedule, we have a break from 3:30 to 4, and then the last 4 to 5 was just open discussion. I'm kind of feeling like we just had a great discussion and that maybe we'll just close here. We can still go out. I think there's some snacks, talk to each other, hang out, but I think we won't have the formal 4 to 5 gathering back in the room unless that makes anyone very sad. You can speak now, but before we do release you to the break, Alper just wants to talk about next steps.
Yeah, so I guess Allison will agree with me that when we were planning this, we didn't expect this much interest. I guess we were thinking maybe we would have 10 or 15 talks and we would be very happy. We actually got a lot more than that. We actually had to, reject a really good number of abstracts. So, well, I guess that's an indication of a lot of interest in the topic of reproducible correctness. So then the question is, what should we do next to maintain this interest and maybe turn this into a community that thinks about these topics? So perhaps one method would be to actually turn this into an annual meeting, or perhaps you guys have other ideas on how we could keep discussing these kinds of topics. So if you have any ideas, just reach out to us.
I mean, one plan is, so in the proposal that we wrote to get funding for this, we did say that we were going to write a follow-up paper kind of summarizing what went on, and the committee members have committed to help us, but we would welcome input from anyone. And so please just be in touch with us with your thoughts after. If I'm organized, I guess I could send out some kind of post-workshop survey. Maybe I will do that, not next week because of supercomputing, but in a few weeks you might hear from us about like what worked, what didn't work, what you think could go next, things like that. But I just want to thank everyone so much. There's been a lot of people online, everyone here in person. I really want to thank you. I think this has been really great. And do you have anything else to say? Okay, so I think that's it. So feel free to go out, have a snack, mingle, whatever, but we're not going to come back in the room, do anything more official. So thanks, everyone.